Prova, test, prova. Prova, test, prova. Prova, prova. Prova. Prova, in teoria lo prendo.
Prova. Hello, good morning to everybody. As a president of the Academy of Sciences of Bologna, I am very proud to welcome all of you to this meeting in this important building. As you can appreciate, this is an old building hosting the society since more than 3 centuries, and this building has more than 4 centuries of history. You can appreciate the fantastic frescoes on the ceiling representing the Ulysses history. And Ulysses is a master of the knowledge, the search of knowledge. And this is one reason for the position of the Academy on this building. And also, I hope that you can appreciate the city of Bologna. We are in the center of Bologna. This street, Via Zamboni, is a street plenty of old buildings, a monument and churches, and it's near to the 2 towers. And I know that many of you come from abroad, and so I hope you can appreciate not only the content and the presentations of this important meeting, but also the beautifulness of the city and of this meeting. So I wish you an interesting and fruitful meeting and a good day in Bologna. Thank you.
Good morning. My name is Simona Tondelli. I'm the Vice Rector of the University of Bologna. I'm very glad to be here for many different reasons. The first one is because of this beautiful place, which is always a pleasure to visit. The second is for the importance of this event, and I would like to congratulate the organizers. And I've gone through the program. I've seen the importance of the presentations that will follow. And I think it is very, very important for us to be here today to discuss this magic of glass together. But mainly my happiness comes also from the possibility to see the results of cooperation among different institutions, the Academy of Science, the University of Bologna, the Italian Society of Physics. I think that when we are able to organize such an important event all together, this is always a sign of the good relationships of the different institutions, but also of the importance of science, of research that goes beyond differences and divisions. And in particular, for us, it's really a pleasure to be here in our Academy of Science, because we have a long tradition of cooperation. We are working together as a university with the Academy on many different events. I think we have the opportunity to strengthen still more this cooperation on this sort of scientific events, and also on disseminating knowledge and science among our territories. So this is the first time for me to be here in welcoming an event in this context, and I think it will be not the last one, so that this will be for us a way to reinforce still more our relationships. I wish you a productive day. I'm sure of this because of the quality of the presentations that I've seen on the program, and unfortunately I cannot stay more because we have our Senate meeting now approving the university budget for 2023. So, you know, this is something not easy this year, but I really wish you a productive and happy day. I also would like to take the opportunity to invite you to visit our museum, which is just upstairs here, because there is a beautiful exhibition of Aldrovandi. So if you have time during lunch break or something, I really invite you to have a look at it. Thank you very much.
Okay, good morning to everybody. So I'm Angela Bracco, President of the Italian Physical Society. I want to welcome you here in this very beautiful place and thank the academia for hosting this very interesting day on the subject of glass. So this is a very interesting subject that really, as it was pointed out, put together many competencies. So this is very interesting now to discuss and also to learn about what our colleagues are doing in this particular interesting topic. As you know, the Italian Physical Society has a main mission the promotion and support of physics at all levels, and in particular also in the wider cultural context. So this is really a good example of our promotion, and I think it was done very careful and the program with the very interesting topics are really chosen, let's say, very carefully and very well by our organizers. That is Professor Luisa Cifarelli, that I want to thank in particular for being very active and put together this program, and also with the help of Professor Giancarlo Reghini. So I'm really looking forward, because as it was pointed out, that already from the title, you see that this is going to be a very exciting day. And so I don't want to really take too much time, and I'm looking forward really now to start and listening this interesting, let's say, talks. And so I wish you a very good day, and enjoy also, as it was said, Bologna, because it's a very fascinating city that offers, I mean, the cultural environment here is very fascinating. So enjoy it also the whole day. Thank you very much.
We have now the online address from Antonio Zoccoli, which is the president of the Istituto Nazionale di Fisica Nucleare.
Thank you very much. Good morning. Can you hear me?
Yes,
Hello?
yes. You can hear me.
Okay. Good morning, everybody. Unfortunately, I cannot be there. I am at CERN for the annual council meeting, and so I am stuck here. But I would have liked to participate to this very interesting event. Glass is a very important topic. Usually we think to glass when we think to the glazed window of the churches or a masterpiece of glass in the museum. But we have also to take into account that this is also a technology which is exploited in many research areas, even now. As it is also summarized in the program, we may use glasses in astronomical searches and even in the searches of gravitational waves. Of course, you need an advanced technology. You need mirrors which are able to reflect not the normal light, but the laser light in the infrared window. But it is a fundamental piece of our instrumentation in order to detect this new type of messenger from the dark universe. So I think that the meeting you are attending is very interesting, and I hope you will enjoy all the different parts, all the different topics, all the different point of view from for the magic of glasses. Thank you very much.
So now I can invite Professor Tega, who is the chairman of the first session, to the chair.
Good morning, buongiorno. Il mio compito è solo quello di presiedere questa prima parte della seduta di questa mattina. Saluti, avete già sentito dagli interventi precedenti le ragioni di questo convegno e la soddisfazione dell'Accademia delle Scienze di averlo ospitato. Il primo relatore, quindi la parola in questo momento chiama la presidenza, il professor Giancarlo Righini dell'Istituto di Fisica Applicata Nello Carrara del CNR di Firenze, Italia, ha una relazione molto importante. Why an International Year of Glass? Prego, professor Righini.
Good morning, everybody. Thanks, Professor Tiga, for your introduction. I'm very pleased and honored to be here with several illustrious colleagues to speak about the magic of glass. Mine will be some introductory talk, as I will try to explain why and how the United Nations declared 2022 as International Year of Glass. First of all, let me recall, let me see if it works. As usual, there is some problem. Come si fa ad andare avanti? Ah, sì, sì. Okay, so let me recall that the United Nations started in 1959, 1960 with the declaration of the World Refugee Year to select some specific years as opportunities to mark particular events or to increase the awareness in the general public about the goals and the activities of the United Nations. Most of the international years have been related to social and cultural aspects of human interactions. But in more recent times, there has been an increasing interest for scientific topics. And indeed, they started in 2005 to declare an international year on physics, which then was followed by astronomy, chemistry, to come to this year with two issues. One concerning basic sciences for sustainable development, and the other one, glass. So I'll first try to explain why glass was really worth of an international event. Of course, glass is a material really ubiquitous in our life. We are surrounded by a lot of glass objects and devices. And glass has been also fundamental for the knowledge of the universe, from the micro scale to the very large scale. And indeed, we can say that, for instance, in astronomy, glass has accompanied 4 centuries of advances in knowledge, starting from the glass lenses in Galileo telescope to arrive to the very recent James Webb telescope. Well, really, the mirrors in the James Webb telescope are not made by glass. The structure is in beryllium, which is coated with gold. But over gold, very important, there is a very thin glass layer, which is protected. So glass has always been present, but it has been present in the history of mankind since thousands of years. Because a natural glass, the obsidian, was one of the very first material used by mankind to create tools and unfortunately weapons, since that's one of the human characteristics, thanks to the easiness of working the obsidian. But this is not the only natural glass. There are also glasses which are produced by phenomena related to the natural events, like the eruption from volcanoes, which produces obsidian, or the impact of meteorites, or the impact of lighting. In all these cases, there are very high temperatures, and when there is a rapid cooling of the material, we obtain glass. And you see, for instance, on the right, a marvelous example of a impactite glass, which has been found in the Libyan desert and is dated about 29 million years ago. Fulgurites are also glasses produced in this case by the impact of lighting on sand. So that's something we have been always familiar with. But there are also some amazing histories, so to say. Since in recent times, say in the last 2 decades, there has been a study of the presence of biological traces in impact glasses. Because it seems that actually looking at the glasses created, for instance, here we have a picture from an Argentina crater, where the impact produced glasses which frozen inside some traces of plants, for instance, or molecules. And in some samples, actually, there was evidence for organic matter. So glass, in this sense, is also very useful to study our early history. And here also we see a very nice picture where you see some tubular biological structure. And this comes from a crater some 24 kilometers wide. So it was really a big event, some 15 million years ago. This was in southern Germany. And the amazing point is that someone has claimed that in a similar way, if we study the impact glasses present on the surface of Mars, then maybe we can get some clues about the evolution of the atmosphere on Mars, and possibly also to check if there has been life. That is not only a theory, because in 2015, the Mars Reconnaissance Orbiter actually detected the presence of impact glass. That was possible using a reflectance spectrometry, and the areas which are in green in the picture correspond to glass. So when it will be possible to actually check the composition and the presence of particles inside this impact glass, it may be that we can get information on the very early times of Mars. Having said that, let us also look at what glass is really and what definition can be given. By the way, it's not easy to give a definition of glass, and there have been a lot of discussions among scientists. One point is that, as we have seen in the examples of obsidian and other natural glasses, one of the conditions seems to be that we have melting of a rock or sand and then a rapid cooling. And in fact, if we go in the laboratory and we study how we pass from a liquid state to a solid state, looking, for instance, at the variation of the volume of the material or another property like enthalpy with the temperature, what we see is a plot like this one. Let us start from the upper right. We are in the liquid state, and when temperature goes down, viscosity increases. And when we reach the temperature which corresponds to the melting of the solid, we have an abrupt change. Sorry, I wanted to have a pointer. Yeah. At the melting temperature of the solid, we have an abrupt change. And then again, the volume starts to decreasing, but at much slower rate than in the first part. So here we have the passage from the liquid to the solid phase. And in this case, the solid has a very ordered crystalline structure, which corresponds to the minimum energy. But there is another possibility. If the cooling is very rapid, and so the viscosity increases very rapidly, we do not have the passage to the solid state, but the liquid continues to say exist in a very viscous form, which in fact is called supercooled liquid, and only at a lower temperature than the melting temperature, we have a variation which brings to the solid. And this is called the glass transition temperature, and this is the characteristic of any glass. To give a say, graphical depiction of the phenomenon, when we are in the liquid, when the material is in a liquid phase, the molecules are disordered and they can flow freely. When we have the passage to the solid state, the molecules tend to organize in a very ordered structure, and this is the crystalline structure. But when we have a very rapid cooling, and so a very rapid increase of viscosity, the molecules do not have time to rearrange, so they are in some way frozen in a structure which is similar to that of the liquid. But we are now with a solid, and that's glass. Of course, there are very many glasses, depending on their chemical composition. And we can speak about glass families. The most common is that of oxide glasses, which are formed by oxides of various elements. Here, say the master of the house is silica, silicon dioxide, which is may form glass by itself or together with other oxides. So we have different glasses which are called silicates, phosphates, and so on. But just to have an idea, over 75% of the manufactured glass is formed by so-called soda lime glasses, which contain a large majority, more than 70% of silica, and then other oxide of sodium, calcium, and so on. So, for instance, most of the glassware that we use every day, or also most of the art objects, are actually made by oxide glasses. And of course, depending on the composition, we can get very nice colors. But from the technological point of view, maybe the most important success of silica glass has been the realization of optical fibers, which are the most important technological issue in the development of optical communications and internet like it is now. And silica fibers are made by just ultra pure silica, so very simple in principle. But as also Dr. Zoccoli mentioned, we also want to look at infrared radiation, for instance. And silica has a limitation that is transparent only in the visible region or the very near infrared. So other families of glasses, which can be classified under the label of chalcogenides, based on fluorides, sulfides, and so on, offer the possibility of looking at infrared radiations. And by the way, Professor Angela Seddon later will speak about applications of chalcogenide glasses, since infrared is very useful in medical applications, in the help to the driver, or in the investigation of health of heat diffusion in the buildings, for instance. Of course, all this activity on the glass has involved a large number of scientific works, and the paper, a review paper published in 2014, has made evident that there have been more than 200,000 publications in a 40 years interval. And in the recent years, there have been more than 5,000 publications per year. And if one looks to the various kinds of glasses, you can see that oxide glasses are always the most common topic. But of course, research has not been self-consistent in the sense that it has been important to transfer research into manufacturing. And again, we can look at numbers indicating the number of patents which have been, for instance, almost 100,000 new patents in a short period of 4 years, from 2010 to 2013. Of course, all the glass manufacturing has a very big economical impact. The market in last year was valued at some 106 billion US dollars. And there is also the prospect of an increase at about 5% or more per year in the next years. In terms of production, the annual production is over 200 million tons, which is again a huge number. And in Europe, last year, production was almost 40 million tons, which makes European Union one of the largest producers together with China and North America. All these developments in glass science and glass technology, glass production, have made some colleagues in Corning, which is an American glass manufacturer, to declare that after a space age and an information age, we are now in a glass age. And let me just read one of the sentences in their article. We have an unprecedented opportunity to harness the unique capabilities of glass to solve some of our world's most urgent challenges, such as more effective health care, cleaner energy and water, and more efficient communication. So I believe that in this way, I have made clear enough why the glass was worth of the recognition of an international year. Let me now say how United Nations came to this recognition. We have to go a bit back to the starting of the industrial production. Of course, there is no precise date, but we can think about some important points. For instance, 1825, when the first commercial glass pressing machine was invented, and then in 1904, when a machine was developed which could automatically produce glass bottles. And that was a revolution at that time for glass industry. A second revolution occurred a bit later in 1959 when the float glass was invented to produce flat glass. Flat glass means glass in large sizes like the ones used for windows in architecture, buildings, and so on. Just to have an idea of the steps we have made, that was a pressing machine around 1910, and the same period we have this quite complicated glass bottle automatic machine. Of course, the development of the industry made evident that there was also a need of establishing some common terminology, the specification of glasses, the testing, the quality testing procedure, and so on. And one person who was really very important in this area was William Turner from Sheffield University. By the way, we have here another representative of Sheffield University, Professor John Parker, who will speak after me. And an important point from our point of view was the fact that in 1916, he founded the Society of Glass Technology in UK. Of course, he was the first secretary, and he was very active in establishing contacts with glass experts in other countries and with the newborn glass societies. Just some important dates. In 1898, the American Ceramic Society was established, and in 1922, the German Glass Technology Society was founded. So these contacts also led to some joint meetings. One of the first meetings was in Aachen, in Germany, in 1928, between the English and the German society. In the picture, you see Turner is on the light. And as a result of these contacts, in 1933, an international congress on glass and ceramic was held in Milano. The technical sessions were held in Milano, and after the technical sessions, the glass experts went to Venice, and the ceramists went to Florence. And what was important was the fact that at the end of the Venice meeting, it was decided to establish the new society, the International Commission on Glass. The first board of ICG was seeing the presence of representatives from Spain, USA, France, Germany, Italy, and of course, William Turner was the chair of it. And it was decided to hold the second ICG Congress in England, partly in London and partly in Sheffield. And you see here, there is a picture of the participants in the London conference. Of course, shortly after it, the Second World War was starting. And of course, that was breaking a lot of these links. And even after the end of the war, it took some time before all activities could start again in a regular way. But eventually, in 1953, that is exactly 20 years after the first Congress, it was decided to take the third Congress again in Venice. And since then, the ICG Congresses are held regularly every 3 years. And the last one was held in Berlin the past July. Just reading an article of ICG Constitution, the aim of ICG is to promote and stimulate understanding and cooperation in the fields of science and technology, as well as art, history, and education. So it was to be expected that also inspired by the declaration of other international years, like the International Year on Light and light-based technologies, ICG was thinking about an international year devoted to glass. So in 2018, a committee started to discuss about this proposal. It received the consensus by a large number of academies, associations, companies, and Italian Physical Society, of course, was one of the endorsers of the proposal, which was submitted to United Nations in 2020 and eventually got the unanimous approval in 2021 on May 18. Of course, in the proposal, besides all the scientific and industrial aspects, it was also underlined that glass, as an overall, in the sense glass industry, glass science, may well participate in reaching the goals of sustainable development that have been put by United Nations in the 2030 agenda. And just to give a few examples, glass is one of the most recyclable materials. It has a variety of roles in reducing greenhouse gas emission. It is made from widely available materials, is contributing to health and medicine technologies. So this year has seen a large number of events, conferences, exhibitions, practical laboratories, especially for the youngers. And it has been, I believe, a very successful event, which will not end really this year, because there are already a number of events which are in program for next year, for instance. And 2 days ago, there was, say, a final ceremony, the briefing at United Nations building in New York. And we have here 2 participants at the briefing, Professor John Parker and Dr. Teresa Medici, who have been so kind to reach us just after that event. And we can say, using the words of Alicia Duran, who is the past president of ICG, goodbye IOG, but welcome to the age of glass. And so at this point, I can also conclude thanking a number of persons and organizations, and thanking all of you for listening. Thank you.
Thank you e molte grazie. Preferisco parlare in un buon italiano che in un cattivo inglese, ma ho poche cose da dire. Credo che tutti i presenti debbano ringraziare il professor Righini per questa amplissima analisi della situazione di chi studia, di chi opera, di chi si occupa del vetro. D'altra parte voi siete riuniti per questo, per una grande occasione. In effetti l'interesse per chi ascolta queste cose, che non è un esperto di fisica o di chimica come me, è quello di vedere qual è l'ampiezza della presenza, la radice storica molto lunga e la utilizzazione adeguata e forte, sempre maggiore, del vetro. Il vetro è eterno, il vetro non finisce mai. E quindi ti ringrazio molto per questa relazione, credo che ti ringrazino anche gli altri, e possiamo passare ad un altro argomento che verrà. Prego. Professor John Parker, nella University of Sheffield, UK, The History of Glass. Dunque passiamo oltre. La storia del vetro è una storia affascinante, molto importante, della quale anche noi possediamo qualche frammento, ma la parola, professore.
Thank you very much. I have no idea what you said about me. Right, okay. I'm going to talk a little bit about the history of glass. Now, of course, we've had a good historical development already, and so I'm going to just focus on a few particular aspects, a few particular stories. It would be impossible to cover the history of glass in half an hour. And I thought I would start here. Now, this is from a newspaper. This is the perception of what glass is like. And there we have 2 people carrying a pane of glass, which the pedestrian couldn't see. And so he ran into it. He thought they were miming. Okay, glass is transparent, a very transparent material. And why is it transparent? And is it as good as that picture suggests? Well, it's transparent because it doesn't absorb particularly strongly. And we'll come back to that. We'll expand on that. It's not reflecting. And again, that's an important assumption, which isn't quite right. And where it assumes that there's no distortion due to refractive index variations that would upset the image. We use the same idea in IOG in developing the arguments. Here we have a young man looking through glass, and what we tried to convey in IOG was that we tend to look through glass without seeing it's there. Now, given that you are a physics society, I thought I would slightly change the wording. We so often look through prisms and lenses without noticing they are there. Okay. I also looked at the title of your event, which is The Magic of Glass, and I couldn't avoid including some magic tricks in the use of glass, and we'll have a few more as we go through. This is from the 1850s, and it's a theatre where you can see a ghostly figure under the stage being illuminated by strong lights, being reflected by a glass pane onto the stage to haunt the actor on the left-hand side of the stage. Clever bit of acting to pretend the ghost is there when it isn't there at all. Okay. Now, we said no absorption, no reflection, no distortion. Well, of course, we're relying on reflection there. And typically glass has a reflection, typically soda lime silica Right, batteries run out. A glass of water. Sorry, Oh, there's water here. Right. Now, this is terrible. Even the container isn't what it should be. Thank you very much. Right. So let's move on to the next slide. Back to magic. 1550 or so, 16th century, person called John Dee, and he got an obsidian mirror from the Aztec Empire. And the fact that you could see a faint reflection in the mirror, he used to con people into thinking that they were seeing their ancestors. And he earned a lot of money through the wrong misuse of magic and reflection from glassy surfaces. Right, so I've explained that the problem of making flat surfaces is that you can blow glass, which gives you a curved surface. So let's just see how people did things. Well, okay, the alchemists use the ability to blow and to produce curved surfaces to do all sorts of interesting things with chemistry and developing medicines from plants, etc., etc. Okay, we have Roman glass, which is blown. I am always amazed by the uniform thickness of Roman glass and just how thin it is. Raises all sorts of questions in my mind about heat transfer and how they managed to get such a uniform temperature, uniform viscosity to give them such a uniform thickness. There's a problem, there's a subject for your next meeting. Right, and of course the Italians, Venice and so on, used to like making things like this. Again, a bit of magic. This is a blown article with some tubes on the side. This was used by rich people to fool their younger guests who were a little bit naive. They would come to a party, they would be given this full of wine to drink, and they would tip it up to have a drink, and the water would pour out of the wrong nozzle all over their best dinner jacket or whatever. You have to put your fingers on certain nozzles in order to get it to work properly. So yes, blowing, fine. Now this is a picture of, I think, around 1700, 1750. And if you look on the bottom right-hand side, you will see someone who has blown a cylinder or blown a bubble which is elongated. Now that's one way of actually making flat glass pre-float glass. So you've got there a cylinder, you've got the ends on it which have to be cut off, but you can take that cylinder, you can cut along it, and you can open it out. And that was one of the ways in which most of the glass for places like Hardwick Hall and so on was made. That's one way. The other way, on the top or halfway down the left-hand side, you'll see a disc. Now, to get from a bubble to a disc is not at all easy. What you need to do is to blow a bubble and to then put that bubble onto a second blowing iron, break off the first one to create a small hole, and then to spin the disc very quickly to make it into a flat sheet. And by around 1800, they could spin a sheet that was about 1.5 meters across. And that limited the size of your windows. And why in England, Georgian windows are small windows. Okay, that left a little lump on the middle bit where the blowing iron's attached. Waste. Or perhaps not waste. Glassmakers are always careful with their products. So they did a market survey and they realized that there was a market for these bits of glass. And the market they found was you take it along to a public house where all the men have congregated to have their long conversations over a glass of wine or a pint of beer. And you put these in the windows so that the wives can't see what's going on inside. Okay. There's something which to me really stands out at the moment. It's a piece of jewelry made from a broken bit of glass, which has got into the sea and been ground down by the action of movement and sand grains and so on, and created sea glass, an item of jewelry. And when you contrast that with what you see of oceans full of plastic, it's quite a powerful image. Right, okay, as we've learned, glassmaking is all about viscosity. Some of the things you can do, you can make a hollow tube just there for your thermometers, you can make beautiful paperweights, the top ones are Egyptian glass and so on. And okay, I'll just go through these quickly. These are images which show glassmaking up to 1959 float glass. Okay. You can see there the glass flowing from the furnace, the glass melt flowing from the furnace onto a tin bath. The whole thing is under a hydrogen containing atmosphere. It's not 100% hydrogen, it's 3% hydrogen or so. Okay, and that's still the dominant way of making flat glass. There is another way now that's used for making the covers for mobile phones. I'm not going to go into that. There's some interesting science involved in that. It's not all straightforward. For example, when you float glass on a tin surface, and if you let it reach equilibrium, what is the thickness at which it's going to end up at? It depends on the densities. It depends on the surface tension of the air-glass interface, the air-tin interface, and the tin-glass interface. And it turns out that the equilibrium thickness, if you don't do anything at all, the equilibrium thickness is about 7 millimeters, which is close to a commercially useful thickness. And it might have worked out as being 1 meter if the physical parameters hadn't been appropriate. Okay, so there are various tricks that you can use to either make it thicker by putting dams on each side to stop it flowing out, or you can stretch it by using rollers to make it thinner. And what you get is glass which is almost flat on an atomic scale. Of course, the problem is when you're looking at things this flat, you're worried about vibrations. So train lines nearby, traffic, all these things can be important. Now, tin on glass. Is the glass completely inert? Well, the answer is no. And some of the tin does end up inside the glass. Basically, your glass has oxygen in it. It has species like iron 2, iron 3, which are oxidized and reduced. And what happens is that the glass at the surface becomes reduced, more reduced than it is. It oxidizes the tin, and the tin starts to exchange with the sodium ions in the glass. And you end up with a sodium, you end up with a tin profile. Okay, and there's the profile of the tin concentration in the surface. And you look at that and you think, what a strange profile with that bump in the middle. That doesn't look like it follows fixed laws of diffusion at all. Okay, you can get an idea of the depth of penetration, 8, 10, 12 microns, something like that. But why the bump? Well, we've got tin metal on the outside. The tin dissolves as tin 2 and tin 4. And near the surface, which is very, very highly reducing, that profile is only tin 2. Further down, the glass is slightly more oxidizing, and we get tin 4 as well. So the extra bump is tin 4. The tin 2 continues on its typical diffusion-like profile all the way down. So there's some interesting things in glass about redox chemistry. And going back to our sheet glass made by the Romans, even they realized that according to the minerals they used, the mineral sources they used, the glass they got was green or less green. And the Caesars didn't like green. They wanted less green. And the redox interaction between things like manganese and iron were very important to the early glassmakers in making glass more transparent. Now, of course, it also matters to have as low iron content as you can. And these days, with glass being involved in photovoltaics, they are making low iron glass sheets because the iron absorbs, the iron 2 absorbs at the same wavelengths that you're using for your photo cells, 1 micron. Okay. I'm not quite sure what time I'm meant to finish. I've got plenty of time, right? Right. Good. Okay. So there we have the explanation of the tin 4 and the tin 2. Okay, let's go on a little bit then. And there you see how the iron redox changes in the two regions where you've got just tin 2 and tin 4. Now, these kinds of tricks for diffusing things in from the surface are being used to create optical waveguide structures. And there's a very interesting one here, which is diffusing silver into a glass rod in order to create a waveguiding rod with a higher refractive index at the surface than the core. This is the concentration of silver from the surface to the middle. So we've exchanged sodium and silver. And again, we've got a funny kink in the curve. And the reason for this is that at the surface, the concentration of silver is such, and the concentration of iron is such that we are precipitating silver metal. So we have silver ions in the surface, but we also have silver metal. So again, there are two species, and this has to be taken into account in explaining the concentration profile. And we're going to learn more in a later lecture about the Lycurgus cup, which relies very much on these kind of redox interactions between different species present. And I'll just go back to this one. You can see here the yellow of silver in the lower picture of the two. That's been produced by painting silver salts on the surface of the glass, heat treating it while the glass is still solid at around 400, something like that, 350. The silver ions diffuse in, and they're then reduced by the iron in the glass to silver metal, a colloid, which gives this beautiful yellow color. The red of the cup is actually a copper red. You can do it with gold. Again, you are producing nanoparticles of gold, of silver, and of copper. And what you have to do is you have to dissolve the copper, the gold at the melting temperature. You cool down and you rely on a second species becoming more reducing, and as you cool it, and suddenly you get to a temperature where you prefer to have the silver metal rather than the silver in solution. And you get a very high, well, you get an awful lot of copper, silver particles produced, and their size is nanocrystalline. There are a few nanometers in dimensions, and the color arises from plasmon oscillations of the free electrons in the copper and the silver. So, okay. Glass history has evolved dramatically over the centuries. The Romans and earlier generations were incredibly gifted in what they could do. And they did it without necessarily understanding what they were doing. But they got it right. The interesting thing about many of these things, like that cup just there, that cup comes from a film. And it was a film about, I think, a Czech village where they specialized in making things like this. And the person who is in charge of the glassworks knew how to do it, but he wouldn't tell anyone else. And at some point he died without passing the secret on. And the film is all about the story of what happened to that village in sorting out that situation. I shall stop there. The magic of glass.
Thank you. Professor Parker, per questa relazione. Sì. Sì. Ma vuoi fare un break? Quindi domani il break. Bene. Thank you. Mi sembra una relazione straordinaria questa, non solo perché ci ha mostrato, come dire, quella che ha chiamato una una storia del vetro, ma mi sembra una storia che abbia aspetti artistici, scientifici, tecnologici e naturali, quindi è un problema della presenza del vetro nella nostra civiltà. Io intanto è possibile rivolgere a questo punto domande sia alla prima comunicazione che a questa seconda. Vorrei aggiungere solo una piccola cosa, magari poi, che in sostanza già alla fine del XVIII secolo, anzi alla metà del XVIII, quando vengono pubblicate le plans dell'Encyclopédie, ce n'è una particolarmente significativa che io consiglio di andare a guardare attentamente, che è quella che riguarda il vetro. È una planche costruita secondo le tecniche di Goussier e secondo tecniche molto raffinate, che propone per un verso l'origine della materia, la lavorazione della materia, gli aspetti nei quali la materia è fondamentale. Non c'era la plastica. Per il XVIII secolo era fondamentale il vetro. Del resto era fondamentale anche per prima, perché quello che ci ha detto il professore Parker è molto importante. Beh, è molto importante che, come sentirete oggi peraltro, che il vetro ci è stato necessario per gelarci il cielo. È incominciata questa storia molto tempo fa, direi che ha avuto probabilmente una consacrazione con Galilei, anzi consiglierei di andare a vedere a Firenze il cannocchiale di Galilei per capire come sia stato possibile attraverso il vetro realizzare questo capovolgimento della concezione del mondo. C'è uno spazio per le domande, sia per la relazione del professor Ghini che per la relazione del professor Parker. Question? Professoressa Cifarelli.
So just to break the ice, I have one question for you, Professor Parker. You said that just related to the end of your talk, you said that these techniques for painting or decorating the glass were absolutely empirical. I mean, they were applied, and it turned out that they were absolutely rewarding, beautiful. But my question is, were they done in special, because I cannot imagine that it was only transmitted by oral communication. There must have been manuals and some communication, scientific or almost scientific communication practice, even in ancient times. Can you tell us, I mean, texts must have been found related to all this.
Yes, giving recipes to glass. Yes, you can go back a very long time and find texts on glassmaking. It's the tricks that I was talking about, the special things that people tended to keep secret, but there's information about the general areas of glassmaking. And just to tell you a little story, glassmakers, I think at the beginning, basically used two components. They started off with as simple a system as they could. So they had sand and they had a flux to make it easier to melt. But if you make glasses these days, we use pure chemicals. So if you take silica, and if we say that their flux was sodium carbonate, if you mix the two things together and make a glass, you get a glass which is water soluble. And you have to start then saying, well, what's the difference? And of course, the difference is that the sand they used wasn't pure sand and would have things like calcium carbonate from sea creatures and so on. And that was very important in making the glass more stable. So studying the ancient texts does provide some useful information. But I think it also, they didn't understand atoms and so on. They didn't know what they were talking about. I'm trying to choose my words carefully. They did things carefully, but it worked. They did what worked, and it worked. We understand now why it works. Yes, yeah. And I guess Teresa is going to talk about this later on. Yes.
The problem is we start to have text about how to make glass since the medieval time, but then modern time technicians are trying to experiment with these recipes, and most of them don't work. And so the idea is that these texts are not exactly what we think they are. They're not instructions for other people to do glass. They are something to do with the alchemics, and they collect several information about property of substances that you can add to the melting, but not all of them are really right or transmitted in order to make other people able to replicate the glass. So it's classified. Yeah, yes, most, yes, like a secret or text that you need to interpret. And there were some Venetian people like Marco Verità, Cesare Moretti. Mainly Cesare Moretti was a technician of glass, so he was very able to understand the words and the substances, the material that were mentioned in the text. And thanks to them, now we realize that some of the recipes are working and some are other things. So it's not so easy, this kind of transmission of the knowledge about glass.
Could I just add to that and say that last summer we went for a holiday in Scotland with my wife, and we went to a library that was 350 years old. And we were the only visitors. For some reason, ancient libraries don't attract large numbers of visitors. I don't quite understand why. But the librarian very kindly started to look for things on glass. And he found a description on how to make, I think perhaps toughen glass, I can't remember now. But the description was based around the blood of a bull. And you heated your glass in the blood of a bull, and that produced the effects that you wanted. And you think, well, what on earth is that about? But then you think, well, could he have been talking about the color, the temperature of the hot glass? I don't know. It's fascinating reading old texts, isn't it?
About the temperature, I'm guessing that the maximum temperature that could be reached is a function of time, of the technology. So in this period, how much was the temperature that could be reached, and how that determined the technology of having a good glass, let's say. I'm guessing that the temperature was not too much, maybe 1200 degrees or something. How the temperature evolved with time.
Okay, I think we're talking about maximum temperatures in a wood-fired furnace. Wood was their fuel, and they would get to perhaps at best 1200. The melting point, the liquidus temperature, which is the key thing for a typical soda lime silica glass is somewhere around 1,000. If you have more flux, you can go lower than that. But if you have too much flux, you get a glass which is not very stable. So they were melting at 12, they had to achieve 1,000, and the flame temperatures were 1,200. It took them a long time. And I think there's a technology that was used where they would have a furnace that would actually be fired for perhaps a month. They would then knock down the furnace, take the glass out, and transport the glass, which could then be reworked at a somewhat lower temperature to produce the kind of things that we're seeing here. So the process of melting and shaping, at least in some technologies, became separate.
Yes, thank you. No, because in Roman times, the production of glass were split into separate phases. What we call primary production is the melting. This was made in very few, very specialized places. And at the moment, we know few of them. They are on the coast of Israel. And because there was the sand and there was the natrum, that was the mineral soda coming from the Wadi Natrum in Egypt. So there were enormous tank furnaces that were only making this enormous sheet of glass. Then it was broken and was commercialized all around the Roman Empire. Of course, the secondary production was much easier because temperature needed was lower. And then adding the cullet, they were able to lower a little bit more the temperature. So, but as Professor Parker told, time was a key factor. So they were firing these furnaces for weeks or months, and also to remelt for blowing objects. Also, you need several days in order to reach the right viscosity and temperature. So they were combining these two.
And I think the cullet would have been used as ballast in the ships as well. Yes. So, you know, they made use of everything. Just to add one little story to that, there is flat glass being made in Australia, transported to Austria to have a coating put on the surface, which shows the value of the coating.
Going back to your question, Luisa, actually there are some written documents. For instance, Padre Antonio Neri in Florence, who made some of the stained windows, has also written in 1610 a book on the art of glass in 7 volumes with the recipes for the different colors. Of course, some of the recipes were a bit strange, so to say, and the chemistry was not so understood. But anyway, there are some attempts to transmit the knowledge.
In more recent times, I guess so, yes. Yes, just a second.
May I come back to the question I got not clear enough? The lenses that have been used by Galileo Galilei to build his telescope, where seen one this morning, this is optically perfect, it's diffraction limited, and there is no defects. The MTF has been measured by a group in Florence many years ago, l'Istituto Nazionale di Ottica, to have that, and Galilei writes in some letters that to have such glasses or lenses, of course the lenses have been done since a few centuries then, but to have that quality, the telescopes were built since the middle of 1600 by in Naples, everywhere in Italy and in Holland. But to change from a toy to a scientific instrument took Galileo Galilei and took having a technology to produce defect-free lenses. That, I guess, that depends also on the temperature of the glass. That was maybe the root of my question. If
Temperature,
the temperature,
time, container.
you don't have bubbles in the glass. I don't know.
Yeah, yeah.
I believe that more than the temperature actually was the purity of the components, because in fact, what was really different, the action of Galileo was taking care of the glass itself, in the sense that he asked people in Venice to produce the best possible glass, and then he selected the very best ones in them. And again, the point is that depending on the traces of other components, as also John said, you can get colors and you can more easily bubbles or so. So more than the temperature, I believe, is the composition, which makes the glass very good. And then, of course, the mechanical grinding, because the surface is the other very important aspect of a good lens.
Yeah. Or many of the famous English scientists were also at some point in their careers glassmakers. People like Faraday did a lot of work on trying to make good glass. It's so important to get it right. And a lot of things like removing bubbles does rely on chemistry, redox chemistry, which they wouldn't have understood, but it relies on having components which release oxygen as you heat the glass up to make bubbles grow, and so that they rise to the surface more easily. But then as you cool down, those redox reactions go in reverse and help to dissolve any remaining bubbles. They wouldn't have understood the chemistry, but they knew those minor elements had a significant effect.
Yes, as an interdisciplinary field, glass is, physics is involved. This is for Professor Brighini, just a comment. There is a phase transition in glass, of course. So can you comment about new development? Because glass transition is a transition which appear as a transition for complex system. Recently, Giorgio Parisi also try to make a theory about to transfer the theory of spin glasses in glasses. But it's very interesting from theoretical point of view because it's an open problem, can involve a topological defect, topological aspect, and I suppose I read that can be interesting also for other development in biology, in cancer dynamics, and so on. So far, just a short comment, just for the first speaker.
Finally.
Yes, I fully agree. It's a very complex matter. It's a very complex matter. And in fact, as I said, there has been a very long debate on how define the glass transition temperature and the definition itself of glass. Of course, I tried to give a very simplified description of it. And say it's something that in most cases is simplified just to have production of glass. But certainly from the physical point of view, I believe that glass still is open to many deeper investigations. And that's one of the good issues of glass, that despite being since thousands of years, still is a mysterious material.
Bene, molte grazie. Possiamo concludere qui questa prima fase della mattinata con un breve coffee break fino alle 10:50. La ripresa sarà alle 10:50 con la presidenza della professoressa Cifarelli, che condurrà la parte seconda della mattinata. Coffee break.
Okay, so we start now the second session, and it's my pleasure to introduce Teresa Medici from Direzione Generale Autonomia e Cultura Regione Lombardia, Milan, who will give us, as you can read from the first slide, an interesting seminar about the archaeological glass. I'm very grateful to Professor Parker and to Teresa Medici because they came from the United States, another event on glass, to Bologna without sleeping almost, to be here with us today. So thanks for this as well. Please, the floor is yours.
Sì, parlo da qui, va bene? Sì. Ah, ok. Funziona questo? Ah, come vuoi, preferisci che mi... infatti. So thank you for this kind word and presentation, but it is a pleasure, but also an honor to be here today to speak to you about glass in this wonderful place. So my talk is focused on the relationship between glass and archaeology. But first, let me give some insight about current archaeology. What we intend as archaeology today has nothing to do with discovering lost monuments or treasures or collecting rare and precious items. Nowadays, archaeology is the study of past societies through their material culture and relies on a contextual and scientific approach. What we immediately associate with the concept of material culture is the idea of material remains left behind by past societies and emerging from the ground, broken pots, discarded animal bones, ruins of ancient buildings, and so forth. However, the real source of information for archaeologists is not restricted to the material evidence buried in the ground, but it was so-called the archaeological record. According to a recent definition, the record is not just material things, but also abstract or intangible context. It is not just the old bones or broken shards, etc., but where they are found, associated with what else, and in what depositional metrics. The archaeological record is all things and contextual information about them. The notion of archaeological record is thus a key concept for a sound understanding of how archaeology works. The study of a single artifact can focus on its composition, shape, production techniques. But the potential information that we can retrieve from the study of the complete record is incomparably wider, because the significance of an artifact is enhanced by the comprehension of this context. One of the main ways archaeologists use to determine chronology and interpret the function of an object is grounded upon its provenance and its relationships with other items and features. It is an important difference when we compare finds coming from proper systematic archaeological excavations with the finds arriving to museums and collections from the antiquary market. The loss of context deprives artifacts of their meaning and can make it more difficult or even impossible to determine their function. Most of the times, they can't offer any other information than their existence. Speaking about glass, I would like to explore with you how archaeology contributes to a better understanding of the role of glass in past societies. It will surprise you to know how the archaeological record can be a chief source of evidence, not only about remote past, but also when reconstructed relatively recent past. I will give you an example. In the frame of the ALPES research program of the University of Trento, aiming at investigating the evidence of pastoralism along the northern slope of Val di Sole in Trento province in Italy, archaeological excavations were carried out in a complex structure composed of various enclosures and the remains of one hut, located at 2,257 meters above sea level. Few finds have been unearthed, mainly potsherds, along with metal objects, including a coin of the Republic of Venice, dated between the 15th and the 16th century. Among the finds, a small glass bead, this one, was also recovered. It is made up of light green glass with white applied stripes, and it is mounted on an iron thread. This type of bead is known as gooseberry bead from its aspect. Gooseberry beads are not particularly rare. Along with other types of beads, they were popular in the context of colonial expansion, thanks to their role of trading commodity in the unfair relationship among Europeans and native peoples. Similar specimens were found in Africa and in colonial settlements in North America. Nevertheless, this single bead, found in a pastoral site at 2,200 meters above sea level, may help us construct a rather different narrative. It is most probably a remain of a rosary, the string of beads that are used by Roman Catholics for counting prayers as they utter them. We know that from the end of the 16th century onward, the custom of carrying a rosary as a talisman was encouraged by Catholic Church. Rosary with gooseberry beads were collected from graves related to the early 17th century plague at Naturzo in the Bolzano province. Furthermore, it should be remembered that the costume of wearing the rosary in the Alps was common until the 1950s. It was hung on the bench where people slept and a sign of protection. And in many abandoned mountain huts, there are still rosaries affixed on the lintel of the entrance doors. Still, the gooseberry bead from Val di Sole is an indicator of the trading and use of this kind of items also in the Alpine uplands, a sort of unicum among the archaeological record of the Alpine mountain. A particularly fruitful situation to appropriately understand the context is represented by archaeological record deposited by people from the past with self-conscious purposes and in a short lapse of time, or even in a single event. In absence of significant post-depositional processes that can alter the record after its deposition, organic decomposition, disturbance by humans or animals, natural events, it means that what archaeologists find is the almost unmodified situation in which the objects spend the last hours of their life as a living object, still in use by the communities they belong to. Typical examples of this kind of context are graves. Many cultures keep the habit of burying objects along with the remains of the dead. There are usually personal possessions for accompanying the deceased journey into the afterlife or offering to the gods. Often, social status or gender played a role in what was left. Therefore, what archaeologists find in graves can be groups of glass objects that were in use at the time of the death of the buried person, together with other items, pottery vessels, personal tools and ornaments, weapons, giving a representation of the material culture related to that specific person and his or her time. A well-known example of this habit are the Egyptian pharaohs' graves. The paramount questions where, when, and where was glass first born can be answered only with the help of archaeological data, most of them collected from excavated graves. It is accepted by the scientific community that the first known glass vessels were produced during the Bronze Age, around the middle of the 16th century BC. But researchers are still debating over the two main possible places: ancient Mesopotamia, present-day Iraq and northern Syria, and Egypt. In this slide, there are some small late Bronze Age core-formed containers excavated from present-day Iraq this one, and from Tomb 8 at Thebe in Egypt. And you can see that the glass coming from Egypt is much better preserved, mainly because of the dry climate. Core-formed coal containers and small bottles retain original blue and yellow color. Most of the beautifully preserved Roman glass items that reached us were found in graves as well. We should recall that the most relevant innovation in glass manufacturing took place during Roman times. I refer to the discovery of glass blowing, discovered during the 1st century BC, somewhere along the East Mediterranean coast, in present-day Lebanon or Israel. The introduction of the technique of glass blowing made the production of objects much more easy, quick, and cheap than before. Consequently, large quantities of glassware became available across the Roman Empire. And for centuries, the Romans kept the habit of burning objects along with the remains of the dead, giving us an idea of the wide variety of items produced and used. Beautiful examples, as you can see in this slide, came from the necropolis of Altino near Venice. A vast assortment of integrally preserved objects dated between the end of the 3rd century BC and the mid-2nd century AD have arrived to us thanks to the fact that they were used as grave goods. Some types of containers are typically found in tombs, as for example, toilet bottle, used for pouring perfumed oils during the funerary ceremonies. This one. Others are objects of everyday use, accompanying the dead in the afterlife, as sets of table vessels, beakers, jugs and bottles, or personal adornment. When the ritual was by incineration, common storage jars were employed as urns for holding the ashes of the dead. But from monumental tombs in Pompeii, not only everyday objects were found, but also very rare specimens, as the blue vase at the National Archaeological Museum in Naples, with scenes of white cupids harvesting grapes dating from the first half of the 1st century AD, shortly before the eruption. It is one of the most important works of cameo glass to have survived, and it is an exceptional record of the artistic life and glassmaking art in the first Roman imperial age. Sometimes very tricky items are found. A recent archaeological discovery made in Japan is a good example of how proper comprehension of the context may help in decoding the meaning of the object. At the end of the 16th, beginning of the 17th century, a well-known type of enameled beaker was produced in Bohemia, often indicating an ear. Several examples are preserved in museums' collections, and they are considered one of the most typical Bohemian production of the Renaissance. What is not typical at all is to find one of these beakers in an 18th century tomb in Japan. In fact, a Bohemian blue beaker with an enameled scene of a bridal couple and with the inscription 1599 was excavated from the tomb of the feudal Lord Tadao Matsudaira, dead in 1736, located in the town of Kota, prefecture of Aichi. According to the author of the investigation, the item was brought to Japan as an import of the Japan-Netherlands trade. Between 1641 and 1843, during the country's 200-year period of isolation, the only official place of trade between Japan and the outside world was a small island in the port of Nagasaki, which served as a Dutch trading post. We know that Tadao Matsudaira was appointed to be Nagasaki Goyo, the director of the contact point to the overseas during the Edo period. To carry out the task, he traveled to the island several times during his tenure, and probably was given this beaker as a gift by the Dutch trading post chief. Even if we are not sure that the whole story of this beaker has been understood, there is no doubt that Tadao Matsudaira loved this glass, which was selected as one of the grave goods by his family, and put right next to the corpse as a wish that Tadao could use that in his afterlife. Another kind of close context are shipwrecks, their content being a synchronous record deposited by the people from the past with self-conscious purposes. Shipwrecks cargoes are powerful sources of information about glass of every chronology. Their study had a key role in the reconstruction of the glass production system in the past. Since the beginning of the production until the Middle Ages, glass melting, what we call primary production, as I told you before, was taking place in few specialized centers. Thanks to underwater archaeology, we know that raw glass became a traveling commodity very early in its history. The so-called Uluburun shipwreck of the Mediterranean coast of Turkey near Kash is a shipment dating to the late Bronze Age, around 1320 BC. The bulk cargo were copper and tin ingots, the components for producing bronze alloy. But the ship was also transporting luxury items as ivory containers or gold jewelry. Raw materials included deep blue and turquoise glass ingots of Egyptian origin, suggesting that Egypt was exporting to other regions via trading ships such as that. Along with raw glass, ships were loaded with broken glassware and glassmaking waste. The benefit of the introduction of cullet in glass batches was very well understood by glassmakers, and glass was habitually collected for recycling since the Roman times. We have many examples in the Mediterranean. The so-called Julia Felix is a Roman shipwreck discovered off the coast of Grado, in the northernmost section of the Adriatic Sea in Italy. The cargo was mainly composed by amphora, dating the wreck to the first half of the 3rd century AD. In addition, it contained a wooden barrel filled with more than 11,000 fragments of glass vessels for a total weight of 140 kilograms, collected and traded for recycling. The famous wreck of Serce Limani, Turkey, sank at the beginning of the 11th century AD. And the glass cullet consisted of 3 tons of raw glass and broken glassware. According to the excavators, they recovered millions of shards belonging to between 10 and 20,000 vessels, produced by a still unknown Islamic glass factory on the Syrian coast. But of course, glass was traded also as fine tableware. During the Renaissance, the fashionable and coveted Venetian glass was shipped all over Europe, crossing the Mediterranean and the Atlantic along Western trade routes in the direction of the coast of the Iberian Peninsula, Flanders, and England, and on the other side, toward Istanbul and the Eastern market. The accurate work conducted on a wreck sunk at the Gnalic along the Croatian coast led to the precise reconstruction of the full history of the ship. Underwater excavations revealed that the ship was carrying a cargo composed by a variety of goods: silk, pottery, raw materials, and as tin bars stamped with the San Marcus lion, the symbol of Serenissima, just to mention a few, including a quantity of glass vessel, and window panes. According to the archive documents, the Galliana Grossa, this was the name of the ship, set sail from Venice heading to Istanbul on its last journey at the end of October 1583, delivering an order of window panes to be used for restoration works at the Sultan's old palace. But already on November 9, the news of the sinking along the Dalmatian coast had reached Venice. Part of the cargo was recovered at the time, but some remained underwater for centuries, until the accidental discovery in 1967 and the investigation that followed. Apart from the window panes, the glass cargo offers a unique portrayal of the variety of the glass items shipped from Venice to the east during the second half of the 16th century. along with the most renowned and spread Venetian production, as for example, trade beads, goblets with a variety of stems, or diamond engraved bowls and vases. The ship was carrying some less common objects, like the sprinkler for scented water. Most of the cargo is made up by the perfectly clear glass characterizing the Venetian production, but a small group of colored glass was also recovered. Among them is worth noting a very rare fragment of opaque red glass with millefiori decoration, not yet documented among the Venetian glass. This one. In contrast with what I showed you until now, in most cases, the archaeological record is not the result of intentional deposition. Instead, it is the byproduct of actions, which means that it mainly reflects what ancient people lost, abandoned, or discarded. If the aim of archaeology is the study of past societies through their material culture, it becomes evident how challenging is the quest for reconstructing past human behaviors through this kind of material remains. The more vanishing the available record, the more relevant must be our capacity to fully understand the information embedded in it. That's why archaeology is an interdisciplinary science par excellence, using knowledge and techniques from many different academic disciplines. For example, iconography is a useful tool that can provide chronological and sociological information about the use of objects. For example, paintings like the Bacchus by Caravaggio or the Weddings at Cana by Veronese confirm the use of large stemmed cups for drinking red wine. A very curious case happened to me when I was preparing my dissertation about late medieval and early modern archaeological glass in Portugal. Examining a small collection of glass shards coming from excavations at the facilities of the Machado de Castro Museum in Coimbra, from a filling of garbage dump dated to the end of the 16th century, I soon realized that a group of blue fragments could belong to the same object. Linking the fragments, I was able to identify the complete profile of a partially preserved vessel whose shape was completely unknown to me. An amazing sort of bottle with a globular body and a cylindrical end with decoration of ribs, mold blown first and then tooled to reach the final shape. I found just few references in the literature. A similar fragment for another excavation in Spain interpreted as the perfume bottle, and a generic similarity with the typical Catalan bottle called almorracha, traditionally used to sprinkle rose water. But the Portuguese find was missing one important feature, the spout for sprinkling the perfume. It was with enormous surprise that I found a possible solution to this puzzling problem in the Cathedral of Seville in Spain, in which an altarpiece with the representation of the birth of the Virgin by Alejo Fernandez, dated at the beginning of the 16th century, is preserved. The painting depicts the birth of the Virgin as a domestic scene. Behind the parted red curtain of her bed, Mary's mother, Anna, rests after giving birth. Two women are supporting the new mother, one bringing a chicle, while the other offers her an object that is almost identical to our archaeological glass. You can see the chicle, the glass, this is the detail. The ethereal aspects, accentuated by the reflexes visible on the surface of the painted piece, indicates that the represented material is intended to be glass. According to the art historians, this kind of emphasis on the human aimed at making the Virgin and her family approachable to viewers by bringing the sacred event into the sphere of their own everyday experience. Therefore, the representation is referring to actions that commonly took place during postpartum care. And in fact, nowadays in Portugal, it is possible to collect relates about the tradition to feed the new mother with chicken stock and to give her special perfumed substances to sniff in order to increase breast milk production. And by the way, it's also surprising the discovery of an identical object in archaeological excavation in Buenos Aires, in Argentina, a city founded by Spaniards in 1558. It looks like this is an object with a special meaning for the Iberian material culture. Speaking about the interdisciplinarity of archaeology, we should also mention the role of chemical analysis. Based on the principle that the chemical composition of the glass reflects that of its raw materials, silica, fluxes, colorants, stabilizers, making possible to assess the sources and therefore the production places of the glass, research of the last few decades has greatly enhanced our understanding of the production and distribution of glass across time and space. We now recognize several major families of glass composition, as, for example, plant ash-based glass in late Bronze Age Egypt and Mesopotamia, in the Islamic world, mineral natron glass in the Greek, Roman, and Byzantine empires, and wood ash and soda ash lime glass in medieval Europe and Venice. Among others, the technology of Venetian glassmaking has been extensively investigated through analytical studies and from information supplied by Venetian glassmakers' treatises. The comparison of the compositions has been widely used to identify genuine Venetian glass, both in museums and in archaeological sites, for instance, with the aim to differentiate it from the so-called Façon de Venise glass, that is, glass produced in Venetian style outside Venice, mainly by expatriate Venetian glassmakers working in other European glassmaking centers. The analytical distinction between Venetian cristallo and other types of glass has been helpful for supporting the interpretation of another glass found in Portugal, among many others. Extensive archaeological excavations conducted at the site of the partly ruined monastery of Santa Clara Vella in Coimbra yielded important archaeological information and a vast variety of finds, including glass. The Port Clare Monastery was relocated to a new site in 1677, and the old building remained abandoned. Most of the excavated deposit is related to the last 50-75 years of the convent life, which means the end of the 16th and the first half of the 17th century. In this context, I was quite surprised to detect among the glass finds a small fragment of translucent blue glass decorated with figures painted in blue and white enamel. It is possible to distinguish two silhouettes dressed in long garments. The one on the left is the female figure turned to her left and attired in a high-waisted blue dress with white sleeves. Of the second figure on the right, only part of the white clothing and what appears to be the left hand here are visible. Despite the corrosion of the enamels, one can note the good quality of the drawing with very fine traces of contrasting colors to produce the pleated effect of the fabric. To a trained eye, the composition immediately evokes a famous group of rare enameled footed glasses, traditionally considered to have been produced in Venice at the end of the 15th century. All made of blue glass, they are decorated with processional scenes featuring groups of young men and women, horsemen, chariots, as well as allegorical figures. The depiction of this kind of parades, interpreted mainly as the triumph of chastity, is well known in Renaissance Italy, and its occurrence as a decorative theme is generally related to the wedding rituals and feasts. Therefore, these glasses are considered to be bridal objects which circulated among the wealthiest members of Italian society at that time. As you can imagine, The identification of a new specimen of this very restricted category of items was a relevant matter. In the hope of unveiling the provenance of this fragment, macroparticle-induced X-ray emission analysis was performed. The enamels display an advanced degree of corrosion, and the discussion concerning their composition is only tentative. Still, the composition of the body glass was identified as compatible with cristallo of genuine Venetian provenance. The study of the cobalt, detected as the blue chromophore, allowed us to identify a cobalt ore in use before 1520, 1530, which is in accordance with the date proposed for this group of glasses. So data were consistent with what is expected for a genuine Venetian object dated from the late 15th to the early 17th century. This is a remarkable fact because most of the finds unearthed from the monastery of Santa Clara Veglia dated to the end of the 16th century and the first half of the 17th century, so much later. The presence of a specimen of these rare Venetian glass objects in Coimbra could indicate that not only the royal house in Portugal, but also the wealthier classes of Portuguese societies, from which most of the Clarissa nuns living in Santa Clara Veglia came, had access to the most exquisite goods available on the European market. A wedding cap is only apparently in contradiction to the monastic life, because it is known that nuns from the highest levels of society tended to reproduce in their enclosure the ambience from which they arose. And by the way, it's also remarkable that among the most important and recent discoveries of glass dating to the late 15th and 17th century in Italy, there is a set of extraordinary enameled beakers and bowls also found in a poor clay nunnery, the former monastery of Santa Chiara in Cella Nuova, Padua. So, to resume, the knowledge of archaeological record and the interdisciplinary approach are key factors for the study of archaeological glass. And the comprehension of the context is of paramount importance for the correct interpretation of glass finds of every chronology. Also, small finds, adequately studied and interpreted, can shed light on the diffusion of this class of objects and can contribute with new and rather surprising data to the discussion. The International Year of Glass that we are celebrating has been a unique opportunity for people involved with glass on different fields to meet and to work together with the common goal to celebrate this unique material. And this will be the major legacy of this extraordinary year. Thank you for your attention.
Thank you. Thank you very much for this beautiful presentation. We have time for questions right now, 5 minutes. So who has the first question to ask to Professor Medici? Curiosities? No, maybe you want to wait at the end of the session. You have time to think about. Oh, there is one.
Thank you, Teresa. The curiosity concern our region. You explained that with the University of Trento, you was around Val di Sole and other places in Südtirol too, looking for different archaeological results, in particular glasses. The curiosity is, what is the oldest sample that you arrived to find in our region?
In Trentino?
Yeah.
There is quite a lot of Roman glass.
Roman
sure.
period.
There were lucky archaeologists in Trento to find a production workshop late Rome, I think dated 5th, 6th century AD. Okay. But if you look, for example, in the museum in Riva del Garda, there is a wonderful collection of Roman glass coming from the necropolis of of there, because there is I think that that part of Trentino reflects the influence of Veneto, because from the glass point of view, in northern Italy, Veneto, Brescia province and Piedmont are the most important place, and until the that part of Trentino province, Trento province, this good quality Roman glass still arrive maybe along the lake.
Okay, there is nothing coming from the north in the barbarian period.
Not yet, not too much so far from the archaeological record.
Okay.
No, I cannot say that there is some medieval glass, but very small shards, and so far I think that any so heavy.
Thank you so much.
Thank you.
I also have a curiosity. The beautiful Roman vase that is kept at the Archaeological Museum of Naples, the blue one with the figures. The blue is still made of cobalt?
I think so. I am not sure if they analyzed, but that particular shade of blue, it's obtained by cobalt. Then you have another, you can have blue also with copper, but the shade is more turquoise, or also with iron. You could have this kind of light turquoise. But when you have this deep blue, usually is cobalt. I'm not sure if they analyze, but from the shade, it's probably. Then it's interesting with cobalt that you can understand where they were collect cobalt during the time. There is a lot of studies. They started with porcelain, because it's the same. The cobalt is used also for coloring ceramics, and you need very few quantity of cobalt to obtain the blue.
No more questions? No? If not, we thank Teresa again. Thank you very, very much. And now it's my pleasure to introduce the next speaker, who is Professor Rosa Barovier Mentasti from the Istituto Veneto delle Scienze Lettere e Arti in Venice. And please, we will hear about another very interesting topic about glass and alchemy. Thank you very much.
Good morning. So I begin with the first slide. Okay. This is a painting by Mantegna about the middle of the 15th century. And I think that this lamp, oil lamp, can be considered a symbol of the first crystal glass vessels made in Murano for the first time just before the middle of the 15th century. Maria Teresa Medici talked about the revolution that occurred just before the middle of the 1st century before Christ, when blowing was invented. This invention changed completely the history of glass, because for the first time it was possible to make functional glass, cheap glass, very easy to shape and easy also to make in a very short time, because just a beaker or a flask can be done by blowing in less than 1 hour. So people in the Roman Empire belonging to not only to the upper classes but also to the middle classes could buy and use glass. You can find pieces of glass in the tombs of not only of very rich people, like in the period of pharaohs, but also very simple tombs also in Veneto, in Aquileia, in Altino, and so on, and all over Italy, and in the other regions of the Roman Empire. In Murano occurred in the middle of the 15th century a revolution that was the opposite of the one that occurred in Roman times. Actually, after the fall of the Roman Empire, in Europe stopped the production of luxury glass. So people demanding very beautiful pieces of glass had to purchase glass coming from the Levant. So, for instance, noble personalities or also institutions like the treasures of churches bought pieces coming from Syria or Egypt. You can think about the treasure of San Marco, for instance, but also in France, in other countries of Europe. At a certain point, in Murano, occurred a new revolution that was, as I said, the opposite of the revolution that happened in Roman times. Glass blowers began again to produce luxury glass in Europe. Who was the man who started this new era for European glass? Many scholars agree that his name was Angelo Barovière. The main scholar who wrote a lot about him and wrote the most important articles after collected in 3 books, was Luigi Zacchini. Actually, Luigi Zacchini was not an archaeologist or an historian of art. He was a teacher of it is actuarial mathematics in the University of Venice. He was an engineer. He was a teacher of glass technology in Murano, and his hobby was going to the archives of Venice, finding medieval and Renaissance papers, documents, and explaining them. So his work has been the base for the new history of Venetian glass. But you have to tell that the history of Venetian glass has not yet been written, because there are so many problems for the scholars in explaining the development of Venetian glass and in the attribution of the pieces kept in the museums, that I think we need a lot of time to continue the work of Luigi Zacchini. Luigi Zacchini based his scripts on documents, but other are the tools we can use to write the history of Venetian glass, that are paintings. Paintings help a lot to date still existing pieces in the museums. You can now we have the possibility to analyze the pieces in the museum and the fragments found in excavations, even if not always it is possible to make a good analysis of pieces because of the bad conditions of the pieces that are excavated, and the study of the recipe books of the old Venetian glassblowers. I go back to Angelo Barovière, who was this man. And Luigi Zecchini attributed to him the invention of crystal glass. That was the starting point to begin a new story of European glass, the story of luxury glass in Europe, again after the fall of the Roman Empire. Angelo Barovière belonged to a family that was making glass since the first half of the 14th century. He was belonged to a glass family, and he himself was a glass blower, a technician, and the owner of a small glassworks. You have to remember that big glassworks are not always the best ones. Generally, in Murano, the small glassworks are the ones who make the most refined pieces. But he was not only a blower with the empirical knowledge of glassblowers of his time, but he also attended some high-level courses in Venice of a famous philosopher. The name philosopher is a generical name for a man who liked the science and natural philosophy and alchemy and theology and so on. He was the director and teacher in the Scuola di Rialto. That was a school in the beginning organized by a Tuscan man, naturalized Venetian, who gave 50 ducats every year to run the school. After it became a public school. We know that from the papers that Angelo Barovière attended the lessons of such a philosopher, and also the people of his time concluded that these lessons were useful to him to develop in a new way the technology of glass. No. This is another example of crystal glass, Filippo Lippi. He's a Tuscan, but you have to remember that for the 15th and 16th century, Tuscan rich men, noble families, bought not Tuscan glass for everyday use, but for their houses, they preferred Venetian glass. We have the inventories, also some papers which testify the purchase of glass in Murano and so on. And so very frequently in the paintings of 15th and 16th century of Tuscan painters, glass is not Tuscan but Venetian. The first document that speaks, mentions crystal glass made probably by Angelo Barovière, most probably by Angelo Barovière, is the journal of Giannozzo Manetti. The journal indeed was written by his secretary. And when he came to Venice for an embassy, and he visited the city. And in a certain day, in September 1448, he went to Murano to visit the master of crystal glass. That is most probably, the only one that in that time produced crystal glass. Giannozzo Manetti was a very important man. He was a diplomat, but also an humanist, well-known humanist. But in this case, we are interested in him only because he visited Angelo Barovière, and he mentioned the crystal for the first time, as far as we know today, for the first time, crystal glass. Antonio Verlino, the famous sculptor and architect that worked for the Sforzas, met Angelo Barovière, probably in Venice when Filarete came to Venice, or also at the court of the Sforzas, because in 1555, Angelo Barovière was invited as a guest at the court of the Sforzas. And when he describes the ideal city, Sforzinda, which he would like to build, and when he speaks about the pieces of glass, windows and floors in mosaics and other works in glass, he mentions Angelo Barovière. My very close friend, who is called Mastrangelo da Murano, the one who makes crystal glass. Indeed, to Milan when Angelo went with his son Marino. Marino was fascinated by the court of the Sforzas, and he did not want to come back to Venice. So a monk, a famous, important monk from Venice, wrote to the Duke of Milan so that he pushed away the prodigal son to Venice again, and Marino came back. And also Marino is mentioned in the Trattato di Architettura of Filarete. Most significant among the papers who mention Angelo Barovière, the Venetian papers, is this one. When Angelo has just died, his son is mentioned as the son of the Angelo who made alchemical crystal vessels. So alchemy is strictly linked with the invention of crystal glass, because Angelo, who was well cultured. For instance, we know that at a certain point he rent a book from a nobleman in Latin, so he was able to write and to read Italian and Latin, and he began to make, thanks to the lessons of Paolo da Pergola, that famous scholar that ran the school of San Giovanni Elemosinario. What is the Scuola di San Giovanni Elemosinario? In Venice, in 1408, this Tuscan man gave the money to open a school of high level in Venice. The seat of the school was a church near the Rialto Market, a church still existing, not in the shape of the time of Angelo Barovière, because the church burnt in the early 16th century, and it was immediately rebuilt. So the style of the previous church was Gothic. The one of today, still existing, is in Renaissance style. No, questo dopo. This is the church. You can't find it if you go to the Rialto market because there are only 2 doors, but the church is completely covered with simple houses. So you have really to investigate how to find the church, and that is the door, but inside the church is very nice. The tower of the church is still medieval. I go back and I tell another thing. What was the new idea of Angelo Barovière? In Murano, already in the 14th century, blowers made a very a glass of a very high quality. They made common glass that was a little green or yellow because of the iron in the sands, in the soda sources, silica sources in the sands. But they made also the so-called, in the papers of the period, vitrum blancum. So a glass that was colorless and pure enough because they used already in the 14th century, they used a perfect silica source that was that were the pebbles of the Ticino River, which were ground before roasted, then poured in the water, and then thanks to the shock, thermic shock, ground. These pebbles are almost 99% quartz, so a very good silica source. Then they used soda ashes coming from the Levant, the best from Syria, and they used the manganese as a decolorizer, so they could make a very good colorless glass and pure enough. For instance, some not very honest merchant sold glass, Murano glass, as if it was rock crystal. So we have some laws against this not honest market. So it is the proof that it was a very good clear glass. But Angelo wanted a better kind of glass. So he applied to the soda ashes purification. The purification of the soda ashes or potash ashes already existed, and it was applied, for instance, to enamels. For instance, we have here this wonderful altar of the Museum of Santa Maria del Fiore in Florence. There are some enamels applied to the silver that are basse taille or champlevé, and they have been analyzed, and the ashes, the flukes, which are the flukes, have been purified. So the use of purification of ashes with chemical methods already existed. The ashes were poured in boiling water, then filtered, then dried, and they obtained a salt that was white, pure, the best to make glass. So Angelo used this already existing method. But what is the novelty? It is the fact that in that time, until probably the 18th century or the end of 17th century, nobody knew the use of a stabilizer in making glass. They stabilized glass because of the impurities of other components of the glass, of other raw materials. But it was not a conscious use of a stabilizer like calcium, magnesium, and so on. So when the enamelers melted, used, probably made in other places, enamels, the enamels were made with purified flux, but the stabilizer was unconsciously used thanks to the colorants. So the enamels were not affected by the weathering, as if there was not a stabilizer. The problem is that Angelo Barovier wanted to make colorless glass. So without colorants, how to stabilize these products? We imagine that probably in the beginning, the result was not good because he absolutely applied the purification of the ashes, and the glass which he obtained was not a good, well-lasting glass. So, and if you read the recipe books of the Renaissance period, there is nothing about this problem. So there was probably Angelo introduced an operation that is not mentioned in the recipes. That was the real secret. So he used to introduce in the batch also a small part of vitrum blancum frit, or pieces of vitrum blancum, fragments of vitrum blancum, to introduce in the batch some stabilizer. That is the new thing, and it is sure that it happened because the analysis of the pieces of the late 15th century and of the 16th century show that there is a small quantity of stabilizer, the same as in less quantity, the same that you can find in the vitrum blancum, that is the intermediate glass in between common glass and crystal glass. So the invention of crystal glass changed the market of glass in Europe, because very quickly all rich people wanted to get Venetian crystal glass. And so the blowers could get a lot of money and could dedicate to new developments of new colors. Also, they could improve their skill in shaping glass. So a new trend started in the history of European glass. In later century. Also, Bohemia applied new methods, some coming from Venice to their typical kind of glass, and also England and so on. This was only the beginning, but for 2 centuries, Murano was the main center for where to get luxury glass. These are enamels of the altar that are made with purified ashes, but they are earlier than the invention of crystal glass. But here there was not the problem of stabilizing the resulting glass. So this is the period when all painters, the most of the painters began to like to paint crystal glass vessels in their paintings. Also Tuscans, because in Tuscany was one of the main markets for Venetian glass. Just an anecdote, I have found not an unpublished paper in the archives of Florence, and they are 2 letters written by Marino Barbier, the son of Angelo, who has gone to Pisa with a charge of merchandises, most probably glass, because he was a producer of glass, and he writes to Lorenzo il Magnifico to be helped in his problems with the officials of the port of Pisa. So you already knew, had contacts with Lorenzo il Magnifico, the Magnificent, and he was trading glass in Pisa and Florence. I think that he was not, he was asking the help of Lorenzo, not because Lorenzo was a private buyer of his pieces, but because, and that is another interesting thing, Florentine and Tuscan banks invested in Venetian crystal glass their money, because we have the Strozzis also, for instance, at the trade of Venetian crystal glass. This is Ghirlandaio. We are in the year 1480. You can see typical crystal glasses. In particular, you can see on the left a salt cellar with 3 feet that are small crystal balls, a kind of salt cellar that is quoted both in Venetian documents and in Florentine documents. Saliere con palluzze. This is a painting, for instance, by Agostino da Lodi, a painter that worked between Lombardy and Venice. This looks like a still life, ante litteram. This is a wonderful Last Supper in Badia Polesine by Girolamo di Santa Croce, who was a Veneto painter. And this is our loved Carpaccio. This is a lamp painted in 1510, and this is a wonderful lamp with some ribs in the lower part that also make the lamp more heavy in the lower part, so that it becomes more stable. This particular lamp is also can be found in the Museo in the Glass Museum of Murano, with the coat of arms of the Tiepolo family of Venice, and we can date this lamp to the same period. A curious thing, this Cesendello, the name is Cesendello of this kind of lamp, which was filled with water, oil, and non mi ricordo più come si dice stoppino. Thick, so this strange piece is kept in the Musée de la Renaissance at Écouen, near Paris. This is an example of the difficulties of the historian of glass, because this is what a friend of mine, Susan Egot of the Wallace Collection in London, called an hybrid, because some year, we don't know when, probably in the 19th century, it was the Cesendello was restored, applying to it the foot of a goblet. So it is a mixed piece. The higher part is a Cesendello. The lower part is an incongruent foot of a goblet, and you can't imagine how many of such hybrid are kept in international museums, the British, in the Louvre, in Verona, in Del Bargello, in Florence, and so on. It was a typical trend of that period. I think the merchant, the antique dealers were responsible of such thing. But before Susan Egot began to write about this strange thing, nobody now we look with other different eyes at the whole piece that look a little strange. And this is another curious thing to explain how complex is the production of glass. This piece is kept in Istanbul because the sultans, Ottoman sultans, liked a lot Venetian glass. So when a new ambassador called Bailo, a resident ambassador, Venetian resident ambassador in Istanbul, arrived, he was obliged to bring hundreds or thousands of pieces of glass for the Sultan and for his families and for the dignitaries, so that he was obliged. It was a present, but not a free present. And this is kept in a new museum opened in Istanbul dedicated to glass. A lot of the pieces of glass kept in this museum are the rest of what the ambassadors of Venice brought until the end of the Republic to Istanbul. Other examples of crystal glasses that this is a bowl you see in the lower part of the paintings, ribbed bowl with some decoration along the border, and such bowl was much in fashion, so that you can find similar bowls everywhere, also in excavation in France and in England. But you have to remember that besides the Florentine people, the Bavarian people was the most wanting clients of Venetian glassworks. This is a painting by Benvenuto Tisi called De Garofalo from Ferrara. This is a delicious beaker with enamel decoration in the early 16th century, and you can find in museums similar goblets. I wanted to show how useful are the paintings to date the pieces, still existing pieces. And just to explain how important was Venetian glass for sovereigns, for noblemen, this is a wonderful standing bowl, big one, kept in the Musée de la Renaissance, with the coat of arms of Anne de Bretagne, Anne of Brittany, and she was the wife of two kings of France, and the piece is dated 1499, 1514. There is a series of such important standing bowls in different museums, also in the Metropolitan Museum, and so in the Petit Palais à Paris, and so on. And this is a shape that is copied from metal works. You can find in paintings also in Northern Europe paintings, similar pieces in gilt silver. Another idea of what, and I am finished, of what made the Venetian blowers. This is the so-called acanino, a name which comes from the Islamic Arab language. In Tuscany, it was called oricano, and maybe you remember Boccaccio, that used such a term. It was a typical sprinkler for rose water, and it was exported to the Eastern countries because at the beginning of 15th century, the luxury glass production in Eastern countries stopped. So they bought Venetian glass. It was exported in Northern Europe. This is with the coat of arms of two Nuremberg families for a marriage, a wedding. And we found a lot of the necks that are the less fragile parts of the bottle in the Lagoon of Venice. Excavations in Venice, but also scattered pieces in the Lagoon of Venice. And another shape that is very old, it goes back to medieval period and late Roman period, pilgrim flasks that were really pilgrim flasks when they were made of metal, but this is not, because you can't travel with such a piece. It was much in fashion as we are in Bologna. I show these bottles which before belonged to the collections of the University of Bologna, with the coat of arms of Bentivoglio and Sforza. And in an article with two friends, we wrote that it is not possible. They are flasks of the first wedding of Bentivoglio with Sforza, but of the second wedding, Alessandro Bentivoglio and Ippolita Sforza. So the date is 1492, a precise date, but also a piece with the Medici coat of arms, a pope. So we have the alternative of two popes, but we are in the first half of the 16th century. And as you are in Bologna, the oldest piece made, the oldest enameled piece of the Renaissance period we know. That is this incredible goblet in the Museum of Bologna, in the Museo Storico Medievale, with a religious subject that is linked to the Biblia Pauperum. So Biblia Pauperum used to link events of the New Testament with events of the Old Testament. So there are two prophets and two events of the Gospel. This is probably not of crystal glass. It is vitrum blancum in blue color, but analysis have found that, for instance, this piece a little later than the former one, we are towards the end of the 15th century, is blue, but the base glass is crystal glass. The first time I saw it directly, I thought it was not old because it was too brilliant, but that was the crystal glass. So I have finished, and it is just, I finished with two other pieces. To Angelo Baroviere, Luigi the King attributed also the invention of the Latimo glass, not fit for blowing, with the viscosity of fit for blowing. And this is a masterpiece in the Kunsthistorisches Museum in Vienna. The twin bowl is kept in America in the Corning Museum of Glass. This is the lady, and the youth is in the painting on the other bowl. And this is Carpaccio style in the painting. So they are dated in the early years of the 16th century, and another invention of the same period, Chalcedony glass, that is also quoted by Averlino, il filarete. And for instance, this is in the British Museum, and you can see this painting by Ghirlandaio of the 80s of the 15th century with the same ribbed vase. Thank you very much.
I could have remained another hour to watch these beautiful artifacts. How beautiful. I have just one question for you. Can I ask a question? Just one, because we are a little late, maybe at the end if we have time. The hybrids, the lamps with the foot. This was only done with the lamps which had no.
You can find also some vases with pieces, with foot that fit, which are not incongruent. They are of the same period, but the proportion doesn't work. So if you look at very closely the foot, you can see there is a junction.
So it was done because glass is fragile.
Incredible. So yes.
Thank you.
But I don't know if also in old times they did the same thing. That is a mystery.
Because
probably
it's fragile. So to put together broken pieces, maybe.
Thank you.
Thank you. Thank you very much again. There was one question. I would like to give the floor to the next speaker, and then at the end, before lunch, we stop a little more and ask the last questions. So please, the next speaker, Rinaldo Fsaro from Istituto di Scienze e Tecnologie Chimiche Giulio Natta of Italian CNR Milan, History of Silica Glass, Chemical and Technological Aspects. So now it's going to be hard again.
Well point. Good morning, ladies and gentlemen. I want to thank Società Italiana di Fisica e l'Accademia delle Scienze for this kind of invitation. The talk, the title of my talk is History of Silica Glass, Chemical and Technological Aspect. Apparently is too much. I try to condense some aspects. Glass is in antiquity a very important material. We heard a lot. It's possible to compare to our modern plastic era. That one is a famous television advertisement concerning the Moplan. Moplan is a very famous plastic, is really is isotactic polypropylene, and Giulio Natta get the Nobel Prize for that. So the glass, we heard a lot this morning from Regini, Professor Parker, and more or less, is in a versatile materials for a wide range of application. Is characterized as a liquid. This picture has been shown in the first presentation by Regini. So is described as real supercooled liquid or amorphous solid at the room temperature. Is a solid, but due its highly dissolved nature, has a property much like a liquid, is too viscous to flow at room temperature. There is a myth that the glass is really highly viscous liquid, thus observable flow can be detected in ancient object. And they believe this observation, in particular in the stained glass window of the 12th century. However, theoretical calculation, however, they verify the composition use either medieval and container window cannot flow at room temperature within the human time scale. And the physical measurements ensure that unless a sufficient compressive state is applied, gas do not flow below 400 degrees. So, which is the reason? Is a result of the limited technique at the medieval used in the manufacture, because the variable thickness and the thicker edge will be mounted in the same direction, with the thicker edge locally mounted at the bottom. Well, glass state, we said that occur when a liquid undergoes cooling increase, its viscosity is to such extent it will formally remain a liquid. Apparently is a physical properties of homogeneous and compound solids. So glass is an amorphous substance, a rigid material consisting of structural unit not organized in a geometric order typical of the crystalline state. We do not speak of a melting point or solidification temperature, but of a temperature range, the transformation range at which solidification occurs. And when the melt solidify called the glass transition temperature, depends, of course, on the chemical composition of the glass and the cooling rate. The composition on the most traditional glass is comprised primarily of silica, silicon dioxide, with an empirical formula CO2. And the most common form of natural silica is quartz, a crystalline solid, and the sand beach is a polycrystalline form. regardless the structural order, the unit is the CO4 tetrahedra, the silicon atom in the center of the tetrahedra. And of course, due to the bridging oxygen, we create a macromolecular structure. There, for example, is a threefold helix made of CO2-4 group. I can give you a two-dimensional structure. So at beginning, we have our unit, and then start real macromolecular or like a polymerization. And you can see this is a polymer structure, a crystalline structure. You can see the order. And this, in the case of glass, was the amorphous structure where we have a complete disorder state. The fusion of silica, of sand, need a very high temperature, 170 degrees. So it's not possible at that period to achieve this particular high temperature. And this limit was overcome when ancient craftsmen discovered that the fusion of silica could be accomplished by significantly lower temperature by use of fluxus in Latin. And in general, the most common flux was soda, the sodium carbonate, and it could you reduce the melting point for silica to below 1000 degrees. The soda is called natrium, as a mixture of sodium carbonate decahydrate and about 17% of sodium bicarbonate, along with small quantities of sodium chloride and sodium sulfate. The soda decomposes during the temperature into carbon dioxide, transform in sodium oxide. The sodium oxide react as a real solid state reaction, transforming the quartz into sodium silicate that melt at a lower temperature. Similarly, the potash we have. So you can see there is no order in the arrangement of atom, and this is a typical feature of amorphous material. So we have an amorphous silicate. This is more evident, this structure. These are the silicon atoms, the sodium, and the different oxygen bridging and oxygen non-bridging. When you use the soda, the sodium containing in the resulting glass is hydrosoluble and thus susceptible to attack of water. So the result is a glass of very low chemical stability. But the craftsmen discovered that there are some elements that we call stabilizer that stabilize this situation. And mainly are calcium and magnesium. Probably as a result, the result by impurities either in the silica, the sand beach, or soda sources. So, which is the real receipt? By combining the soda, calcium, salt, and the fusion temperature can be reduced really 1700 degrees. This triple eutectic mixture, the composition is the same, is the follow: 73.5 silica, 21.3 sodium oxide, and 5% of calcium oxide. And this type of glass are referred to soda lime glass, and most early glasses in the Western world consist of this type of materials. Of course, the composition is more complex because it depends by the area, it depends by the sand, it depends the composition, the flux. To further complicate the things, the character of the glass depends not only on its chemical composition, but also in the manner and degree of heating, but very important, as well as the rate of cooling the glass, the so-called annealing glass. We heard that the flux in Roma Vera was natron, and is coming from Lake of Egypt and the Middle East. This was discovered in Pompeii as a block used by glassmaker of Pompeii for the Myla procedure. An analysis of the chemical composition confirmed that they contain raw materials from the Middle East. And this shows that the glass was produced in a well-known Mediterranean sites as Sindon, Alexandria, and Egypt, Israel, and then exported for the second step. We heard before, in the Middle Age, natron was repaid by plant ash. And depending on the geographical location, the plant were burned, it could be marine or terrestrial origin. In the Mediterranean was obtained soda from the ash of a continental plant, mainly using potash was obtained. But we heard that potash and soda are the same properties. Of course, the craftsmen are not able to carry some chemical analysis, and judged by the quality of the ashes, smell, and with the help of the taste. Many years ago, I remember our professor Lamberto Malatesta that showed us some salt in laboratory using the test and the smell. Okay, I'm close. Today is not impossible. When one wants to produce, we heard, colorless glass, it was necessary to extract sodium carbonate from the ash by leaching. This is the process developed by Venetian. That means dissolving the ash in boiling water and filtering out the insoluble residue. And after leaching, about 40% of alkaline salt, carbonate, sulfate, and chloride could be obtained from the best ashes. And this was the main secret, the Venetian glassmaker, that the invention of the crystal glass to be so clear and colorless as to be compared to the crystal rock, to rock crystal. This is a beautiful painted in Pompeii, where showing the revolutionary technique of the glass blowing, also attested by Pliny the Elder or Plinio il Vecchio. So really the glass blowing, really a revolutionary technique in advance in the production of glass making for external diversification. There are some features. So a revolution in custom, particularly during the period of peace of Ottaviano Augusto, it created a real industry, probably the first real industry in the world. And of course, domestic terracotta and metal vessels were progressively flanked and replaced by glass vessels, which were recognized for having a special and were value characteristic for preserving food, cosmetic, and the medical field for pharmaceutical substances, because it's possible to follow the progressive degeneration of material inside the glass. Architecture revolution. The existence of window pane in Rome was a subject for many speculation, considering a phenomenon. But the first visitor in Ercolano and Pompeii were amazed at the amount of glass still placed in the window frame of house and public building. And Seneca considered the application of glass a recent invention. In addition, of glass, when also used the mirror stone, the mica, used for cut into thin, transparent sheet that are used to sell window or greenhouse to plant and flower. This is the depiction of medieval glass, but this is a window light green glass, and this is obsidian mirror. You heard before about obsidian, this is a natural. I carry with me a piece of obsidian just to, this is a very block of obsidian. And natural glass. Before glass manufacture, we have obsidian, volcanic glass, as well as impact glasses. We heard before Professor Regini, impactite or tektite. Obsidian, we have in particularly in Italy, in Aeolia Island, Pontin Island, Pantelleria, in Sardinia, and very large abundance of obsidian, and to make sharp and resistant. This material was traded over long distance. Probably this is the first Mediterranean trade route in the history. Obsidian is the greatest value from the fact that the conchoidal fracture of obsidian allow for its easy transformation into jobs with very sharp edges. This is from Syria. And this was an obsidian-based knife. It did not consist of single large blade, but utilized a length of wood stood with sharp obsidian teeth. And the manufacture of these tools long predated the development of metal tools, and thus played a significant role in development of early civilization. Obsidian, you look there, is a volcanic glass, is of course, again, like a glass due to the rapid cooling lava. Inside volcano, temperature, pressure are high, that silicate melt, giving rise to lava. On contact we are of the margin of flow, it cools very quickly, giving rise to obsidian. But again, the unit is the CO4 tetrahedra. A pumice, these little pieces of pumice, is amorphous again, composed of tegel-air-filled vesicular cavities. Again, is effusive magmatic rock, is very light due to the very high porosity. This is pumice is a nanoporous material. It is mainly formed by explosive eruption, and the porosity is due to the formation of gas bubbles. Rapid cooling look, the vesicular structure remain, and the solid part is 90% of volume is really a void. The chemistry of color glass. Small amount of transition metal species, 1 to 3% weight, were often added as colorant. Early glass in antiquity was really color. It's very difficult to have a colorless glass due to the impurity either in the silica sand beach or alkali sources. All sand contain an amount of iron in the 2 oxide, iron 2, iron 3. The iron 2 species is a problematic, very strong coloring to give a blue-green color to the glass. The iron 3 oxide give a yellow color, while a mixture of the 2 oxide can result in color from amber to green. Initially, the impurity might have been initially unintentional, but the glassmaker developed the ability to generate a variety of colored glass through the proper choice of transition metal additive, and the range of color for both opaque and translucent glass has increased rapidly. The blue color glass produced using copper and or cobalt color. Copper is generally considered the early colorant along with iron. It was the most common coloring species, giving glass that can vary from translucent, pale blue to dark blue. The analysis has shown a range with the average of copper oxide of 1%. Cobalt was common in production of deep blue, violet, and indigo glasses. In Egyptian deep blue glasses fall in the range from 0.75 to 0.55% of cobalt oxide. The addition of antimony would render the glass opaque and would usually give the final glass a turquoise color, although glasses could also vary from opaque, mid to dark blue. Other opaque glasses via antimony, including white from calcium antimonate and yellow from lead antimonate. In the case of white glasses, the lack of transparency is due to small particles of calcium antimonate which scatter the light, resulting in a milk or opaque appearance. As these glasses do not contain higher calcium content, it's believed that the antimony alone is added to create the white glass, with a hypothesis, with the line content of the glass contributing to the formation of the calcium antimonate particle. These are some examples. This marvelous Roman aubergine glass aerobilio used to carry oil to public baths. These are the columbines on the glass bathware, Museum of Antiquity of Torino and the Leone Vercelli. This is the intact only one with some probably water and the deposit. We have tried to study, but we have not success in determining really the content because we cannot destroy the columbine. These are the typical chemical elements that are used to color glass also today. We have a lot of elements. And it's not clear, particularly in the past, when the color was mixed with the initial raw material or added to the frit during the second stage, or it's even proposed that it might have been a first stage where the color was finally added. Of course, it's possible that the coloring process was done different at different workshop, at different country. Anyway, at the transition metal species would generate metal oxide, providing the strong coloring of the resulting glass. The final color will depend not only on the resulting metal oxide, but also the amount of the mixture, the ZAP process used for glass production, particularly the flux used, and the manner of heating. This is the famous Lycurgus cup. The Lycurgus cup really represented the outstanding achievement of the ancient glass industry. It is extraordinary in several respects, first in the method of fabrication, and in terms of unusual optical effects displayed by the glass. It's one of the glass known as cage cup or diatreta, where the decoration is open work. There are among the most technical sophisticated glass object producers before the modern era. There are not many examples, probably are 50 to 100 examples in the world. The glass of cup is a dichroic. In direct light, it's possible to see in the British Museum in London. And when I visit, the people are not really interested. But when I push the button and they change the color in red, the people are asking me what happened. Because when the light shine from inside, so transmitting light, it turned to a translucent ruby color, so dichroic. The cup was, some history, was acquired by the British Museum from Lord Rothschild in 1958. The Licurgo cup is first mentioned in 1845 and then acquired by the Rothschild family. No investigation till 1950 when Rothschild asked a request to understand. And there is this paper by Arden and Tony B. resulting in the definitive article in Archaeologia in 1959. Initially, there was a debate over whether the cup was it glass. It seemed impossible with the technical of INFN glass work in the time to produce such unusual optical effect. Dr. Clarenbourg, a mineralogist, concluded that it was made of glass rather than opal or jade. The result was later confirmed in 1959 by X-ray diffraction. This is important. In 1950, the base, which had itself been added sometime with early modern period to cover a repair, was removed, and some loose glass fragments from the original were found. This is very important because we have some species to characterize and analyze. And the British Museum sent a sample in 1959 to the General Electric Company for more detailed microanalysis, try to determine the colorant. Cooper noted the presence of trace quantities of gold, silver, and other elements responsible for the complex color and the scattering effect of the glass, so that the color may arise from a combination of physical, optical, because we are here speaking not a chemical aspect, but a physical, optical, coloration of colloidal metal in the glass. Chemical analysis showed that the glass to be soda lime, silica type, similar to most other Roman glasses, contain in addition about 0.5 of manganese. In addition, a number of trace elements, including silver, gold. It was further suggested that the unique optical characteristic of the glass might be connected with the presence in glass of colloidal gold. In 1962, a sample was sent to Dr. Brill of the Corning Museum glass, along with the sample of the diatratum. And it was confirmed that the dichroism was linked to the presence of minute amount of gold, about 40 ppm, and the silver, about 300 ppm in the glass. However, simply adding traces of gold and silver to glass would not produce these unique optical properties. So color system gave rise to the light scattering phenomena. And it was suggested that both gold and silver contributed to the color, and the gold component being made responsible for the reddish transition and the silver for the greenish reflection. These are hypotheses. Using the available technical, it's not possible to demonstrate this hypothesis and the relative contribution on the silver and cobalt. Therefore, the late 1980, a further small fragments of the cup was subjected to examination by Barber and Friston. And the transmission electron microscopy revealed a presence of nanoparticles, typically of in the range from 50, 100 nanometer in diameter. And X-ray analysis of this particle are silver gold alloy. So silver gold alloy. In 2000, Wagner and co-work indicated that the gold dissolved in the glass into the monolayer form as gold 1. So the reduction of previously dissolved silver and gold during the treatment will cause the fine dispersion of silver gold nanoparticle responsible for the color. Antimony has been involved in the redox reaction. that reduce the metal which is present in the glass of around 0.3, because we need to reduce the metal, silver and gold. So we can say that the Licurgo cups is really a nanotechnological antelitteram application. Of course, we don't know the nanotechnology, but it was really in the world of nanotechnology. And this is some steam image of these are silver gold alloy, and this the high resolution 10 microscope image showing single and also polycrystalline. Now this is our really crystalline image. So the production anyway of this glass is very difficult, and is mentioned medieval Islamic writing, but examples of the glass in the medieval just be confirmed. Several the red stained glass of medieval church is sometimes suggested to be gold ruby. The analysis confirmed that the colorant has been found to be copper in all cases. So the production of gold ruby, like a routine basis, does not appear to have taken place until the 17th century in Europe, and this cover often the credit to Johann Kunkel, a German glassmaker, chemistry. In 1685, another German glassmaker, Andreas Cassius, published in a book, De Auro, in which it described the method of producing the red-colored solution of gold that came to be known as the purple of Cassius. Cassius first reported in 1966, and in Kunkel in 1679, in Potsdam created the piece of ruby glass, and this the paper and the book of Kunkel. This is the marvelous example of ruby gold glass, ancient and modern. This is from my house. Is a cup, probably on the 20 period, and the color is really marvelous. Unfortunately, one is broken. But so this is an example of preparation of nanoparticle. These are nanoparticles of gold from synthesis via polyol, and these are stable solution of colloidal magenta is a gold, and yellow in water. We know now this different optical property in the case of gold, that the color is strictly dependent on the dimension of the nanoparticle. You can say we can a very large is like a different color. This is an example of a practical application of nanoscience, because you know that the gold bulk is yellow. Stop. But if you go down to the nanometer scale, we have a different property. So for this reason, we know for different application that gold that is inert, it could be, for example, a good catalyst when we go down for this dimension. I've carried with me two solutions of gold, colloidal gold. This is, for example, the color. These are stabilized colloidal gold. So the gold is zero from this is another example of color. And again, I can transfer the colloidal gold on the silica surface, and I have very different color that move Now I left here just to. No, ce n'è ancora uno. Qua. And of course, the color is strictly depend on the dimension of the nanoparticles. Just to the conclusion, because the time is running. This is a curiosity, are the Prince Rupert drops or Batavian tears. And these droplets are characterized by very high residual strength, are obtained by dipping molten glass into cold water, which causes to solid into a tadpole-shaped droplet, so with this very long thin tail. So what happened? If you use a hammer or mallet on the bulbous without breaking, but if there is an explosive disintegration in the fine dust in the tail, even slightly damage, causing, of course, the release of the enormous energy storage with the stress. In nature, similar structures are produced under certain conditions in volcanic lava, are known as Pellet's tears. There are some examples. Laboratory, I'm a chemist, so laboratory glassware is required not only for the alchemist, but also for the chemist. It is required for a virtually every type of chemical, biological analysis. In this case are borosilicate glass, which made of silica and boron oxide is the most common material for laboratory glassware due to its resistance to high temperature and corrosive material. So, this is the end. I would like to thank for your attention. I like too much papillon. And I ordered that one, but unfortunately it doesn't arrive in time because this was a papillon in glass. I use this alternative with in plexiglass, so it's not a real glass. I'm sorry.
Thank you. So we still have time for questions. And before lunch, you will be able to look at all the, I didn't know that the gold could make such an effect depending on, I learned really this today. Thank you. So there were questions related to previous speakers. So I think that Professor Bettini had one, and then, okay, to Professor Psaro. So please, Sandro.
Yes, maybe can I say that we owe to Angelo Barovière also the telescope of Galileo Galilei with the optical qualities of those lenses? I am exaggerating a bit, maybe.
I thought you were... No, cosa ha chiesto?
I think that
No, but the lenses were made in the 14th century in Venice already with vitrum blancum, and I know that Galileo was a good friend of a certain Sagredo, and at the end he did not use the glass made in Florence but the glass from Murano, mainly from the same glasses it was used to make crystal glass mirrors. That was a very high quality glass. So Galileo used at the end Murano glass. The same, the development of the glass invented by Angelo Barovière. The same crystal glass, probably better, of a higher quality in the time. So there is a link, I think.
it was the high technology of the time, of course. Yes.
May I comment on that? For an astronomical lens, there are two things which are necessary in the glass at the Galileo time. One is the transparency, and this is the reason why I choose the Murano glass. And the second is the grinding to give the surface. And the grinding of Galileo is unclear as far as I know how it happened. But the selection of a silica for the glass to have it as much transparent as possible was really a key point. But it was achromatic, it was not perfect. Only the introduction 2 centuries after of the flint and crown glass could solve the problem.
Professor Bracco over there. So.
Curiosity for the last speaker. I just would like to understand how much companies or industry are using nanotechnology for the color of what they produce. So it's just a remark from research, or it's just there is already technology based on nanotechnology to to be used in coloring glasses by industry.
Rinaldo, can you go back to your microphone, please?
So really, on the glass, I'm not really experienced, so I show you this long travel. The application, anyway, of metals at nanotechnology level, for example, in another word is catalysis, is very peculiar now, because it's evident that you change completely, particularly in the case of gold, the properties. So I don't know if this is the answer, what is nanotechnology or nanoscience, but it's real when you go down in the dimension, the properties are completely different in terms of physics and chemical property. This is very peculiar. And for that reason, I think is an open mind for different applications. We use copper in catalysis, gold, but it's very, really, as a chemist, we speak many time ago of nanoparticles, but now the concept of nanoparticles is a change with more importance. And it's just, if you are interested, it's possible to see the presence of nanoparticles, the typical is possible to see the presence in that solution, but one could say, you had some drop of colorants. By using a laser, if you put the laser, this is a Tyndall effect. Possible.
So I would say, okay, bello, do it again.
It's possible to see the
yes,
reflection. The reflection is due to the presence of metal particles.
Last question from Bernardo Spagnolo.
Sorry, just at the beginning of your talk, you speak about the movement, the absence of movement of glass. But nevertheless, when you put in a vertical in a vertical line or surface, there are some molecules. You don't need to go to the transition temperature, but there are some molecules, because of the effect of the temperature, can become free and depositate in the bottom because of the gravity field. I saw many windows of old palace, old building is known for the life of one man, but 2 or 3 centuries, because in the past they build a palace for forever. So some content for you about this, because I believe that there was from some slow movement in this sense.
Okay, thank you very much.
You can. Okay.
I thank you for this very interesting observation.
I would like to conclude to ask Teresa Medici to tell us about what you told me yesterday about the Lycurgus Cup and the International Year of Glass.
The 7 glass wonders.
Yes.
Yes, in fact, in the framework of the International Year of Glass, there was a competition was launched, was a challenge to find 7 glass wonders in the world and in the history of humankind. So every kind of glass objects of glass application could be presented. And in the last week in Tokyo, in a closing conference of the International Year of Glass, there were announced these 7 glass wonders. And if I can quickly resume for you, in the chronological order, the first is the Egyptian glass from the Tutankhamun grave. The second one is the Lycurgus cup, and then you understand why. It's really not only for the composition of the glass, but also because of the technique. This is among the small group of cage cup, this is the only one with figures, because usually they are with letters but this is very complicated to do. Then we have the stained glass, medieval stained glass of the Sainte-Chapelle in Paris, dated to most of the glass are already still the original glass from the 13th century. Then we have the Blaschka collection of flowers. I don't know, the Blaschka brothers were 2 men from Bohemia working the second half of the 19th century, and they were specialized in lamp working, and they were produce replica of specimens for scientific collection in university and the natural science museums. And they were really specializing in reproducing marine being, but the most spectacular is this flower reproduction collection that it's in Harvard University Museum. And then we have the Corning Museum glass, because Corning, to celebrate the company, to celebrate the first 100 year of life in 1951, decided to open a museum, a library, and to create this as a leading institution for the glass studies in the world. And there are still, for us, for people studying glass, really a reference. And they published the international journal, the Journal of Glass Studies, that I can say it may be the only scientific journal accepting paper in Italian because of our strong tradition in Italian studies. Then you have the optical fiber, of course, because they're key factor for the developing of the humanity, and the Hubble telescope, because the 2 mirrors they are making in glass. So of course, this is quite a symbolic competition because it's very difficult to find 7 glass modes, but I think that it's resume really a lot of several aspects of the importance that glass has and still have and will have in the future for our life.
Thank you. Thank you. So we thank the speakers again. I have few things to tell you. First of all, you can admire a nice Renaissance stainless glass at the back of this wall, if you want, when you go now to lunch. We should resume after lunch at, say, 2:15. And the other thing is that if you have time, if you grab something, you may visit the exhibition of the naturalist of the 16th century of Bologna, Aldrovandi, which is just next door and upstairs in this very palace. The only point is that the entrance is not free, but apart from that, if you have time, you can visit. So thank you very much to all the morning speakers.
Voilà. So good evening. Welcome back. We start the first part of the afternoon section. We switch to use of the glass in science, in modern science, I should say. The first speaker is Michele Punturo from Perugia, INFN, that will tell you about the glass to explore the space-time, gravitational waves, I would guess.
Okay, thanks. So the preparation of this presentation has been a challenge because I need to explain first what I mean for explore the space-time, how we explore the space-time, and what is the space-time, and then how glasses, or better in our case, fused silica, played a crucial role in important discoveries that occurred a few years ago. So, the first reaction is, wow, glasses space-time, how to talk about that? And the first question to answer is what means to explore the space-time? So I'm sorry, there will be few formula, but I will go very quickly through them, and I will try to make it as simple as possible. So we are here in a room that more or less is a square room, and we are used to indicate a position of everything through 3 coordinates. So in fact, we are in the classical vision of our space, not space-time, of our space. We are living in a Euclidean space, and we represent in mathematics, geometry, physics, everything through Cartesian coordinates. Then, if you want to have an important concept that is a distance in a space, maybe the most important concept is a distance. Okay, the distance is given by very simple formula. So you have that is the Pythagoras formula essentially. The distance between 2 points is given by the quadratic sum of each coordinates, different coordinates between the 2 points. And then if you are talking about space-time in classical physics, okay, time, the difference of time is one moment and the other moment. So are 2 completely independent concepts. Time and space are completely independent. Okay, then if I move a space with respect, okay, this formula can be written in this way if you like mathematics, but you need to write in this way when I talk about general relativity. Then if you have a 2 reference system, okay, I change this place, this object, these 2 reference system, and I relate the movement between the 2 reference system by using essentially the Galilean relativity transformation. And it is quite simple. If this object is moving in one direction, the formula that relates the coordinates is very simple. Then, we are here. You are in your chair. I am standing here, and we can do everything. This because there is gravity, and for everybody since the beginning, we say gravity is a force, and we have to fight against this force. Okay, this is a classical vision of our space-time. Okay, this is a formula that there is Newton tell us how this formula is expressed. Okay, perfect. Then there arrived this guy. I suppose you know who is this guy. So Albert Einstein, and first tell us no, the space-time is 4-dimensional. Time and space are intrinsically related. And then if you want to describe the distance in space-time, you need to use these 4 terms Pythagoras theorem. And so the matricial representation or tensorial representation that you have to use is this one. Okay, there is one more rank, is a 4x4 matrix. And if you like to write everything in a compact form, you can write in this way. This is called the Minkowski tensor. Okay, and then what is nice in this expression that a particle that is moving in a trajectory has to respect this concept here, the fact that the distance is smaller than 0. This is just a way to say that you cannot go faster than light. And then if you are light, if you are a photon, this distance is equal to 0, or in this case, this cannot be the 2 points in a trajectory of a particle. And in special relativity, gravity is absent. Now, the real revolution in the vision of a space-time arrives with the general relativity. In the general relativity, the space-time is curved, and you can express again in mathematical way, in a similar way, but this is a more complex tensor. This is a metric tensor. And what you have is the fact that the gravity is no more a force, but is geometry. Gravity in general relativity is geometry. And the presence of mass is generating a curvature of the space-time. And any other object, like the Earth around the Sun, is forced to orbit, not because there is an attraction, but because there is a deformation of the space-time, and you are trapped in this curvature of the space-time. So let's look at this statement. I will use it later. The trajectory of particles that are not affected by other force with respect to gravitational force are called geodesic. And then studying the trajectory of these particles that are not affected by other forces with respect to the except the gravitational force, to study the trajectory, you can reveal the curvature of the space-time. So this is a space-time with a positive curvature. In this case, the saddle is a space-time with negative curvature. Okay, now I think that's all for general relativity in 3 slides. Maybe I can say one slide more, maybe in general relativity that I like to show here. The mathematical way used by Einstein to express what I told you before is through this equation. In reality, is a complex system of equations. And I like to represent it because it is a formula that relates the cause of the space-time curvature, that is the energy or mass of your star, your black hole, and the curvature of the space-time that it generates by this term that is a constant, okay? And when you compare a curvature with a deformation with a force, in classical physics is the Hooke law, the elasticity law, okay? Then if you consider the space-time like elastic medium, you have that this is the inverse of the elasticity. So this means that the space-time is incredibly rigid. So to deform the space-time, you need a huge amount of energy. Okay, this is the message that I wanted to give you. It's a very naive interpretation, of course, but I'm an experimentalist. I am allowed to make a very naive interpretation. Now, how we explore this space-time? Modern physics is exploring the space-time through another expectation of general relativity, the gravitational waves. I told you that the mass curve the space-time, but it's not only a static curvature. Like there is a bending of a rod, there is also a wave in the rod. Now, like there is the bending of the space-time, there is a wave in the space-time that are called the gravitational waves. Okay? There is a ripple in the space-time. And these waves are essentially have an effect on the space-time. If there is a wave, there is a distribution of mass that is circular, is perturbed by a wave in this way with 2 polarizations. Okay. In very, very simple way, we can see that is modulated the distance that I showed you before. Voila. Who is generating these waves? The waves are generated by compact objects. by stars, by black holes. But if you walk by stars, all the stars by me, I'm moving like that, I'm generating waves. Okay, but if you want to detect this wave with waves, you need to have a huge mass with the north circular distribution, accelerated, and the wave, this term is very small, then the wave is very small, and this is the effect of the rigidity of the space-time. It is damped, it goes down in amplitude like 1/r. That is a crucial point. We will see the next talk telescopes, electromagnetic telescope. Everybody is used to the electromagnetic telescope. Electromagnetic telescope are looking to power. So the signal goes down 1/r². We are looking to amplitude. Our signal goes down 1/r. This is an incredible advantage because we can see very far in the universe. Okay, and this is a typical signal that we expect. Okay, then if you go to the absolute value, you need to measure. And an amplitude, for example, a typical gravitational wave is perturbing 1 kilometer length by 10 to the minus 19 meters. So we saw these beautiful glass nanoparticles, nanometer, 10th nanometer. Okay, this is 1 billionth of one nanometer. So it's something that is smaller of the radius of a proton. Okay, by order of magnitudes. So for this reason, Einstein said, okay, the effect is no practical interest since it's too small to be detected. That was a statement by Einstein. But physicists don't believe to ipse dixit, and we attempted to measure. And after 1 century, we had been possible. In fact, the prediction of gravitational waves started in 2016. There has been a long evolution of technology, first with the resonant bars, with observation through radio pulsar, and that generated a Nobel Prize in '93. But okay, until that, there was not a direct detection of these gravitational waves, but started the idea of interferometric gravitational waves and detectors. And the idea of this kind of detector are related to this shape of the wave that I showed you before. So let's go here. The space-time by this wave is deformed in this way. And then we are entering the optics, so we are arriving to the glass. How to detect this object? The most appropriate way is to build something that is sensible to this difference of length, optical length. So it's a Michelson interferometer. And a Michelson interferometer seems a natural choice for that. And in fact, in the 1920 was realized the first gravitational wave detectors, so interferometric, LIGO and Virgo, after 4 years, entered in operation. And okay, how it works? If you realize that Michelson doesn't work, it's not enough, because you need to have hundreds kilometer length to have sensitivity. I haven't told you, but you need a huge object to detect this tidal force. And if you wanted to realize an object of 100 kilometers in the Earth, an interferometric device doesn't work because the Earth is rounded, is spherical. I can tell you the Earth is not flat. Okay, we have the proof. We cannot realize this object in the Earth. Okay, without a trick, is like having a Fabry-Perot cavity. So there are mirrors here that are reflecting the light back and forward for hundreds time in order to have an equivalent 100 kilometer object. In our detector, this is 3-4 kilometers, but the optical length is 100 kilometers. Okay, and this is the first step. And how do we realize this mirror? We are realizing with glass, or better, fused silica. It's a synthetic fused silica, okay? As pure as possible. And this is crucial for our purpose. So essentially, these are there is just one producer in the world that is able to produce with the quality that we. I heard this morning about the coatings coming from Australia. So to produce this mirror substrate of Australia, I coated in Europe. These mirrors are produced in Germany, are polished in US, and are coated in France, because there is just one laboratory for each continent or each country that is able to do that. Okay, this is the only configuration, and I mean we are using in Europe in Virgo. LIGO is using in the US, but the same path is made by all the mirrors because there is just one possibility. Now we are attempting with a new one. Do the polishing in Europe, but because cost less, not really because. So the characteristics are pure fused silica substrates and multi-layer is a tantala, so is pentoxide, tantalum pentoxide with doped with titanium coatings, and our alternate layers of these mirrors are realizing Bragg mirrors, okay, in this way. The optical and mechanical requirement of this object are incredibly stringent. For this reason, we have just one laboratory in the world that is able to do that. And for example, these mirrors are 25 centimeter diameter, 20 centimeter thick, about 40 kilograms. The beam splitter reality of the Michelson is larger. And one of the first characteristics is the absorption. We need to absorb less than 0.5 part per million per centimeter. And the polishing requirement, as I told you, there is one, maybe two now laboratories able to polish at this level. The micro roughness is less than 1 Armstrong RMS, and they should be very flat in the central part of 15 centimeter. So the coatings, the requirement coatings are even more stringent. COVID coatings are glass, so in some sense are also glass. So you have a flatness, very stringent flatness, and the scattering losses should be lower than 10 ppm per round trip, and the absorption is less than 0.5 ppm. Okay. And okay, then the optics should be to mirrors as equal as possible, and then are produced. There is just one coater in the world large enough or quality enough to produce them. It's producing two mirrors at the same time in order that the two mirrors have the same characteristics. Otherwise, there is mismatching between the mirrors that we are producing. And our lasers are working at 1 micron, but in reality we are using different wavelength because we are resonating different beams in order to make the different kind of contrasts. Okay, so these are the optical requirements. Then the optical requirements are less stringent of the mechanical requirements. But to talk about mechanical requirements, I wanted to make a digression and change a bit. Let's go back to the general relativity. We are realizing what Einstein called the free-falling system. Okay, as a particle, a mirror, that is not subject to other force with respect to gravity. How to do this? In orbit is very easy. You have a satellite, there is just gravity, and this is continually falling in the orbit, and this is a free-falling mass. But how to realize in the Earth? The easiest way, or the most close way to realize a free-falling mass is a pendulum. Okay, the old pendulum that you study the first year of the. So the pendulum is really free-falling, not in the vertical direction, of course. There is an elastic reaction of the wires, but in the horizontal part, close to the equilibrium, is a free-falling object. It's really free to oscillate, almost free. Okay, and then what we are realizing, the free-falling masses in the Earth, isolating the test mass from the vibration of the soil. In this moment, my foot is vibrating of the order of 1 micron, and I need to measure on 10 to the minus 20 meters. So I need 14 order of magnitude of damping. Okay, we realized a mechanical filter that filters 14 order of magnitudes. This is a technology realized first in the PISA INFN unit and the university. And then all the optics in Virgo are suspended through these systems that are filtering, and they are realizing free-falling systems. Okay, and okay, it works. So everything is solved. It seems that we realize that we can detect the gravitational waves. No, I'm sorry, we cannot do that because I am at 300 Kelvin. Everybody is more than 300. Okay, I'm alive. So my molecular, my atoms are vibrating because I'm fine at the temperature. And how much it is this vibration? Okay, let's make this simple computation. The thermal energy that an oscillator, everything is an oscillator in physics, a terminal energy of an oscillator is given by this simple equipartition theorem formula, principal formula. And then if you put the numbers, you have you have the number of this energy. Then if I am an oscillator, this is the energy, mechanical energy in my oscillator. If you compare these two objects in a very stupid way, you have that the RMS of the vibration is 10 to the minus 12 meters. So I cannot measure anything because I needed to measure 10 to the minus 20 meters. So I have to scratch my head. I think, is it possible to do that? Yeah, because I'm realizing an oscillator and a pendulum is an oscillator. Let's look in oscillator. The pendulum is doing like that, no? Then why the pendulum is coming back? Because there is the restoring force. The restoring force is gravity. Okay, this is the pendulum that we teach to the student. But the real pendulum, there is also the elastic force of the wire because there is not a monodimensional wire. So the wire has a dimension. So there is an elastic force of the wire. And the elastic force of the wire it can be expressed like with the Hooke law, elastic law, but where there is a structural loss angle, there is a dissipation, is losing energy in some way, okay, this object, because internal mechanism. And if you work a bit with the mathematics, with the fluctuation dissipation theorem, I don't want to annoy you, and then if you ask me, I will tell you how it works. What happens if you take an oscillator can be a pendulum, a mirror, can be the violin modes of the suspension, can be the mirror's vibration mode. If you make a simple formula, you see I'm starting from the equation of motion, so a physicist should do it at the first year, you obtain that the spectrum of your thermal fluctuation is this object. This object is a resonant object. Okay, an oscillator has a resonant frequency, I'm happy. And you have the Q, the quality factor of this pendulum is given by this dissipation angle. The dissipation angle that I introduced you before in this structural loss angle expression. Now, this is a crucial result, okay? Because if I wanted to realize even something to detect the gravitational wave, I have an excess of thermal energy, but I can put all this thermal energy in the resonant mode, and then outside the resonant mode, I'm free from oscillation. So I'm totally blind in the resonant mode, and I'm working well outside the resonance. So I need to find a very high Q material, okay? And this plot, that is one of my first plot when I started to work in Virgo, and in the 99 was this. So it's a comparison of all the metals that we tested with respect to glass. So you see this incredible difference between metals and fused silica. This simple plot shows you many things that, okay, there is the structural loss, but there are other effects. This peak is called the so-called thermoelastic peak. And then in reality, you here are limited not by losses of the material, but the so-called residual clumping loss. Okay, and this means that we needed to make a design very complex. So let's go through this path. So we needed to find the material with the lowest dissipation. We needed to take into account other thermoelastic effect. We needed to to realize our suspension in order that the restoring force is given mainly by the gravity and as less as possible by the elasticity, because gravity is a conservative force. Gravity is not dissipating energy. And then if the restoring force is the gravity, we will have that our system is not dissipating. This is called the dilution factor. Essentially, then I have to minimize clamping losses. Perfect. Then why the fused silica is lossy? Why there is this dissipation? In metals, it's easy. In metals, there are imperfections, okay, and on different crystal planes and so on. And these are main cause of dissipation. In fused silica, in reality, what you have is the fact that you have these silicon-oxygen bonds. And what you have that if you look at the potential energy landscape in this amorphous, you have a system, a two wells, double well structure like that, with the difference of potential energy level, okay? And when you have a wave that is passing through your system, this potential structure is deformed, and spend time to find a back equilibrium. Time means lag, means dissipation, okay? The retard is dissipation. And so this is essentially the explanation. So it's really related to the different angles of the silicon-oxygen bonds inside the amorphous. And this is crucial for what I will tell you. Okay, I annoyed you with all this part. But this part is crucial because we worked for years between 2000 and 2010 with metal wires and not very good mirrors, and we have been unable to detect gravitational waves. And then in 2015, LIGO, in 2017, Virgo, were realized using fused silica suspension and very good coatings, good coatings, and test masses, and okay, arrived at the Nobel Prize because we detected the gravitational waves thanks to the improvement in sensitivity, mainly, not only, mainly given by this process. Okay, let's talk about the fused silica suspension. Then these are the suspension of Virgo. These are fused silica, so glass objects. These are glass fibers, okay, and 400 micron glass fibers with a special shape that is important to reduce the dilution factor that I mentioned to you, the fact that the large fraction of the restoring force is the gravity. And we need to realize these objects with a monolithic design altogether. And there is no in the industry that produce that. I'm sorry for us, not for it. So we need to build our fiber producing machine, but it's not a fiber, it's fiber with strange shape with big heads, okay? And this is object that we realized in the Firenze Urbino INFN team, realized this machine that is producing these strange fibers. And let me reduce a bit. Okay. You see, there is a laser, a CO2 laser. This is a mirror. Because we need this laser that is illuminating in a uniform way the fiber. And then there are two motors that are pulling and pushing the fiber, the rod, in order to produce this strange shape for dilution factor and produce this fused silica fiber, okay? And the laser is pointing here. You don't see because it's infrared laser. And we are able to produce the fiber that we need. Are fiber robust? Okay, if you look at the breaking strength of fused silica is huge. It's wonderful. And then you break everything. And because the bulk breaking strength is very high, but the glass has a fragile behavior. So the breaking strength of a fiber is dominated by surface effect. If you have a defect in the crack in the surface, you break after a while, after a load period, you break your fiber. And the effect is catastrophic, okay? So we are testing our fibers, but then there are physicists that want to play and say, okay, let's suppose that we are able to produce a fiber without cracks. Are they robust? Okay. Now we like to work with hammers. We are doing experimental physics for that. No, playing in the lab. And then these are 400 micron fibers sustaining a 40 kilograms object, and people is hammering on it. Okay, and it's wonderful. If you remove the cracks, we are removing first we made with hydrogen oxygen flames. Now we do it with the laser. And you have a very good breaking strength. The problem that if you have a contamination in your tower, and we had a huge problem with that, so dust particle generated by vacuum pumps that were a little bit damaged, old pumps, then you are projecting particles of dust on your fibers, and you have a crack that is sub-micrometric, but this grow up in our days and then it breaks everything. Okay, so this is very crucial. But okay, people is really playing. It's fun in laboratory that we are doing that for fun. Okay, I told you that we need to have a monolithic fused silica suspension. Why monolithic fused silica suspension? Because there is you saw in my plot there was the so-called clamping loss. If you have a wire, you have to clamp it. You have to keep. When you clamp, there is dissipation. We need to clamp in a way that in reality we are building a monolithic object. That everything clamp, wire, taper is everything one single object. And to do that, we are doing a bit of chemistry. So we realized a bonding technique that is called the silicate bonding, that essentially is reconstructed between two pieces of fused silica, is reconstructed the SiO2 chain, let's say, by using catalyzers like potassium sodium catalyzer, but really a very negligible quantity. And we are able, after a curing period, doing this in very clean condition. This is not a very clean condition, was a test. But doing it, we are able to build this object that is like one single piece of glass. Okay? By doing that, by gluing with this technique, these anchors to the head of the fibers and so on. And this is crucial for the suspension. Then we learned that the dissipation in the glass is crucial for the suspension. It's crucial also for the mirrors, but not so much for the mirror. This is a curve that tells you the noise that we are able to fight. The black curve, the sum of the noise. And if you look to the mirror thermal noise, I think that is here. Okay, this orange one, if I'm not wrong. So the fused silica is so good that bulk fused silica that is not annoying us in thermal noise. The problem are the coatings. The other glasses, the coating that we are using on the mirror are very dissipative. Okay, and the thermomechanical properties of these coatings are the most limiting factor for the sensitivity of the current gravitational wave detector. So for this reason, there is a global R&D plan to resolve this problem in US, in Japan, in Europe, and in Bologna, for example, also here. And we are working on this aspect to reduce this dissipation. Just a picture to show you this was a Virgo mirror, this advanced Virgo mirror is more complex, but the concept is similar. And okay, we have been able to realize all that, and let's see what we have been able to demonstrate. With the advanced detectors, with the first 3 runs, we've made the first detection of gravitational waves never made, and we started to make the physics of black holes. The first detection of gravitational waves from a binary neutron star system, and it was the real birth of multidimensional astronomy with gravitational waves. And we have been able to localize source, to test the speed of propagation of gravitational waves, test of general relativity, so a huge amount of tests. And this is the signal that for the first gravitational wave detector, so is a detection of black hole. You see this the chirp that I showed you in a plot before. It's an 8 cycle of this black hole. These are 2 black holes of 35 and 30 solar masses that are in a fraction of a second. You see, it's really a fraction of a second. Makes all these cycles and sweep the frequency from 32 to 200 hertz, more or less, and then merge. So we have a phase of a spiral merging, and we are not able really now to detect the ring down, but when we will be able to detect that there is a huge amount of physics inside. But what is very astonishing is 2 years later, LIGO and Virgo detectors detected the coalescence of 2 neutron stars. And now we are talking about neutron stars, not black hole. Neutron star is matter, black hole is mathematics, sorry for this approximation. And the matter, especially the matter, there have been light. We saw the light arriving. There is atoms, nuclei generated by this interaction. And what was impressive that we detected the wave, and after 1.7 seconds, the Fermi satellite detected the light, and we have been able to localize the source in this way, then improve the bioastronomical observation. And a network of 70 telescopes were measuring for days, weeks, months, the electromagnetic emission that was in all the wavelength that you can imagine. And what is nice, what I like to say now, that since there is matter, there are fusion process and nuclear process, what we have that starting from, thanks to the silicon and oxygen, okay, we can say thanks to the silicon and oxygen, we understood the origin of EV elements. EV elements like gold are not produced in normal star in the sun, okay, 2 EV. Above the iron is not possible to do it in the star. Was expected to be produced in the supernova, an exploding massive star. But what we learned that the collection of neutron stars are 5 minutes, perfect, are the right place where to produce EV elements. So thanks to glass. Okay, now we are satisfied. We go home, we drink our cocktail. That's all. No, because essentially, when we have x, you want x squared, and this is the sequence of a subset of the detection that we had with the advanced detectors, LIGO and Virgo. So it's distance with redshift with respect to mass, and this is where we wanted to go, because where there is a huge amount of physics that we want to study. So we needed to jump an order of magnitude even more in distance in order to see this, the physics that we are interested in. So we needed to start from the current detector to go beyond. And another way to say this is the present, this is the history of the universe. This is where we are in capability to investigate. This is the limit for the current gravitational wave detectors, and this is where we want to go before the formation of the first star, to see what happened before the formation of first star. And for this target, we are studying, hopefully realizing a new project that is called the Einstein Telescope. That is a new infrastructure, longer, with underground, cryogenic, with an improved sensitivity, maybe factor 10 normally, but much more the low frequency, in order to investigate the whole universe. This is all the astrophysics that we want to realize with this machine, and we will not go through all this, but you can read. And this is a fundamental physics. So it will be an incredible discovery machine, and an incredible precision measurement machine. To do that, we need to realize 2 machines, one in room temperature, one cryogenic. So we need 2 development lines, one based on the current detectors and one completely new. In the new one, we will change the test mass, no more glass, sorry, but we will use silicon, okay, or maybe sapphire. And new coatings, again, the problem of coatings, what we attach on the mirror to transform it in a mirror is a problem. Maybe we will use crystalline coatings. And why we cannot use fused silica? because dissipation of fused silica. I told you that the dissipation is given by these angles. Then if you go at a low temperature, you have that these dissipation angles as a maximum around the temperature that we want to use for our detector. And so we cannot use a fused silica at 10 Kelvin because it's strongly dissipative. Then we use a silicon. What we use to make a reflectivity, again, the tantalum seems not the right solution. And then now we are investigating a totally open question. I have no answer. Crystalline coatings or hafnium oxide. So this is, for example, a paper that you can read where they are thinking to realize a multi-layer, multi-material coating using amorphous silicon, so we can call it glass maybe, amorphous silicon, and using other materials in order to realize this coating. Now in Italy, we started the 1st of January, a project founded inside the PNRR that is called ETIC, Einstein Telescope Infrastructure Consortium, where there is a pan-Italian collaboration to candidate the site in Sardinia and to realize technology. And we are in Bologna, and both INFN and, Bologna is here. Both INFN and the university are collaborating to this project. And the conclusion, okay, glass is crucial to detect gravitational waves in LIGO and Virgo. Optical quality of fused silica is essential. Optomechanical quality is even more essential. And it's a challenge. We are working to that. Thermomechanical properties of fused silica suspension are one of the tools we use to detect the gravitational waves. But we have a new challenge in front of us. So we need to develop better performance glasses and new crystalline materials.
Thank you for the talk. We have time for questions.
You share the microphone. Okay, perfect.
Thank you. Thank you, Chairman. And sorry, just the time scale of the relaxation time of a stable system is, of course, is connected with the Kramer time.
Yeah,
it depends on the age of barrier, yes, and the intensity of the thermal noise. No,
yes.
Just
yes,
very short question. Okay. So in this direction, it is possible to make improvement, of course, of the time of the relaxation time.
How? We are doing it by annealing, because if there are stress, you have this double well is deformed. Yes. But then how to reduce it? With dopants.
Yes, yes.
But the optical properties then?
No. You can improve. You can change this.
Yeah, we are changing by using different fused silica.
Okay.
But the problem that you have different constraints. The first constraint is thermomechanical properties. Yes. The other is absorption. Okay.
Yes.
And then you have also scattering, the number of defects. So at the moment there is one single fused silica that is with our quality. I can tell you is not advertising. Is Ereus Suprasil 3001. And 3002, there are two different, one for the splitter and the other for the test mass, but there is just one producer with these characteristics.
Thank you.
There's a question there.
I have 3 questions.
3? One by one, because at the third I forgot already the first one.
Okay, first question. Supposing you've got 2 universes and one has gravitational waves and the other doesn't.
Oh my God.
So what would be the cumulative difference between the two?
This is too complicated. I don't know. I have already difficulty to understand one single universe. And how these 2 universes are communicating, I don't know. If there is no gravitational waves, it means that the general relativity is not valid in the second universe.
So big repercussions.
Sorry?
So there would be big repercussions. maybe. Okay,
I don't know.
second
You
question.
should ask to a philosopher.
So, second question. You said there are only 2 potential energy wells in silica, but my understanding of silica is different bond lengths and bond angles everywhere. So more
Silicon, you said, or silica?
Silica.
Okay.
But my understanding of silica is many different bond lengths and bond
Exactly.
angles. So why not many potential wells?
Yeah, there are many of these double wells.
Okay.
It's not one single one.
Yeah.
In fact, I called, if you read the text, is the potential landscape, because you have many of these and with different angle.
Okay.
And the sum of this angle, you have this total behavior. Sorry, I made a simplification by giving us.
I understand. Thank you. And my final question is, I teach sort of general materials to mechanical engineers, and always very impressed with the properties of diamond. It's the stiffest material, and you can now make synthetic diamonds. So why not go for diamond?
I'm not expert on diamond. I think that it is birefringent. I'm not sure, but it should be birefringent. No, it is not. I'm not expert on diamonds. But
John Parker will know whether it's birefringent.
Okay, let's
okay.
Maybe there are other questions. Let's leave some time to other questions there.
Okay.
There was a question there, maybe.
I'm a bit afraid to have a diamond like that. So, but silicon, the other, why with silicon? Because silicon industry is huge, and they are building huge objects, and we are interested to industrial production.
Other questions? If not, we thank. Oh, use the microphone.
Just about the coatings. If I understood you said that there were less stringent conditions on the coatings.
No, they are very challenging.
Okay.
No. Coatings are very challenging, and because the optical characteristic is challenging because it's a Fabry-Perot cavity.
Yeah.
Then the mirror attraverses the ones. The coatings are touched hundreds. Okay, if there is a defect, dissipation on the coatings, you multiply by the number of bounces. And so optical characteristics and mechanical characteristics for this reason are incredible.
Okay.
Okay. Then we thank the speaker again. Andrea Cimatti from here, from Bologna, glass and telescopes. Of course. Okay. Thank you very much. Thank you.
Okay, so let's move to the very first slide. Just to remind you that before the telescope, there were already optical devices, let's say, based on glass, the use of glass, that were used, for example, to build and to use eyeglasses. And this is a detail from a painting of 1352, where you can see very well that this guy is using eyeglasses. And before the telescope, the let's say, spy glasses, or also called the spectacles, were invented in the Netherlands. And here you can see, for example, one of them in this detail from a painting of 1611. But they were not used to explore and to study the sky and the universe. That was done always in the early 17th century from Galileo, as you know very well. So 1609 is taken as let's say the birth of astronomical observation with telescopes. And the telescope that Galileo used was built by himself, taking inspiration from the invention in the Netherlands of spy glasses. There are also claims in the literature that the very first observations of the sky with telescopes were done by Francesco Fontana 1 year earlier. but this is not, I think, as I understood, fully accepted by the community. Anyway, it doesn't make any difference for this presentation. So soon after the invention of the astronomical telescope, there was an evolution of the optical design proposed by Kepler, with an improvement, for example, a more uniform illumination of the field of view, a wider field of view, and also a slight reduction of the optical aberration that I will mention later. And there was a very rapid evolution also of the size of a telescope. And this is the very famous giant Hevelius telescope, which is this length, which is 45 meters, and we are in 1673. Okay, so a very fast evolution, but with many technical challenges to be faced. So I risk to explain something very obvious, but let me remind you, for non-astronomers, what are the main advantages and the main roles of a telescope. First of all, is to collect many more photons and much more light than the human eye, of course, and that in astronomy allows to observe fainter sources and to observe at larger distances. And the other advantage is that telescopes magnify the apparent size of the object, so they allow us to study the finer details of these objects. And the heart of the telescope is, of course, glass. And this is the optical design of the original Galilean refracting telescope, where refracting means that a lens is used as a main optical element for the objective. And the size of the telescope, the objective was about 4 to 5 centimeters, the Galilean telescope, and the length, the focal length, so the distance between the objective and the point where the image is reconstructed from the focal point of the image, was about 1 meter. Now, I mean, we can use optical glass, which is the highest quality glass that you can use for building this kind of lenses for astronomy. And this is an example from the Vera Rubin telescope, which is in the building phase. So optical glass means that this glass has the highest purity, homogeneity, durability, surface accuracy, so image quality, highest image quality, and transparency and thermal stability. And now, depending on your application, you can choose between about 50 materials that you can use to tune the characteristics of the optical glass that you want to use for your own telescope. And the main materials are oxides, such as silica, boron oxide, and alumina. Then another problem that was faced by Galileo and in the 17th century was the problem of the optical aberrations. So telescope images are not perfect. So here you can see 4 stars without any optical aberration, but this is the real life of astronomers when they do not have ways to correct for these aberrations. So this is, for example, the spherical aberration, where the different rays focus in different places in the focal plane, and they produce a sort of a defocused, blurred image. This is the famous chromatic aberration, so where let's say light rays of different wavelengths focus in different places of the focal plane, and they produce a sort of a rainbow-like structure. And this is the coma aberration that is stronger if you go to the edge of the field of view. So Galileo's observations were done through telescopes affected by this kind of problems. Despite optical aberrations, there were, of course, very, very famous scientific milestones in the 17th century. The first came, of course, from Galileo, that was the first human to observe the moon, the sun, the planets, the stars, and also understanding that the Milky Way was full of stars that were not visible with the naked eye. And these are the original drawings from Galileo's observations. He also discovered the famous 4 Jovian Jupiter satellites. But, for example, in the same century, Huygens in 1659 discovered the rings of Saturn and also many satellites of Saturn. So that this was really a century of, let's say, full and complete revolution. But the evolution of the telescope continued in the 18th century, with an effort to correct for the optical aberration. That was the main achievement from the technological, let's say, point of view, in this century. And the main achievement was thanks to the work of Hall and Dolland in the first half of the century, who invented the so-called achromatic lens to correct the chromatic aberration using 2 lenses with this optical design and these shapes, so one convex and one concave lens, to focus rays of different wavelengths in the same place of the focal plane. And this is one of the Dolland original telescopes. In parallel, there was also a mitigation of the spherical aberration through a combination of optical lenses, new optical designs. This is too technical for this kind of presentation, but there was this effort to produce better images to better understand the cosmos and the astronomical objects. And the evolution of the size of telescopes increased a lot during this century, ending for refracting telescopes, so telescopes with an objective lens, with the largest refractor at the Yerkes Observatory at the end of 19th century, by the way. And this is still the largest refracting telescope, which is too large, too big, and no other refractors were built larger than that. But there was another parallel revolution that came online, let's say, together with the invention of the reflecting telescope. So that was an invention coming from Newton at the end of the 17th century, who proposed a new telescope where there were no lenses, but a mirror with a spherical curvature, very small. This is one of the original ones, 1672. You see 5 centimeter diameter. And there was a very fast evolution to a very, very large telescope for that time. This is the very famous 48-inch, which is about 1.2 meter diameter telescope used by William Herschel. And the largest one in that century was the Lord Rosse 72-inch telescope. And here there is no glass, by the way. It's a sort of a period of the astronomical history where no glass was used here. So the mirror was actually made of metal called the speculum, which is a combination of copper and tin that gives a very highly reflective surface. And the optical design is the following. So light rays come from the left, they are reflected from a surface which is curved, and they are then reflected back from a secondary mirror here, where you see the eyepiece, and the astronomer is actually 90 degrees from the light rays propagation. Okay, there were major milestones also in this century. So we are in the 18th century. First of all, Herschel discovered the planet Uranus, and this is the original drawing for that discovery. So a new planet in the solar system that was not visible with the naked eye. And also the very first map of the Milky Way, counting the stars with this big telescope, the 48-inch telescope, in 1785. Okay, so that was really a major effort done by Herschel. So we move, you see, I try to follow the evolution, the historical evolution of, let's say, technology, and then also the main scientific milestone that were possible thanks to telescope and thanks to glass, of course. So 19th century, this is really a revolutionary century. We are back to glass. So mirrors for the reflecting telescopes are too large, too heavy. So they started to use glass to build the primary mirrors. And there was also a proliferation, let's say, of new optical designs in addition to the Newtonian design. Here you can see some examples. This is the prime focus. So the mirror, the primary mirror is here, and the focus is inside the telescope. This is the Newtonian design that we saw before. This is the Cassegrain design, where you see there is a hole in the primary mirror, so you can see and you can do your observations from the back here. And this is another case called the Coudet focus telescope with the 2 reflections. Of course, you use glass for this mirror, and you use coating made of silver or aluminum, depending on the applications. And it was a century really very rich of fundamental discoveries, and also it was the century of the birth of the so-called astrophysics, that is, let's say, the evolution of astronomy in the physical context, in the understanding of the physical properties of astronomical objects, and that became possible thanks to spectroscopy. Spectroscopy is really the other fundamental tool, in addition to taking images, to really understand the nature and the physical properties of astronomical objects. And here you can see my personal selection of these main milestones. 1901, discovery of the first asteroid by Piazzi. So understanding that the solar system didn't include only planets, but also many, many minor bodies called asteroids, or also comets. The first solar spectrum by Fraunhofer. The discovery of another planet of Neptune, and the birth of stellar spectroscopy thanks to Donati, Secchi, and also Draper. And this is a drawing of the first solar spectrum. These are Ceres and Neptune. Of course, these are modern images taken with satellites or telescopes. They are not, of course, coming from that period. But there was another revolution in that century, which is even, let's say, it's as important as the invention of the telescopes, so the birth of astronomical data. Because in that period, at the end, in the second half of that century, the photography was invented. It was very soon, very quickly implemented in the astronomical observation. So it became possible for the first time to record the data, images or spectra for the first time, and to have recorded data on an objective medium like photographic plates, where you can do many measurements, you can repeat the measurements, and you are not forced to describe what you see with your eye at the telescope by drawing that as Galileo and many others did. So these are the very first pictures taken with telescopes by Henry Draper. This is the Orion Nebula. That means that you can measure the position, the motion, the size, the amount of flux and light that is present in these images. And this is the first spectrum of a star of Vega, star Vega. You can see we are at the end of that century. And since the topic of this meeting is glass, let me remind you that together with that, of course, also astronomical instrumentation started to become available, and astronomical instrumentation is plenty of optical elements made of glass, so mirror lenses that are needed to then to produce the images or the spectra that you then record with the photographic plates. So it was, let's say, the second half of 19th century was extremely important from that point of view. Then we move quickly to the 20th century, which is another revolutionary century, that where, let's say, the refracting telescopes with lenses were completely abandoned, and the focus was only on increasing the size of reflecting telescopes. And this is a short history of the main telescopes that became available. The very famous Mount Wilson, 2.5 meter diameter, which is this one. The primary mirror is there. The very famous Mount Palomar, 5 meter. The very first optical telescope in space, the Hubble Space Telescope, 2.4 meter, and then the advent of the giant telescopes of the 8-10 meter size. The very first were the Keck telescopes, 1993, and then followed very soon by the European, let's say, reaction to that with 4 8.2 meter telescopes in Chile. I will show you some pictures later. And here there was this major problem. So let's take as an example the 5 meter mirror of Mount Palomar, okay, which is this mirror. The thickness of this mirror, which is a monolithic mirror, is about 80 centimeter for a total weight of about 20 tons. So it is a super heavyweight mirror that required a super heavyweight structure with extremely high accuracy, mechanical accuracy. And that mirror was simply needed to, let's say, allow the coating of 1 gram of aluminum with a thickness of 100 nanometers. So the question was, how can we improve on that, and how can we increase the size of the mirrors without increasing too much the weight, because otherwise that would have been really a showstopper in the evolution of this kind of technology. And there are three ways out to overcome this problem. One is to build a thin meniscus mirror that are basically made in this way. So you start from a piece of glass that you position onto a structure that has the same curvature of the lens that you want to build, or the mirror that you want to build. You heat the glass, and the glass takes the shape of the structure that you have, let's say, produced in advance to have the curvature and the accuracy that you want for your application. And this was a technique already used by ancient Greeks. This is a cup, a glass cup. This is from the National Museum in Athens, third century before Christ. So you can see here the technique. It is exactly what astronomers did for the VLT telescope, actually. And what you can see here is the 8.2 meter mirror with a hole here that was produced in this way, with a thickness which is only 17 centimeters compared to the 80 centimeters of the 5 meter Mount Palomar telescope. Of course, that required a new technique to keep the mirror with the correct shape and accuracy that you need for your observation. And that was also the invention and the advent of the so-called active optics. So you have the mirror here, and you have a very large number of actuators or pistons, let's say, below the mirror that keeps in real time continuously the shape of the mirror as you want. So this was one possibility. The second possibility was to abandon the monolithic mirror and to build the so-called segmented mirrors. And this was an invention by Guido Hord-Arturo in the 50s in the Specola Tower, which is here at number 33 of Via Zamboni. Okay, where you don't have a monolithic mirror, but you have a segmented mirror with hexagons that are, of course, positioned with a curvature that is what you need for your optical design. And this design was extremely successful and implemented in many optical telescopes, such as the Keck 10-meter telescope. So this is a real example. And also the famous James Webb telescope that is right now in orbit is using this kind of design. And the third way out to reduce the weight of giant mirrors is the so-called honeycomb mirror, where you have again a monolithic mirror, but built and on a structure that has this shape. Let me show you a movie that, if it works, where you can see the casting of the 8.4 mirror for the Large Binocular Telescope in the US. And you can see that the fused glass is above this structure that allows not to use completely all the structure full of glass, but to reduce the weight significantly. Here you cannot see that, but the structure is rotating because we want a parabolic curvature on the surface of the mirror. Okay, so the main materials, the topic again here is glass, are Zero-Dur or Pyrex or LK5, which are, let's say, different variations of glass with extremely low thermal expansion coefficient. And I like very much also this kind of picture where you can see different mirrors for the many telescopes, the largest telescopes that are available today. So, for example, this is the LBT, the VLT, the two Keck telescopes, and this is in comparison the Yerkes refractor telescope, which is 1 meter diameter. So you can compare on the same scale the size of these mirrors, and also compare them to a tennis court or a basketball court, just to have a concrete reference. These telescopes are placed in the best sites for astronomical observation. So, for example, the ESO VLTs are on the top of this mountain in Paranal in Chilean Andes. These are the two Keck telescopes and other observatories on the top of the volcano Mauna Kea in Hawaii. And this is the LBT on the top of Mount Graham in Arizona. But you can build gigantic telescopes, but you have to face this problem, which is the problem of image degradation due to the atmosphere, the atmospheric turbulence, which is due to the fact that you have a star, let's say, that above the atmosphere, the light from that star crosses our atmosphere, which is made of different layers with different chemical composition, different physical condition, different optical refraction indices. And then that means that the wave front coming from that star, which is in principle a plane and parallel, is distorted through this travel to the ground-based observatory. So if you start from an image like that of that star, on the ground, the image is distorted in this way. So it becomes larger, irregular, and this is what you don't want to have, of course. So you want to have a fully detailed and in focus images. So what is the solution to this problem? There are two solutions. One is to send the telescope to space, and that was done, for example, with HST or with James Webb. And to show you the power of having a space telescope is in this image. This is a comparison between an image of a galaxy observed from the ground with an 8-meter telescope and the same galaxy observed with a 2.4-meter telescope, so much smaller, but the angular resolution and the details and the depth of the image are not comparable to that image. Of course, there is also another solution, which is called adaptive optics, AO, which is a very modern way to try to mitigate or reduce as much as possible the atmospheric turbulence. And that, let's say, the heart of the AO is a deformable mirror that can be deformed in real time with let's say, a sampling of 1,000 times per second that can correct in real time the wavefront, which is the distorted wavefront coming from the star that you can see is what we get without AO. So this system is magically capable to reconstruct the image fully or almost fully corrected for the atmospheric turbulence. And let me show you two images which are really spectacular in my point of view. This is a planet Neptune from the ground without AO. So you don't see basically anything, any details here. And with AO, you can see the detail here. And this is another image. This is the galactic center, which is full of stars with a very high density of stars. It is the place where also the supermassive black hole is located, but you don't see that because it is a supermassive black hole. This is without AO, and this is with AO. So you can see that we see much better individual stars. We see many more stars, and of course, it's like putting eyeglasses to a telescope. And that this is my personal selection of the main scientific milestones in the 20th century. I know it's a very long, not very pleasant slide to be shown in a meeting like that, but I think this is really extremely important to show the evolution of astrophysics and cosmology in this century. I don't want to go through that in detail, but let me just remind you that, for example, the HR diagram was extremely important and essential to understand the stellar evolution, Cepheid stars to measure distances in the universe. The first gravitational lensing observation during a solar eclipse by Eddington, the very famous Eddington experiment, also proving the predictions of general relativity of Einstein. Understanding also that Andromeda and other galaxies were external to other galaxies, and also understanding that the universe was much larger than it was thought before 1923. The expansion of the universe, the very famous Hubble law, the discovery of dark matter by Zwicky in 1933, and this I let's say underline this dark matter in this way because this is also another application of glass and telescopes. So through a telescope, we were capable to understand that there is a large amount of matter that we don't see, but that we can indirectly infer thanks to the observation of light passing through glasses and collected by a telescope. So it's really fantastic in my view. Quasar redshifts, strong gravitational lensing, again, a prediction from general relativity, the discovery of the very famous double quasar, again, dark matter, but in disk galaxies by Vera Rubin and others in the, let's say, since 1940, 1950, the first exoplanet, Nobel Prize, the first supermassive black hole in galactic center, Nobel Prize, accelerated expansion of the universe, Nobel Prize, and also the combination, the synergy of Hubble Space Telescope and the Keck and VLT telescope to study with observations galaxy evolution. And that comes to the end of my presentation. This is pretty obvious, but I like every time I have this kind of presentation, I like to remind that telescopes are really time machines, and this is the beauty of astrophysics, because we can really see in the past as the universe was in the past. So, and also when you observe the sun that you observe is not the sun of that time, it is the sun of 8 minutes ago. So you can use the same argument, and then you can observe how galaxies looked like in the universe more than 13 billion years ago. So that means that in astrophysics, we pay the price that we don't have, let's say, experiments in the lab, but we can see the real evolution of the universe, really studying and seeing the universe as it was in the past. So that is not possible in other scientific areas. And this is, let's say, the father of the universe evolution, which is shown here in this picture, which is the case of Edwin Hubble. So let's say something about the future, just a couple of slides. This is not a real picture. This is not a photograph. This is a simulation of the so-called ESO extremely large telescope. First light of this telescope is expected in 2028 or maybe a bit more. Why extremely large? Because the size of the mirror will be 39 meters. So today the largest telescope is 10 meters. And the segmented design will be used with about 800 segments, hexagonal segment, each 5 centimeters thick, so really very thin, that need to be put together and controlled by a very sophisticated system that will keep everything in place with the right curvature and the right accuracy. And I like to conclude with this slide, which shows in parallel the increase of the size of the objective of the telescopes from Galileo to ELTs across centuries. And this evolution is tightly connected to the evolution of our knowledge of the universe from the solar system and different scales to the understanding of our galaxy, and also the understanding of the role, let's say, and the nature of our galaxy when we include our galaxy in what we call the universe, so a system made of matter and energy, where thousands of billions of galaxies like our galaxy are located, and where a lot of matter is not visible directly. It is visible indirectly, but also thanks to telescopes. So what you see here is the so-called cosmic web, where you see the light coming from galaxies, but galaxies are included in a structure that is called the cosmic web, that is made mostly by dark matter, which is about 85% of the total matter of the universe. So there is a very strong connection between this evolution, glass and telescopes, and the evolution of our knowledge of the cosmos and the universe. Thank you very much.
For the beautiful talk, but poor Lemaitre. I mean, the expansion of the universe was discovered by Lemaitre before happened.
No, let's say, Hubble did the observations that were, let's say, connected to the theoretical foundations of that possibility of the expansion of the universe by Friedman and Lemaitre. So
Lemaitre had also the data.
Yes,
he made
yes.
a plot of the distance, the velocity,
That is fully
versus the distance.
No,
He
no.
discovered the fact.
It's fully correct, but who did the observations was Hubble, not Lemaitre. That was my point. Okay.
Okay, and questions?
Thank you for this very nice talk. I have a question. The space telescopes and the adaptive mirror telescopes, how do they compete? I mean, which technique is going to be in the future the most performing? Because the results are spectacular. So,
yes.
What is the road that will be pursued?
Let's say that they are complementary. So a telescope as big as the ELT, 39-meter size in space, is beyond our possibilities for the moment. So they are complementary, and they are also complementary in the spectral range where they work. So, for example, James Webb in space is working in the far infrared, mid-infrared, whereas other telescopes from the ground can work only in the optical and near infrared spectral range. So they are really complementary to each other.
Other.
How do radio waves?
Wait for microphone.
How do radio waves fit into the story?
Oh, yes. Radio waves fit very well into the story, but the topic of this meeting is glass and telescopes. So there is not much glass in radio telescopes. They are antennas, but of course, I mean, modern astrophysics is called multi-wavelength astrophysics. So we need different telescopes working with different techniques to fully cover the full, the complete electromagnetic spectrum. So they are extremely important, and that require another talk probably.
Other questions? If not, we thank the speaker again. Now will Wilfred Planck from this glass for photonics. We lost the speaker.
Okay, so thank you, Mr. Chairman. And first of all, I would like to thank the organizer for giving me the opportunity to give this talk. Well, actually, it's a great pleasure to be here, and it's a great day. I learned a lot of things dealing with the glass materials. But there is one thing that I did not expect to learn because we are at the Academy of Science. So for sure, as they host us, I can imagine that they enjoy the glass material, but I'm not sure about their feeling about the silicate. Actually, you see the stone. Stone is silicate, and it's quite dangerous to be here, I guess. So maybe they use it. So we were aware about the sword of Damocles, but now we know that there is too the stone of Polypheme, the Cyclope. So take care with the stone, maybe with the silicate. Okay, so the idea of this talk is to discuss about glass photonics Of course, don't worry, I will not speak about all glass photonics because I have just 30 minutes, so I will just make some focus, some part, and I want to make a mix between the applications and the historical point of view from the glass photonics. And the idea is just to show you how, even if we are more involved, when you speak about glass photonics, what you have in mind is the application. But even if you are interested in application, and while you are doing glass photonics, you are still interested to learn something about the glass. And even if we want to promote new application, then we have to learn about the glass for sure. Okay, so first, I will start with the basic consideration on the glass and the link between glass and optics. So it has been already said that if you consider the etymology of the word, so in French or in Italian, it's ver or vetro, so it's coming from the Latin word vitrum, which is related to the fact that this material is transparent and glitters, while the word glass comes from glaceum, which is more connected to the fact that this is connected to the amber and the color aspect of the glass. So of course, as it has been already said, that so the glass and optic are strongly entangled, to say a word which is good related to the last Nobel Prize, and it is of course first transparent material prepared by the humanity. So that's why we are so it seems to be so magic for this glass. So just 2 points. If you consider the word transparent, so first of all, you have to keep in mind that it's transparent for our eyes. Actually, we say that it's transparent so that the light is going through to the glass, but this is transparent actually for our eye. Okay, so if we were another animal, if we were more sensitive to another wavelength, let's say to the 2 micron region, then this carafe or this bottle, which seems to be very transparent, then it will look like an obsidian. And when you look, when the first time you look at the obsidian, you don't think that it is a glass because it is black. And so, okay, so this is about the word transparent. And the other point is that as it is transparent, so it means that this glass is not invisible. Okay, so it means that there is a link with the light. The light is just passing through the glass, but there is an interaction with the glass. And of course, as you can see, for instance, here and it has been already said that the glass is it glitters and the light can interact with the glass. And this, so we had this meeting, this presentation this morning. So I want to thank Rosa Barovier Mentasti. I'm correct with that name, sorry. So when she presented this painting, actually, you see that then the painter, so they try to paint the invisible, to paint the glass. But if you look carefully the glass, so just imagine that when the light is passing through the glass, then the object behind should be deformed. The picture that we should see should be deformed. Or here, you see that there is no deformation. So they represent the glass as a invisible material, or almost invisible, but not really transparent. So they were not aware about the deformation induced by the glass, actually. So when you consider light and optics, the first optical phenomena that we know, it's about the refraction. So the first formula of the refractive or the reflection was proposed by Snell and Descartes. So of course, you know this law. This law is important because it's the first time that the geometrical optics became an exact science. We are able to predict if you know the incident angle, so then you are able to determine the angle of the refractive ray. So this, as it has been said, that so this formula was written first in 1625. So when Galileo first developed the telescope, actually, he was not aware about this law. And to give you an idea of what was the knowledge about the light at that time, so the first measurement of speed of light was 50 years later. Okay, so this is where we are in 1625. So here it's a picture extracted from La Dioptrique, which was written by René Descartes. So you see that there is the incident ray, which is refracted when it's going from air to water. But if you look at carefully the angle of this ray, you see that it's wrong. There is a high angle, here is a higher angle. So the exact path should be, the exact path for the ray should be like that. And in this case, he represented the refracted ray in water in this direction. And this is not a mistake, actually. He assumed this and say that it's okay because the light is traveling faster in water or in glass than in air. Because when the light is passing through at the interface, there are some molecules which act like wheels. So they accelerate actually when the light is passing through this interface. The molecules are rotating and then it accelerates the light. And depending on the rotation speed of these wheels, actually, so then you can have violet or red depending on this rotation of this speed. So for him, the light was faster in the water than in red. So even if he has the right equation, actually he did not understand anything about the nature of the light. So there is also one important step for the glass and optics. Of course, this is the famous Newton. When he was on, so he was only 24 years old. Just think about so it's the same year that he discovered the law of gravity. Okay, so like a PhD, actually, every PhD at the same age do the same discovery. We know, we are aware about that. And it's nice to remember that this is during the lockdown period for him already, due to the Great Plague in London. So here, this is the usual picture that we present with Newton thinking in front of the prism and the white light and the rainbow behind this prism. So actually, this is not a novelty. This dispersion of color has been already observed 6 or 7 centuries before. So this is not the main novelty. The main novelty it's about the composition of the light. At the time, the way that we are thinking about the origin of the color is due to Aristotle, and it was almost 20 centuries back. It was from 20 centuries back, and so we have the white light, which is very bright, and when the light is interacting with any material, so then the brightness so the light is degrading, and then the brightness is going down. So from the white to the yellow, red, and down to the black. So this is how we can explain the origin of the color. And actually, if you think about what is doing the light inside the prism, so the light is going into the prism, and it crosses several thickness. So the prism has a given shape, so there is several thickness. So we can imagine that, okay, when the light is crossing the top of the prism, thickness is quite thin, and at the bottom, okay, it's thicker. So that could make sense with the fact that the light is degrading depending on the length crossed in the prism. So based on this hypothesis, so we can explain even if the order or the sort of the order of the color is not the right one, but you could explain it. And the great novelty or what understood Newton is that now if you take a second prism, so then you observe that the red, so now if you imagine that it's only due to the thickness of the prism, which is crossed, so then you should observe that, okay, I start with a red, and if now I go with the red light across different thickness of the prism, so then I should observe different color. But actually, you know that if you take the red light, so whatever the thickness of the prism, you will continue to observe the red. And then this is how he concluded that, okay, so this the white light is not contains all the color. Quite interesting to remind you that this is the first sketch. So then in this case, you see that there is only 5 holes because at the beginning he observed 5 colors in the rainbow. It's only 5 years later that he decided to say, no, actually there are 7 colors because there are 7 days, and for religious consideration, he preferred 7 colors than the 5 color. And notice that the optics where he published the explanation of this color, the optics book was published only almost 40 years later, because when he presented first this consideration about the color, the origin of the color of the light, everybody say no, it's wrong, we can't accept this. So he has to wait that Hooke and all his colleagues died actually to publish his book. Yes, so actually when he observed this, actually it was a faint light that he was able to observe on the wall. So it looks like a ghost, and he called it a spectrum. And we continue to use this word, emission spectrum, absorption spectrum, or this thing. Okay, so now if we are going forward with the optics and light and glass, so as it has been presented in a previous talk, of course we can shape the glass, and then we can have refractive optics, and then the telescope and microscope. So in the same century they were both developed. So it's nice to observe how the same material, the glass, can allow to observe different scale, of course. Here for different parts, and I'm still amazed by the artistic skills of this scientist. And just to finish with the foundation, I can't forget to mention Zeiss, Haber, and Schott, because they are up to before them, all the glass were prepared, and if you want to obtain a given refractive index, for instance, so then it was just try and error. So they prepared, you can prepare different composition, and after you measure the refractive index. And actually, they use this additive model. So then you know that then you are able to predict the final result of the refractive index. You know that you need to add X% of silica, X% of lanthanum, and X% of barium, for instance, and then you should be able to reach this refractive index value. And this allows to prepare a huge number of glass, of different glass, for the refractive index, thermal optics coefficient, and so on. Okay, so now if we are reaching the photonics, so it's more recent. So let's say that the previous consideration were mainly dealing with optics. Now the photonics is this evolution. So it started to be mentioned in the 40s, 50s, or 60s. And it's the science and the technology which allow to generate, manipulate, and detect the light. So I will just illustrate some of this aspect of generating, controlling, and detecting the photon. So a good way, which is traditionally used to generate the light, for instance, it's that we are doping the glass with the reverse ion. So here is the map of the world, or the periodic table. It's up to you. So all the reverse ion correspond to these lanthanide elements, and they correspond to the filling of the 4F shells. And these are the common elements which are used in any lighting system, for instance. Here you have so if we consider the energy level diagram, because this is what we are interested in when we are dealing with the optical properties of this reverse ion. So here you have the splitting due to the interaction between the nucleus and the electron and so on. So it's just the splitting that we observe in the free ion. And as these reverse ions are embedded into a glass or a crystal, so then you have an additional splitting, which is related to this is what we call the crystal field. So then we have all the optical transition. So it could be an absorption or emission related to the transition between all this level. So here it's for the 4F levels. We have choose the 5D levels. So let me conclude with the 4F. So the 4F level is here. So here you have an example of emission spectra. So as all so each peak corresponds to one of these transitions. So in the crystal, the structure is well organized. In the case of the glass, we have disordered. So around each reverse ion, the environment is is slightly different, meaning that this energy level can slightly shift, and the oscillator strength the transition between this energy can slightly change too. So we are moving from this peak emission to a broadband emission. And under this broad emission band, you have all these peaks which are larger, and this is what we call the inhomogeneous broadening. So you see that in this case, so the shape of this emission is changing, but the central wavelength is always the same. In the case of the, so it is for the 4F transition, then you have the 4F 5D, which is the higher excited level. In this case, the 5D electrons are very sensitive to their environment. And then if you adopt the rare earth ion in fluoride or in nitride or silicate, so then you will have a change not only on the bandwidth, the shape of this, but also of the emissions. For instance, cerium can emit in the violet or in the blue in the fluoride, while it can turn to red in nitride. So there is a very big change of this emission wavelengths depending on this on the composition. So to illustrate one application of this glass doped with rare earth ion, so one of the well-known application is the glass laser. So the first glass laser was proposed in 1961 by Schneider. It was a silicate glass which was doped with neodymium. So why? So of course we know that there are many crystal laser, which is commonly used. So why we are interested in glass laser or glass amplifier? Because there are different interests. So among the main advantage that thanks to the glass, we are able to produce a large amount of glass laser with a good doping homogeneity. The stability is very good, and we can avoid the beam distortion. Of course, there are some disadvantages to use compared to crystal to use the glass. So the thermal conductivity is much lower. So it means that if you want to use glass for high power, and this is what I will illustrate in the next slide. So then you need to manage all the thermal properties of the system. And the emission band is different. In particular, the absorption cross section is lower in glass compared to laser, meaning that you can be less efficient with glass than it is with crystal. But there are of course, great interest to use the glass laser. So it could be illustrated by this application, which is the high energy laser facility, such as the INFN, National Ignition Facility, or Laser Megajoule in France. So have in mind that they need to amplify and to reach this megajoule energy. So they need to use 3,000 glass plate or even 4,500 glass plates for the laser megajoule. So of course, which represent 300 tons of materials. So just imagine that if you had to produce this with a crystal, it's just impossible. So then in this case, it's very useful to use this case of glass. So in this case, it's phosphate glass, and you see that the size of these plates, it's a very it's 40 or so centimeter length, and it's very large volume of glass. Each one plate is already a larger amount of glass actually. Another application is the glass scintillator. So it's more related to the way how we can detect light. So in this case, it's not the visible light. It's more the high energy radiation, I would say. So neutron, X-ray, UV, and all this high energy radiation. So here the advantage is that it's the same as for glass lasers, is that we can produce a large amount of glass. We can reshape it in different form, and the transparency is also very high for this one. And you may have better chemical durability than certain crystal scintillator. The one of the drawback by using glass scintillator is that you may have a lot of defects inside the glass. So then in this case, So as the scintillator, so you convert the ionizing radiation into electron pairs. So if you have defects, so then the electron and or hole can be trapped, which will degrade the quantum yield of this scintillator glass. And usually for this scintillator glass, we prefer to use 4F5D transition. So one of common element could be cerium or terbium. The idea is to have a very fast decay curve. But John, who is here, is the expert in glass scintillator, so I don't want to say much about that. And if you have any question, please ask to John. Okay, so now a last example where we use the rare earth ion is on the solar cell concentrator. So of course, as you know, in the context of this climate crisis, we are more and more involved in how we can use natural energies. Of course, this solar radiation is interesting to be converted. So here is in blue, you have the solar emission, and in red, it corresponds to the silicon, crystalline silicon absorption. So you see that there is an overlap, but the overlap, of course, is not 100% efficient. In particular, there is no overlap for the longer wavelengths, and even for the shorter wavelengths, the overlap is not at the maximum. So the idea is to convert the high energy, the low energy photon into 1 micron photon, and to convert this photon, also the visible photon, to cut and to have the 1 micron emission. So we can use two mechanisms. So the down conversion. So in this case, with the visible or let's say high energy photon, you can excite the rare earth ion, which can then transfer its energy to ytterbium, which emit at 1 micrometer. So this is one of the process. So the down conversion, so it's efficient for this kind of photon to convert down to 1 micrometer. This process depends on the distance between the rare earth ion. So we have to change it's very sensitive to the concentrations because it's a way to control the distance between the rare earth ion. Another way to control the distance between ions is to use glass ceramics, because in this case, even if the average concentration could be quite low, as the rare earth ions are all inside the nanocrystal, so then you have a high concentration in the crystal, and then you can emphasize this process. The other process, which is the hop conversion, so meaning that we want to convert this low energy photon into 1 micron. So in this case, we can use rare earth ion because we have this process. So the first photon we are allowed to excite and the first energy excited state, and the second photon can be absorbed to reach the second excited state. Then it can emit at 1 micron meter. So this phenomena is the excited state absorption, or it could be through energy transfer between two rare earth ions. The point is that in this case, this mechanism depends strongly on the power of the laser. So you need a high power. So it's difficult to reach for the case of the solar cell concentrator. Okay, so now I want to spend some time on the optical fibers. Just want to check time. Okay, so because I had the pleasure to learn that optical fiber is one of the 7th wonders, so it's very nice to learn about that. And actually, if you look at this picture, so you see that here optical fiber is present. When we look at the website of the International Year of Glass, optical fiber is also on the website. So yes, as it has been already said, so optical fiber is very common glass, common application, which is presented to show how glass can be a very high technology product. So here's a picture just to remind you the size, typical size of optical fiber. So it's 125 micrometer if you consider the optical fiber for the telecommunication with the core 8 or 10 micrometer. So the light is only guided inside the core, and it's compared with the hair here. So just to remind you that it's very the size are quite similar. I just want to say a few words about the history, the development, how we reached this optical fiber, why we reached to this optical fiber. Of course, as you know, it's not a H2020 program. We say that, okay, we put 1 million euros to promote this glass to have a new telecommunication system. The history of optical fiber is older than that. And actually, it started by like serendipity, I would say, because it started with Félix Savart so almost 200 years ago. He did not discover the shower, but it's just discover that. So if you look at I don't know if you can see it on this picture. So, but it's about it's about the behavior of the light. So first you have the jet. So the jet first is homogeneous, and after a given length, so then you have instability, and so this continuous jet is a droplet transformed into a droplet. So this instability is known as the plateau relay instability. And actually, Jean-Daniel Colladon, who is a physicist in Geneva, want to reproduce this experiment to present this discovery to his student. And so he prepared this fountain, and by lighting this fountain, because inside the amphitheater the lighting is not very, very good. So finally, he observed that the light is trapped inside the water jet, and for him it was a discovery, and say, well, it's a very wonderful experience, and he decided. So this is the light fountain, and he decided to send a paper to the Academy of Science in France in 1842. And the secretary of the Academy of Science was aware that Jacques Babinet, a French physicist, has made almost the same observation, but not in water, but in a glass rod. And when you took the glass rod and you bend the glass rod, so then you observe that, okay, the light is trapped, is guided inside this glass rod, whatever the bending. And for him, it was not very new phenomena, because you can explain it with the law of the Snell-Descartes formula, so which was 20 years old. So he was not very pushy to publish this paper, but when the secretary of the Academy of Science asks you to publish a paper, usually you say, okay, I will do it. But he had in mind that we can use it for at least 2 applications. So the first one is, so it could be a way to remote the light source for dentistry, and to illuminate the microscopy preparation too. And actually, it has been used for that. Then the next step for the development of the optical fiber, of course, the main application, first great application for the use of optical fiber is the fiberscope. So we are in the 30s, 100 years ago. So the fiberscope is, I think it's very important for the fiber for different reasons. Not only the fact that it is one of the concrete application for medicine, for us. It's also because in a fiberscope, you have a lot of fiber, okay? And when the fiber, so the idea is that you can able to transport image because of all this fiber. Each fiber acts like a pixel. And of course, when in fiberscope, you have a lot of fiber, then the fiber can touch each other. And when the fiber can touch each other, so the light which is in one fiber can move to the other fiber. And of course, you imagine that if you have your image at the first image, all along the fiberscope, if all the fiber are touching, the final image will be completely blurred. So they have to find a way to avoid this blurring if we want to improve the quality of the fiberscope. And this is how they came to the idea that, okay, we have to develop the core clad approach of the fiber. So we still have the core where the light will propagate, and we have to put something around to avoid that, even if fiber are touching. So it doesn't matter because the core we will not touch each other. So this is how. So it's 20 years later, in the 50s, that this idea came to develop the core clad fiber. And the next step was, okay, it's always the same. You have the idea, but what will be the clad? And one of the first idea was to put alumina or something metallic clad, but it was not very successful. And then a student, so Curtis, proposed the idea to put another glass around this glass rod for the core. And he used actually the techniques that we can call we call the rod in tube technique. So you have the glass rod, which is embedded inside a glass tube. So of course, the idea is that the clad must have a lower refractive. So this glass must have a lower refractive index than the one of the core. And you draw it at high temperature because we are with, so in the case of silica, this temperature, typical temperature for the drawing step is about 2000 degrees Celsius. This is one of the inconvenience when you use silica. You need a very high temperature, or with silicate it can be lower. So we transform. This is what we call the preform, and this preform is drawn into an optical fiber. And this is still a process that we are continue to use to prepare the fibers. So there are different ways to prepare the preform, but the way to obtain the final fiber is still to prepare the preform and draw it into an optical fiber. So for all these reasons, fiberscope is an important step for the development of optical fiber. Now the next point is that at that time the transparency of the glass was not that good. It's okay. You can transport light over 20 meters typically, but after 20 meters, typical loss is you only have 1% of the remaining light. So in the 66, we had a seminal work paper published by Kao and Hockham. In this paper, he said that, so he questioned the origin of this transparency. Is it intrinsic or extrinsic problem? Is it due to the fact that silica is pure or not pure enough? And his conclusion is that, okay, the transparency is mainly related to the fact that inside silica, we have a lot of impurity, in particular iron. And if we are able to remove this impurity, so then we can have a much more transparent glass. And if we reach the value of 20 dB per kilometer, so the value at that time was 10,000 dB per kilometer. So if we are able to reach the value of 20 dB per kilometer, meaning that we are able not only to reach 20 meters, but 1 kilometer. So then we can start to imagine to develop telecommunication based on the optical fiber. And so he published this paper in 66. So he was awarded with the Nobel Prize in 2009 for this paper. And only 4 years after this paper, so a group in Corning was able to prepare this first low loss, let's say, optical fiber. And you see that in the 70s, it was a very impressive improvement because we were able to reach 1 kilometer up to 100 kilometers. So the transparency made a giant step in 10 years. So now if you consider the value now, so typical value at the end of the 70s was 0.2 dB per kilometer. Now typical value we can find 0.15 dB per kilometer. So of course the improvement is less than the one we had in the 70s, but why there is still an interest to continue to improve this transparency? Because as you can see, we are able to propagate light over 100 or 200 kilometers, let's say. But of course, compared to the length of a transatlantic line, you need 6,000 kilometers. So it means that you need to use to re-amplify the light. And of course, in the cable, telecommunication cable, the main issue will come from the amplifier. So if you are able to promote to have a better transparency, so then you will have less amplifier, and it would be probably safer for the cable. Okay, so the way they obtained this high transparency is because previously it was made by melting quartz or glass or sand. So here, this pure glass was obtained by chemical vapor approach. So you see, so you have the oxygen going through the silicon tetrachloride, which is a liquid one, and at the output you have the gas of silicon tetrachloride plus oxygen, and with burner you have the reaction oxidation of this one, and you can produce silica soot. And this is a way to obtain very pure silica, because, so first of all, we are able to prepare very pure silicon tetrachloride, and the vapor pressure of the silicon tetrachloride is much, much higher than other any impurities. In particular, if you consider iron, so even if there is iron inside the silicon tetrachloride, you see that the vapor pressure is about 0.5, let's say, atmosphere. It's 10 to the minus 12 for iron. So even if there is iron inside the silicon tetrachloride liquid, so the vapor pressure is so low that it will not evaporate. So now there are of course many applications for the telecommunication, laser amplifiers, sensors, and I will go fast up just to mention why we need to improve our knowledge on the optical fiber and the glass. So one of the new optical fiber that we try to promote is based on the presence of nanoparticles inside the core of the glass. The idea is that if the rarest ions are inside this nanoparticles, so then they will see an environment, a chemical environment, which is different from the silica. So we could combine both the advantage of silica, but with an environment which is not the one of silica. So we may have new luminescent property. So the idea is that we need to have some, if we want to have a small or laser amplifier, of course, we need that the light is able to propagating and leaving the fiber. So for this, it has been suggested that the particles must be very small to avoid light scattering. And actually, so we are able to prepare that kind of particle by using the phase separation mechanism, by adding, for instance, magnesium or any alkaline earth ion or lanthanum ion. So here we see the nanoparticles inside the particles inside the preform. And the point is that based on this doxa, what we have observed is that here is the variation. So we are able to measure the composition of the nanoparticles with the atom probe tomography, and you see that the change of depending on the radius of the particles, we have a change of their composition, meaning that the smallest particles, which are the one we're seeking for the laser to avoid the light scattering, actually, the composition of these small nanoparticles is very close to the one of the matrix, so meaning that they are not of interest for the luminescence property. So we have to find the balance between the size so small size to avoid light scattering, but they should be large enough to have modification of their composition. And this has some application, and as they are changing, so this is a quotation that Maurizio enjoyed to use generally, that we can conclude, in this case, that the smaller objects in nature are not just a scale replica of similar high object, and because the composition is changing and is depending on the size. Another point, just quickly, is that when you have the fiber, we have spherical nanoparticle inside the preform. When we draw the fiber, actually the glass is flowing and the nanoparticles is elongating. And it's so you see the elongation, and there are, I don't know if you can see it, but there are also the breakup of these elongated particles. And so we can explain it with the fluid mechanics. But it's nice to see that actually we use the same phenomena as the one we started actually the origin of the optical fiber and the light guiding. I will go through. So we can use now, it's time to conclude. So we can use through this kind of optical nanoparticles, because there is a huge amount of backscattered light. So we can use this kind of backscattered light to have some sensors, but I go fast. Actually, I have a lot of slides, because as I was among the last speaker, I was thought that most of the first slides were already presented by the previous speakers. So that's why I have all these slides, sorry. And so there is no conclusion. No, just the sustainability, because this is always the question. So about the sustainability, it is expected that optical fiber will help to decrease the emission of CO2. And I just only found one value for what is the emission of CO2 for it's 8 kilo CO2 per kilometer of optical fiber. Which means that if you consider a transatlantic cable, then it should correspond to about 50 tons of CO2. And to compare the equivalent, so each French, we emit 10 tons of CO2. So I don't know if it's a lot or not, but this is here are some value. And there is no conclusion, but because the story is still going on. And just I want to emphasize 4 points for the next trends. Of course, for the next step for the glass photonics, we will have so the 3D printing will be very useful to have a completely original geometry for all the fiber or any waveguide or anything else. So we will hear a lot of, there is a great expectation with the 3D printing. Artificial intelligence will also be involved in for the next photonics. There is no doubt for that. And one point which is interesting, of course, flexible photonics. So Maurizio, Giancarlo, you worked hard on that, and I'm sure that this has to be pushed. You should continue to work on this. Maybe not you, but younger one would be. And the last is that other glass are prepared on Earth, but there is now some glass which are prepared in space, in particular fluoride, because you know that fluoride is expected to be very transparent. So the theoretical limit of optical fiber made with fluoride should be 10 times more. They should be 10 times more transparent than the silica, but when they are prepared, they are on Earth, they are 10 times lower transparent. So so now they try to prepare optical fiber, so fluoride optical fiber in space, and you see that the transparency of this optical fiber, fluoride optical fiber prepared in space, are close to the theoretical limit, but they can prepare only 500 meters of fiber. So okay, let's see. But now we have to understand why they are more transparent, because when you consider the material aspect, there is no gravity, no space-time gravity, and we don't consider this for the development of the fluoride. So okay, why it is more transparent? It's an open question. Okay, so thank you very much for your attention, and if you have any question.
Thank you very much for that. Very informative.
We were waiting for the microphone.
Thank you. Actually, a curiosity with regard to the last slide you showed us about the sustainability, not this one, actually, just before that one. A curiosity about the end of life. How long is the life, the lifetime of an optical fiber? And after that, can they be reused or recycled? Well.
Okay, so it's hard to answer to this question for one reason, is that so the optical fibers, if you just consider the optical fiber, the glass optical fiber, the glass can be used for a long time. But the point is that you use it's in the cable. Okay, so the lifetime of a ocean cable is it's about 25 years usually. All right. Now, are we able to recycle it? I think from what I know, they are still on the ocean. So for the moment, they don't try to recover this optical fiber. And you know that it's very small amount of glass. If you want to recycle this glass, if you just consider a transatlantic cable, the volume you need for or the weight of glass you need. Do you have any idea what is the weight of glass you need for a 6,000 kilometer of cable? No, it's 150 kilo. So just a cube of 42 centimeter. So you can try. We can try, but I don't think that if you want to recover the cable, it's not for the glass. It's yeah, probably.
Rita.
Thank you for this very nice talk. Can you tell us more about fabrication in space? I'm curious. How is it done, actually?
Yes. So they brought this. Okay, so actually it's just inside this one. So from what I understood, so you have just a rod, a fluoride rod, because compared to what we do here when we draw fiber on Earth, we use the gravity. But of course, when you are in space, there is no gravity. So you have the rod, and they just pull. Actually, they heat. So the advantage of fluoride too is because you can heat. You doesn't need a very high temperature. So I don't exactly remember the temperature, but maybe it's a few hundred degrees Celsius. It's not that high as for silica. And then they pull the glass. So that's why the length of the total length of the fiber is limited. So for sure here it's very transparent, but a very highly transparent fiber, which is only 500 meters long. There are four or five companies. One is made in space. I think is closely related to NASA, and there are at least 2 or 3 other companies which are promoting this fiber. But the question is why? Because on Earth, what we assume is that the fiber are not transparent because there are some heterogeneity inside, such like or crystallization or something like that. But when you consider the mechanism of formation of this crystallization or phase separation, all this stuff, there is no gravity inside. So where the gravity is acting, I don't know if if someone has the answer to that, but it seems that they are more homogeneous. They are more transparent because they are more homogeneous. But why in low gravity you have more homogeneous material?
But was the same procedure, so without using gravity, tried on Earth?
Sorry?
Here you don't use gravity to produce the fiber.
Yeah, in space, yes.
In
no
space.
gravity, yes.
But so you are pulling it in a way or another. But the same procedure was ever used on the Earth without using gravity.
We can use the same, and in this case, the loss are increasing.
Oh.
So it's only when they are pulled inside the glass rod is prepared on Earth. So it's not due to the higher quality of the glass rod because it's prepared here on Earth. So just when it is pulled that something happened. The magic of glass. Probably.
Okay. Maybe I have a question myself. How long, if you increase, get better transparency, how in the future can you foresee to have that conserve the time coherence and to have phase, entangle, not through satellites transmission, but on fiber? Now they transmit from fiber.
Yeah.
You have entangled over a few thousand kilometers using satellites because you have only to cross the atmosphere. But then in principle, you might do that with fibers if you have not to amplify, of course.
Yeah. Mm-hmm. But I don't know the length. Yeah, but probably the problem is with the length will be the rate too.
But you can have entanglement over which distance now with fibers?
I would say that the transparency is 100 kilometers. I don't know if we can go above this. I don't know actually. The point is that as you have attenuation, so from what I understood is that you will. It's not only a question of distance; it's a question of rate too.
I don't know if it's just a matter not to amplify, or there is something else. that forbids to use fibers.
Satellites, you've got the problem. If they're in a geocentric orbit, it's the time it takes. It's only for close orbits to the Earth that you can use satellites as an alternative. There's a big time delay if you.
Between,
Yeah.
And you think it's the limit.
Okay. But if there are no more questions, we go for a coffee. Thanks, everybody.
Okay. So we are ready to start the last session of this very interesting and very stimulating day with all this nice presentation. And these are going to be also, I expect, very nice. So I give the floor now to Angela Seddon. Thank you. From the University of Nottingham, United Kingdom. So she will speak about chalcogenide, I don't know, glasses and optical fibers for mid-infrared applications. Okay, so thank you very much.
Thank you. I'd like to thank the organisers very much for this absolutely wonderful day. Hello? Hello? Can you hear me at the back? Is that better? Oh, good. I'm so sorry. I just want to thank the organisers. This has been a most fantastic conference. It kind of is likened, I don't know if John remembers, to the Glass and Art in Glass. Do you remember? Held in the Royal Institution. It was Neville Greaves that chaired it. It's the only other time I've seen art and glass and history, everything coming together. So this has been a fantastic day, I think, really enjoyable. So now to the outline of my talk. So an introduction, I'm going to talk about the mid-infrared quite a lot, and then to do some glass science. We've produced a fiber laser that's very long wavelength, and then draw some conclusions. So this is the motto of the Royal Society, which is the oldest scientific society in the world. So I tell this to my PhD students so that they won't believe me about anything, and they'll have to go and read it up for themselves. So I come from the city of Nottingham, which is right in the middle of England. Stick a pin in the middle of England, and it's got an airport if you would like to come and visit. And of course, famous for Robin Hood, not just a Hollywood myth. And I've cracked this joke before this week as well at a conference, but this business about them being outlaws and living in the Sherwood Forest and robbing the rich to give to the poor. So it's the opposite of the British government and what they're doing. And so now into the mid-infrared. And actually, the last speaker did mention this, so I won't spend too long, but Woolsthorpe Manor, which was the childhood home of Sir Isaac Newton, is only half an hour from the University of Nottingham, and it's a National Trust place, so you can go and visit. And he went there in 1666 because of the Great Plague. And of course, we all know now about Great Plagues, and we all went home during the Great Plague. And there's an apple tree in the garden, which is about the 5th generation apple tree of the discovery of gravity. But this experiment is still mocked up in the upstairs bedroom of just taking a shaft of sunlight through the shutters and obtaining a glass prism. Yes, in those days, because we've been talking about Galileo, which was in the era just before Newton. And so dispersing sunlight as a rainbow color for the first time. But the story goes on for me for the infrared. Because around about 1800, and Herschel was also mentioned earlier, but he mocked up the same experiment as Newton, but put a thermometer beyond the red and detected invisible radiation via temperature rise. So this has also been mentioned. But what I do want to mention is that he was the astronomer royal, but his sister Caroline did all the mathematics. So this is an unsung heroine or hero who was female, who perhaps hasn't been recognized as much as she should have been. So also this follows on nicely from the telescope talk, because in fact this is 4.6 billion light years away, this cluster of galaxies. What happened was last Christmas Day, the James Webb Telescope was launched, and the images started coming back in June. The great thing about this is it's mid-infrared light, which can travel further because it's longer wavelength and scattered less by the dust in the universe. And also because it's mid-infrared light, so this is an exoplanet, so a planet not going around our sun, 700 light years away. Because mid-infrared light was being used, therefore carbon dioxide could be detected on this planet by absorption. So basically the James Webb will run from 0.6 microns wavelength to 28.5 microns wavelength. And in that we'll be able to find signs of life, the signature of sort of humans, if you like, within the mid-infrared spectrum. Okay, so this is a deep field image. So I'm an English person, very proud of the Beatles, and you can see the line that I've highlighted there. This is a song called Blackbird, and the two links there. One is to a real blackbird, and one is to a link of Paul McCartney singing this song. But the line that always intrigued me was this: "Into the light of a dark black night." And so, if we look at this beast actually has mid-infrared vision and can go into the light of a dark black night. If you can see here, so let me just find out where the laser is. You can see there's a nostril, an eye, and a pit hole. And in fact, mid-infrared light can be detected here and can be signal processed in just above the visual cortex of the brain. So the pit viper can go into the light of a dark black forest and detect dinner. Okay, but mid-infrared light, so what does it mean? Well, in fact, there is an international standard that dictates what wavelength range that is. And the mid-infrared is 3 to 50 microns. So the near infrared is the telecommunications that we were talking about before, the internet, the fibers around the world. This is perhaps called terahertz these days. And here we are in the electromagnetic spectrum. So this is the little bit we can see with our eyes here. This is the whole of the electromagnetic spectrum. So the near infrared is telecoms, telecommunications, and I'm going to concentrate on mid-infrared. So there are other interesting things about the infrared. This is transmittance over about 1.8 kilometers here at sea length path in the atmosphere, and we actually have atmospheric windows here. So the short wave is here, mid wave here. This is the carbon dioxide that was detected on the planet, and this is a big atmospheric window here as well. So that's another useful thing. So of course at school we're told about heat transfer, conduction, convection, and infrared and radiation. And what I want to think about first of all is when infrared energy is emitted by a molecular species, it's because their vibrational rotational state changes. Well, I'm talking here about black body radiation. So Stefan Boltzmann found empirically that the power radiated by a black body varies with T to the fourth. This is absolute temperature, and that the spectral radiance per unit wavelength peaks with reciprocal wavelength. So what that means is that basically we have mid-infrared radiation here, whose power out is a lot smaller than near-infrared here, and you can see the corresponding temperatures. So if we think about near-infrared, first of all, if we're detecting off Earth, this would be the cooler red stars, but on Earth, it's a good way of detecting burning fuel or furnaces, or indeed in defense, in detecting the exhaust from a plane. And if we're thinking about mid-infrared, so detecting off Earth, the planets in our solar system, what we find is that, in fact, this is a mid-infrared view of the Earth, and it's radiating strongly at 10 microns, which is slap bang in the middle of the mid-infrared. And then, of course, we're used to seeing these thermal cameras. In fact, our peak temperature is 37, which corresponds to a wavelength about 9.3. So we're used to seeing this kind of image of mid-infrared light being given out. But I want to think now about mid-infrared light absorbed. If we shine light onto a molecular species, what will happen? So I'm a chemist, and that's why I feel so honored at being in a physics society, because I've learned all my physics from along the way since doing physical chemistry PhD. The physics has come afterwards. But so what we're used to seeing in chemistry is the vibration of molecules like a workout in a gym. This is water molecules with its various vibrational types, its oscillations. And what we can correlate here is that the Szigeti equation just talks about this as an oscillator. And so the frequency of oscillation actually depends upon the strength of the chemical bond involved, and also the reduced mass of the two little balls on either end of the chemical bond. And so this will dictate the frequency of interaction with, electromagnetic radiation. And if we have mid-infrared frequencies, then we can get resonance between these two. So we can shine mid-infrared light and excite molecular vibration to greater amplitude at the same frequency, of course. And of course, it's quantized. I was speaking to somebody during the tea break just then, and they said, everything's quantized, the gravitational waves and everything. Okay, so what we have here is an asymmetric well, and we saw one of these with the person who was talking about the silica, building the silica system to measure gravitational waves. And here's the potential energy well of a chemical bond. It's asymmetric because of this steeply rising repulsion here as the internuclear distance becomes smaller. And so this 0 point energy is still present at 0 Kelvin, but this first transition here is mid-infrared. In fact, if you shine in 2 photons, it's equivalent to near-infrared absorption. But actually, the extinction coefficient, which means how powerful the absorption is 100,000 times weaker in the near-infrared than in the mid-infrared. So the mid-infrared is just opening up at the moment. It's very new. It's an emerging field, simply because in the past, the sources have been very weak in the mid-infrared, a bit like candlelight. So the black body sources are equivalent to candlelight of the 17th century or something. And we're just beginning to get more powerful sources in the mid-infrared. And my work has been to try and develop fiber optics to actually guide that light around or even produce that light. So if we take one of these black bodies and we heat it, so this can be a silicon carbide bar, it's heated, it gives off mid-infrared light, and we can detect it. And as you saw, there's some windows in the atmosphere, so we can see how much light we may detect with increasing wavelength, and we can detect most of it if it's in one of the windows of the atmosphere. But if instead we put a molecular species in the way of that light and bounce it off that, transmission, reflection, or some kind of way of interacting the radiation, we can then start to stimulate molecular vibrations. And in fact, in that case, stimulate molecular vibrations in the skin. Okay. And then when we see what we've detected, we can actually detect all of the molecules in the skin. And that's because these molecules are being stimulated by the mid-infrared light. But clearly you can have all kinds of molecules in the way of that mid-infrared beam and start to have their signature on the light when you detect it. So the mid-infrared isn't going to be for telecommunications, that's near-infrared and silica fiber and long-distance haul communications. But the mid-infrared will open up a new sensing era in photonics. I know that the last speaker spoke about photonics, and many people say last century was the century of electronics, and this century is the century of photonics. So this is, of course, we're at the speed of light as well, which is an advantage over electronics. So the skin is composed of biomolecules. My particular thing is that I would like to be able to detect cancer from non-cancer. Many scientists are doing this actually with tissue from all over the body that's excised, and one can distinguish cancer from non-cancer tissue, but I'd like to try and do it through fiber optics, through a new type of endoscopy if possible. So here are the types of, sorry, it's displayed a bit, but these are the many kinds of biomolecules that one can detect in skin. So there are lipids, there's DNA, nucleic acids, polysaccharides. One can detect all of these biomolecules, but it tends to be as an envelope, okay? So I was part of a European push where we got at last some decent funding. This is why Brexit has been so painful for the UK, because we've been stifled for funding for a couple of years now, but we've just got permission to go into EU applications. So please listen. I think the British government is going to pay our way, just like Switzerland does for the Swiss researchers, so that we can start to enter into proper Yeah, research again. It's so fantastic to be in a European research group of people. It's been very stimulating. So back in it then, I was part of something called an EU Minerva project, and within that project, we were trying to use mid-infrared light to look at disease. And what was published here by, this is the group down at Exeter University that was part of the push. And basically, this image you're seeing here is a colon tissue cut out, but this false color imaging is showing us where all the different biomolecules are. And what happened in 2016 was that we were able to go from a 5 micron what's the word I want? The detail is a 5 micron size to a 1 micron size, but that was simply by oversampling. So it's quite a slow process. So molecular sensing is direct, no labeling, no fluorescent tag, high contrast, quantitative, and widely applicable. And what you can use it for is to look at adulteration of food and drink. So this is some beer samples. We have a thing called shandy. I think Maurizio remembers shandy, where you can is what. So there's the shandy response because it has lemonade in the beer, and here's diluted beers. But also you can detect explosives, narcotics. And this is a polymer here with, it almost looks like a barcode. This is across the mid-infrared here. So one has a great potential for detecting gases, liquids, solids, for manufacturing purposes or for health purposes. All sorts of, fields are going to open up here. So now I want to talk a little bit about glass science. So this is a picture that I show the students, from the beer bottles here. The helicopter windows can be slumped in the way that we saw the meniscus telescope made. It's slumped over a former. Here's some photoluminescence from a fiber. And in fact, optical fibers are now being laid up in 3 places still in the world, and that's around Africa, in the Caribbean, and in Southeast Asia, in Bali and Indonesia. So still, this technology is being rolled out in the near infrared, and the world's being wrapped in these fibers. So in sort of preparation for telling you about our new laser work, I just want to show you where lasers are at. Now, this is lasers in a glass fiber. So just as the last speaker was saying, to put the fluorescent ions into the glass, if you have a cavity, then you can actually make the glass laze, and that's what's happening here. So this is a sort of commercial company, IPG, and what you can see is the development since 1995 going to greater and greater powers. And this is 100 kilowatts, amazing, out of a fiber that's probably about 4 times as big as the hair on your head, and used in cutting and welding in the metals industry. So, I mean, this has been a fantastic success story of great power, and factories having lasers, just like gas is piped around the factory and water. One can have laser light piped around, and then this is opening up a new technology. They're discovering all sorts of new things, like a donut shape of the laser beam gives better metal cutting and cleaner metal cutting. So this is still an ongoing story. So, okay, so I'm going to ask very simply, what is glass? And when I arrived at the University of Sheffield, John Parker told me, what is glass? Okay. And this is basically a snapshot of the latest definition. It's got more words in it, but it's an X-ray amorphous material which exhibits the glass transition. Okay, so what does X-ray amorphous mean, and what's the glass transition? X-ray amorphous means that when you shine X-rays in and you do constructive and destructive interference of the light coming out and see what's happening, but that interference can tell us about the periodicity, which means the distances between atoms in the glass. And the results that we get are that for a crystalline silica, this is a crystalline form of silica, we get some nice sharp peaks. And that's because there are repeated distances in the crystal. And this gives us this nice sharp X-ray pattern when we shine X-rays onto the glass, onto the crystal. But with the glass, you can see we just get this hump because there are so many different distances within the material, and this is smeared out. It's great because actually crystallography is a very hard subject. And so for glass, one can go into this in more detail and do radial distribution functions and so on. But as soon as we get this, we know, we're getting our glass that we wanted. And so this has been shown before, but this is the random higgledy-piggledy on a 2-dimension, and this is just showing the repetition of the sort of spacings throughout a crystalline ceramic there, as opposed to something. So going for an atomic walk is slightly different in a crystal and a glass. What's the glass transition? This has also been shown, but I do want to tell you that I think this is the most important diagram in glass science. It really tells us where we are. And what I do with the students is I do analyze it. So basically, if we take the liquid and it freezes at the melting temperature, we can get the crystalline solid. But if we cheat on that ordering up of the atoms to make a crystal, then we can just keep going down. Whoops, sorry, I've gone a little bit further there. So we can just keep going down in the liquid state, which becomes so sluggish and thick it can't move anymore. And so then we have this change from liquid-like properties to an elastic solid in the glass transformation region. Sorry. The point I wanted to make here was that you can actually take the glass and you can reheat it above the glass transition temperature for shaping. And then you can come back down again to the glass. And really that's the basis of the 100% recycling that we know that glass is capable of. Glass is a very clean green. This is why it's the United Nations International Year of the Glass. We can get the recycling because we can go up and down that path backwards and forwards to reshape and make what we want and recycle the glass. So it is a very important concept. And this is just to show students who didn't get it from the diagram that you can supercool, go through the glass transition, make a glass, but you can also go up as well. You can go back as far as the true melting temperature or just into the supercooled liquid stage for doing all of your molding of glass bottles and so on, just keep going round and round in that way. So I also learned these things at Sheffield. It's only correct to call the material a glass below the glass transformation temperature. Glass is a state of matter rather than a particular material. And so you can have glassy metals, glassy polymers, you can have glassy anything. In fact, the Nobel Prize in 2016 was awarded to Lausanne for glassy water. So you can have glassy anything. And okay, in theory, any liquid, if cooled fast enough, will form a glass, even water. So now to my glasses, my glass science and technology. So we've already been shown this little structure for silica. This is a tetrahedral distribution. So this one's coming out of the plane of the paper, and that's going back into the plane of the paper. And so silica, the silicon surrounded by the 4 oxygens in glass is actually very uniform. It's just the way these things are strung together with different bond angles and different bridging, different lengths of bridging bonds that makes the glassy structure. So if we instead look at my glasses, so basically my glasses, I've got germanium instead of silicon. So I've gone one down to a larger atom here. And instead of oxygen here, I've gone down all the way down to selenium, which again is very large. So I've got large atoms here. They have weaker bonding. And so going back to thinking about that vibration, the Szigeti vibration, it means that these kinds of materials will allow much longer wavelength light through much lower frequency light through the material. So this is the material we've been making. And as you can see, it's opaque to the human eye because it's transparent to mid-infrared radiation and not visible radiation. And here's the problem, going back to the most important diagram in glass science. If you're not careful, if you don't do things properly and have the right composition and cool it fast enough, then it crystallizes. So it looks as if I've wrapped this in aluminium foil, but no, these are crystals. Okay, so that's actually crystallized in from the surface there, and you can see the crystals under an electron microscope here. And even better in the next slide, where one of my students has taken this beautiful optical micrograph. Here's the glass, but here's the crystals growing in. So we have to fight crystallization. I guess because these chalcogenide glasses, as they're called, because they come from the chalcogen, a group of the periodic table, which starts with oxygen, but we don't include oxygen, sulfur, selenium, tellurium. Because they're more weakly bonded, this manifests in all sorts of bad things, like they want to crystallize more easily. They perhaps have lower mechanical and chemical properties than silica. Okay, so what we do is in the lab, I've tried to pick out some pictures of women here to show we do hard work. And what they're doing here is they're batching. We have a glove box and we have less than 0.1 parts per million water and oxygen in the glove box. But 1 ppm is enough to give us a loss of 1 dB per meter. And if you remember, the telecom fibers were 0.2 dB per kilometer. So even the glove box is not really serving us well enough to get the high enough purities of the glass. So we have to work hard at that. Then we have to seal the batch into melt containment. We now have turbo pumps to replace this, because as somebody pointed out, if you've got oil-based pumps, then you risk putting the oil vapor into your materials. So we've gone to turbo, which is oilless pumps. And then this came out of a thesis that Maurizio examined. I don't know if you can remember the picture, but basically the chalcogenide glass is very viscous, and you can't get in to stir it because it's locked inside a silica glass ampule. And so what we do is we rock the whole furnace during the melting cycle, just to get the glasses nice and homogeneous. And in the beginning, they were rock and roll furnaces, in fact, because the tube used to be rolled. And I think we were given one at Sheffield, weren't we, by Savage? Do you remember? I never actually commissioned it, but we just roll. We just rock. And then this is showing very crude quenching of that glass, of the liquid melt, to bypass the crystallization, go through the supercooled liquid, go through the glass transition temperature, and obtain our glass. This is crudely just plunging it into water, but we can also use a liquid nitrogen jet on the outside and things like that. So the chalcogenide glasses have what are called low phonon energies, which is manifested as this mid-infrared transparency. High refractive indices, so much higher. I think normal silica glass about 1.5, whereas we can go up to the same refractive index as gallium arsenide, which is a semiconductor that's very popular. We have large optical nonlinearities, and we can write gratings in the glass because they're photosensitive. They can be rare earth doped, and they do have sufficient mechanical and chemical robustness. We can't do the vapor deposition as for silicate glasses because we can't put congruent materials down, because everything has different vapor pressures and they're quite complex formulations. So what we've invented and what we're trying to pursue, we're kind of world leading in this, and it's now rolled out to Australia and also Denmark and Poland. So people have followed our lead in this. So this is called extrusion, not really of a glass, but extrusion of the glass melt. And what happens here is that we can load in 2 different types of glasses into our extruder. We have a hydraulic load here. We have a furnace to heat up above the glass transformation temperature to do our shaping and then cool it down again. And we can end up with, as Wilfred was saying, a core and a clad. This is just a cut through the cross section. So that blue is the core, and it's concentrically surrounded in this red glass, which is the cladding. So that's the way we make our preforms. And this is an example of a preform, and you can see the extrusion process through the die. We graphite line the die so that it slips nicely through the die. And as you can see here, the tolerance was on the outside diameter of this rod was plus or minus 4 microns on a 1/4 of a meter long rod. So it's quite a precise process. And you can see here where it's fractured, you can actually see the core and the cladding structure here. So the next thing to do would be to draw that to fiber. So what we do is make some tubes. So the tube here is 10 millimeters outside diameter and a 0.9 millimeter orifice down the center. So I'm going to zoom in and look at that orifice. I think you can see the hole now. And this we do by having an extrusion die that has a little pin in it. The pin has to be sufficiently stiff because when we didn't use a stiff pin, the pin precessed and made like a spiral hole down the center. So we've had to develop that carefully. And then what we can do is we can put a cane inside the tube and draw to fiber rod in tube, as was mentioned before. So this is we're very fortunate to have a clean room, a 10,000 class clean room, because if you swing around as a human being just once, apparently you throw off 1 million particles. So we ourselves give off a lot of rubbish into the glass if you're not careful. And what we can do is we can make a core clad that's quite large so that it takes many rays of light down it, or a core clad that's small, so we can make this down to 4 microns diameter if we just want to restrict the number of rays of light that go down. And we can draw sulfide fiber, so this is orangey in color, the selenide fiber, and this last one just shows the dancer to get the fiber onto the drum. So this is how we would draw down our preforms to make this weird optical fiber. Okay, so just recently, one of my PhD students has realized actually, if we had near infrared eyes, we would be able to see inside this glass. So what he did was we had a fiber where you can see the core wasn't really interacting very well with the cladding. It hadn't stuck in there during the fiber drawing process. And when we viewed this under mid-infrared light, you can see for this fiber, you can actually see this pipe, and that's actually that core glass in there, but we can see it, we can see we've got a problem. And so we can feed that back into the manufacturing process. And also for preforms, we suddenly found we got some bubbles. Now we think these are vacuum bubbles because mainly, but sometimes we can get a tiny bubble inside a fiber that lasts for 1 meter of the fiber. So it's one of these being drawn down for 1 meter. But obviously what we need to do is optimize our manufacturing processes not to have, this is about, I think it's about 5 millimeters across. I mean, it was incredible when we saw this, and we realized, you know, that we have to perfect our manufacturing process to get rid of that. But it's a very neat way of looking at what we've made. So just to go into a little bit more detail on these glasses, yes, they are more weakly bonded. Now, the Young's modulus is when you stretch something, it's how stiff it feels. That's the Young's modulus. It's actually called the elastic modulus in the United States, but Young was, I guess, a British scientist. Round about a fifth of silica glass. And actually, all of the mechanical properties go pro rata. So everything about chalcogenized is about a fifth in terms of the mechanical properties. But the hardness in terms of window glass being 5.5 is about 2, so a bit lower than half. Now, the fluoride glasses, so we were discussing fluoride glasses actually taking telecommunications across the Atlantic because they're theoretically more transparent than silica glass. But the big problem is that fluoride glasses are actually attacked in water. And I've done experiments myself on this, and within half an hour I had crystal growth due to water attack of the surface of the fluoride glasses. So this has actually stopped production of some active components by 2 companies, one in France and one in Denmark, because the products, they made lots of products, but they sat on the shelf and weren't reliable. So the fluoride glasses have got a bit of a bad reputation for all non-silica glasses. But what I want to say is that the chalcogenide glasses are very stable in liquid water and in water vapor, and they're not oxidized in air, apart from a nanometer of oxidation, which is very like silicon. Actually, silicon within half an hour does oxidize, but only a nanometer, you know, and then that passivates the surface. So we've had plastic coated and uncoated chalcogenide glass fiber just lying around the lab, not looked after, and the ultimate fracture stress medium is 80 megapascals, which I believe is about the same as bottles, glass bottles. Okay. And we've had things maintain optical truth. It shows how long I've been working on this for 7 years. We've also proved, because we want to roll out our fibers into some kind of endoscopy if possible, we wanted to see what the cytotoxicity is. That means whether they're going to kill human cells. And what we did was we put our glass fibers into water-based media for at least 14 days. So the water didn't attack, and we actually had human cell growth on the surface of the fibers themselves, as long as they were arsenic free. Clearly, if you're going to put arsenic into your glasses, that's sort of bad news. And basically the arsenic wasn't too bad, but if we put hydrogen peroxide on the arsenic and got some arsenic oxide on the surface, then the cells didn't last a few hours even. So clearly we have to choose the composition carefully for whatever we want to use them for. And this is a group in the United States. I prefer to quote their work because it's independent of our work, but they have reported very high power densities down fibers. These were sulfide based without fiber damage. So there is a possibility of them actually carrying reasonable power. The big problem in the mid-infrared is because we're new and because you can't walk into an optics shop and buy what you want. So, you know, we can't go in and buy a dichroic mirror, for instance. We have to specially, oh, is that all? Okay, I better whiz through. So let's go through to this work that we've just published. So basically in 23 years, people are trying to push to longer and longer wavelengths of fiber lasing, and they only pushed out 0.02 of a micron in 23 years. And then we started working on these fiber lasers in 2010, actually, so a long time ago, trying to develop in chalcogenide glasses. The reason being that chalcogenide glasses have a much lower deactivation of excited states that will give you potentially the lasing. So you can see that the gradient there is very different from all of the glasses, which is good news for if you want to have lasing in your fiber. And here's the periodic table showing the chalcogens and the rare earth ions, and the fact that we put in some complexing agents to help, just as they do in silica. This was where the field was when we began. So this is emission across the mid-infrared, nice fluorescence here of rare earth ions. And the first thing we did was made sure that we could dissolve our ions in. I'm a chemist, so this is a Beer-Lambert law of looking at the area underneath the band of the rare earth ions as we increase the concentration. And basically the blue line shows nice linear characteristics. So that's a good solubilizer for getting lots of rare earth in there. So we cheated, I guess, because we went for cerium. Now in the cerium has UV absorptions up here, but in the mid-infrared, there's only two states, which means there's no possibility of the electrons jumping higher up. So it's an easier system. And basically, what we can do is there's a ground state there, and there's a hot transition into the second ground state there. And then these are the emissions that one would get, or sorry, they may be the absorptions, I can't remember. So those are the absorption bands. This is just the two glasses that made the core and cladding, and this is the loss of the fiber. So it's quite lossy, and here's the cerium absorption band that we're going to pump into. Here's the just the characteristics of refractive index of the glass that we made. And this is just showing that we pumped in band. So this is the emission bands here, and we pumped with a pump laser to see if we could make a cavity and make a laser. So we had long lifetimes here as well of the excited state. So then this again is just showing the fact that we were pumping here. So this is a two band system and hoping to get emission. And this is the setup here. So unfortunately, we didn't have a very transparent window here at the other end of the cavity to actually measure how much lasing light there is. But this is the laser characteristic that we got. And this is the first one above 4 microns, let alone above 5 microns. So we were very pleased to obtain that result. And the threshold was about 86 milliwatts here. So that was the first in the world. And I want to pay tribute to the PhD student writing up his thesis in Trinidad and Tobago. This young man, he spent all of the lockdown when we were all staying at home. He locked himself in the lab and made it laze. So it's brilliant. And I want to just show you some Russian results. So this is our competing group, if you like. They got lasing in the same year as we did, but in bulk glasses. And this is the diagram that I want Mauricio to explain to me, because it's quite nice. They've got 36 milliwatts out of their fiber laser. They've managed to measure the power out. We've just got funding to do the same, so we want to see what we get. But this is a very strange characteristic here that they say they get. It's very spiked. So maybe Mauricio and I have to study their paper and see what's going on there. So my conclusions, we've got narrow peaks. We've got a threshold at 86 milliwatts, evidence of fiber lasing. So it's proven as a host for mid-infrared direct lasing. And of course, having a laser like this means that you can detect molecules in the mid-infrared, but also we can use it to pump what's called a supercontinuum, because we've made a supercontinuum also, which I haven't presented today. So we could think about an all-fiber system for something like an endoscopic application or some other application. So these are all our sponsors, which I thank. And this is the wonderful group. Very multinational, and here's the young man who did the fantastic work. And thank you for listening.
Thank you very much for this very nice presentation. You gave a very nice insight. There are questions? Yeah, please, Luisa.
Oh, yeah, I have the projector in front, so I stand up at the project. So thank you very much. Now, the technique you have been presenting, this is a new approach. And you said to stay tuned for the future. So, but in the future, what is, in your opinion, the big jump achievable in a short time scale?
Oh, that's a great question. So everything's poised for going, because we have. Perhaps I can stand here and then you can have that one. Yeah, okay, that's a great question. So we now have a supercontinuum, which we helped to, it's commercially available now, and we helped to make that. The supercontinuum is a laser, but it gives out a broad rainbow of light in the mid-infrared. So that's a suitable bright source now to shine onto tissue. So these are the experiments that we're going to do next, and hoping to get some feasibility on that for getting more grant funding. So definitely that, but also on the fiber lasing side, we want to measure power out, because we've had a sneak preview at some other Russian work, and it's firing us up to, it's like the space race, I suppose, to try and beat them, so that in terms of over 100 milliwatts being given off by one of these lasers, which opens up a whole new field actually, because as you can see, it was below 4 microns before, so we can start to push into the mid-infrared, use them for gas sensing and so on. But I think really in the near future, it requires us to collaborate with people. I think collaboration is a great way. We know certain amounts of the field, but people who want to use these systems, I think those are the people to try and collaborate with, to push it as fast as we can. Does that answer the question? Thank you.
Okay, thank you very much. Other questions? Yes, please.
Thank you for your speech. A curiosity, at the beginning you showed us a picture in which there were some germanium selenide crystals formed in the glasses, in the unlucky experiments in the glasses. Is there the possibility to melt them down again to recover and or is there a sort of hysteresis or?
I think it's the same answer as Wilfred. When you've made a fiber, there's so little glass, and you have to sort of look after every stage of the process to get a nice transparent fiber. So we've also got the best transparency fiber that's been made, but that requires a lot of attention to purification and particularly getting the right composition. I mean, going back to the Venetian glass that was talked about this morning, I've heard that the Victoria and Albert Museum in London has 15,000 pieces of Venetian glass, wine glasses from the 1600s, but they're all crizzling because they were the wrong composition. So it just shows you that getting the right formulation is absolutely, and the ones that were shown to be crystallized were just the wrong formulation, that's all. Once you get the right stability, and you can, we do that via thermal analysis. We see, where the thing's going to crystallize and if it's sufficiently robust and stable against crystallization. That's always the thing. Does that answer the question?
Yes, thank you.
Thank you very much.
So I have also curiosity. When you show one of the last graphs concerning this intensity in the cavity, there were so many bumps centered in the same position but with different width. Yeah. Sorry, with different width. There were bumps.
Yes,
in the same position.
Were different pump levels.
Ah, this is due to that.
Sorry, I whizzed through it because
no, I just wanted to know if there was some physical effect. What was the physical?
I mean, I hope there's some new physics here.
Yeah, it's nothing to do with the that is an harmonic system, or is something that is connected to that?
I think there are different ground state levels, and this is responsible for the different peaks. And I think that they were building up okay. But
it's very interesting.
We have to remember that the glasses are actually amorphous semiconductors, and they do have a band gap. And the impurities in the band gap, because for a while, for 10 years we didn't get LASIK, and I did wonder if the pump light was going into the band gap and promoting. There are things called dangling bonds that are impurity levels, and your light could go in a different place entirely from where you want it to go. So the jury's still out on that, but the fact that the Russian group are getting good powers now, I think gives us some optimism. So, yeah.
But we talked later. Very nice. Well, thank you very much. It was very interesting and stimulating. So I think now we thank you again, and we move to the next speaker. This is very important talk to get ready for the ending of this nice day, and so it will give also some motivation for what we are going to drink later on. Okay, so please, sorry, I have to announce you. I was so excited about the topic. So is Eugenio Capparone from INFN Bologna. So the title is Glasses, Flutes, and Gobelets. Okay.
This is not the first slide.
Let me close it.
No, not the first slide. No, there is a problem on the. There is a problem on the. No, questo non è la. I have a problem with the presentation. I'm sorry. Cosa? Non è questo. Ho spedito quella sbagliata io. Ok, this is fine. Ok, come si va avanti dietro? Control L. Ok. Per andare avanti. So, first of all, let me thank Luisa for inviting me to speak about glasses from a different point of view. And when you accept to speak just before the coffee break, you have to make a commitment to be as short as possible. But this time is even worse because, as you probably know, we are supposed to toast just after my talk with a very nice Italian sparkling wine from the Franciacorta region. So I will try to be very short. Well, I had a tight relationship with glasses about 20 years ago when I was involved in the massive production of the multi-gap RPC, a very big effort led by Rosario Nania that is sitting today with us. And this was a massive production for the construction of a huge area detector, the multi-gap RPC, that was the key element of the time of flight detector of the ALICE experiment at CERN. And in this detector, the glass is the spacer that make possible the gap. in a very controlled way that makes possible a fantastic resolution of about 50 picoseconds. It was a huge effort, a very long one. And at the time, I started to think that it should be a more relaxing way to deal with glasses. And I thought that drinking wine was a very nice possibility. But this point of view is not widely shared today. So according with the Yale University Neuroscience Golden Shepherd, drinking wine is not relaxing at all. This is because in its point of view, when you start to drink, there are a lot of activities that your brain starts to make, and you are engaged a lot when making all these different cognitive computation. It's his point of view. I am not a neuroscientist. I cannot compete with him. Personally, I have a lot of fun when I drink something, but okay, maybe there are different points of view. Now, what is the role of the glass in the wine world? Basically, it's twofold. The first one is that wine makes possible the making of the wine, especially a few types of wine. And the second one is that, okay, glass cannot add anything, but it may help to maintain the wine characteristic that you risk to lose if you don't pay attention to the container of the wine itself. We may ask ourselves when people started to realize all these things, when they started to pay attention to the type of glass that we use to drink. The answer is that we started to pay attention since a lot of time ago, but in the wrong way. Centuries ago, the focus was on the aesthetic of the glass rather than on its use. This is a typical mistake. Elegant doesn't mean appropriate. This is the worst glass you can use for champagne. But we went ahead for centuries using it. And by the way, there is a study that tries to understand why this type of glass was selected centuries ago. A possibility, but it's just possibility, we could never have confirmation for that, is that since 2 centuries ago, the champagne was quite different from the one we usually drink today because it was a muddy liquid. And somehow this shape helped to concentrate the yeast at the center, making it a bit more transparent on the border. So this could be a possibility why they try to select that. They did not filter yet it. And so it was quite different from the one that we drink today. Anyway, it is a mistake. Now, the peculiarity of a champagne or a sparkling wine made with metodo classico is a peculiar wine when the carbon dioxide is dissolved in the wine itself. And there are about from 10 to 12 grams of dissolved carbon dioxide for each bottle of champagne. People at this point say, okay, but this is trivial. I get a very good white wine, I put inside the carbon dioxide, and the game is over. This is not correct, because if you do something like that, when you open it, immediately you lose all the carbon dioxide, and in few tenths of seconds, you have a completely flat wine. So the point is that you have to keep the carbon dioxide inside the wine, and you have to fight so that the release is as low as possible. Now, there is a very important law, that is the Harris law, that is very dangerous for divers, but is very important for champagne. And it says that the solubility of a gas in a liquid is proportional to its pressure. So high pressure in the deep water, you know, that gives more nitrogen to dissolve in your blood, and it's quite dangerous. But high pressure in champagne bottles keeps carbon dioxide dissolved inside. So you need an environment when you have high pressure if you want to keep the carbon dioxide inside. Now, what is the difference between a good white wine and the champagne? White wine has just one fermentation, the one that we know. The yeast are at work. You want to select very good yeast so that they give a good wine quality. You have the sugar inside the grape, and then you have this reaction. And CO2 is produced, but is lost. You can do it at open air, or you can do it in a controlled way in steel tank, but you don't care of the CO2 that you produce. The difference is that when you make champagne, you you have a second fermentation. And this is made by taking this wine. Then you have to put again yeast and some nutriments for the yeast, that is extra sugar. Then you put everything in the bottle, and this time you produce CO2, but you keep them inside the bottle. This is why the bottle of a champagne has several atmosphere of pressure, something like 7 to 8, and the fermentation is made inside. This gave historically a lot of problems, because we know that there is a legend that this was a monk named Dom Perignon, his name that we know quite well for other reasons, that discovered the champagne. The problem is that at the beginning, it was very difficult to control this process, and there were a lot of broken bottles, so that people came to believe that this wine was the divine wine, because it was very unpredictable and no one knew how to take under control this process. The answer is that if you want to make champagne, you need very thick glass, because you have to hold the pressure, and now usually the champagne bottle can withstand the pressure of about 20 bars. And let's say that the champagne is something that comes from our ability to produce thick glass bottles. So the big fight is to keep the CO2, and we will see in the choice of the glass. The choice of the glass for the champagne is basically a way to maximize the amount of CO2 you can keep. What you want to avoid, as I just said, is to lose all the CO2 in a single shot. And this is a picture that tells you why it's important to refrigerate the champagne. This is what happens when you open a bottle at 18 degrees, and this is at 4. You see that when the temperature is high, the CO2 is dissolved very fast, because it just accumulates below the cork. And once you open, the most of the CO2 is immediately lost. So keeping chilled the champagne is not only something that we do for us, for our usual taste, but it's something also that helps to preserve as much as possible and as long as possible the CO2. Then what we want from a champagne is called perlage. So what we want to have is a plenty of bubbles. We want them to persist as much as possible. We want to have high density, otherwise we do not appreciate it. And we want that the size of the bubble is small. Why? Because if you have a given amount of CO2, if you have a small bubble, you can have more of them. And we want a champagne rich of bubbles. Well, as I say, the glass choice was not properly handled for centuries. And the change of attitude came quite late. This guy was a chemistry professor, but was also a great businessman. His name is Riedel, and now it's you know, a brand that is very well known on the glass world. Riedel produced one of the best type of glasses in the world, and he started to realize that the taste of wine is affected by the shape of the glass. And since he was a businessman, he was very effective also in spreading out this point of view, that is more than a point of view, of course, and to make money with this idea. Now, about the champagne, the fluid is the right choice. Why? Because it minimizes the glass transverse area so that you can avoid most of the bubble dissipation. And it limits the amount of liquid that you may have the temptation to get with a single sip. You have to go slow if you want to appreciate some champagne. And also it allows the fingers to stay far from the liquid so that you don't increase the temperature, giving the side effect that I just described. And also, from a visual point of view, the fact that it's shaped in this way gives you the possibility to have long chain of bubbles so that you can appreciate the quality of the champagne that you have. It should be mentioned that nevertheless, recently, there were some criticism about the use of the fluid. This is because we went in a direction in which this shape was somehow exaggerated, and you cannot fit in few flutes your nose. And this is something that is because, of course, you cannot properly smell it. So the last trend is that you still have a flute, but slightly larger with respect to those that we use in the past. So if you go in a shop that sells professional glasses for sommelier, you will see that now the most of the glasses are more or less this shape, but are slightly larger than those we usually saw a few years ago. Now, the point is that, okay, this is what in principle should be, but when you drink wine, do you really realize all of these things, or it's just something that since you expect to have, then you try somehow to find also if this is not at all evident. So there was a nice, let's call it experiment by Bonera that was awarded as best Italian sommelier a few years ago, that organized a series of wine tasting in which he tried to see what happens if you taste the same wine in different glasses and to try to make a comparison. One of the things in which he insisted so much, although this is not intuitive at all, is that the shape of the glass does not affect only the tasting itself, but has an impact on the way in which the wine enters in our mouth. This is just a question of geometry. I'm not fully convinced of what he tried to explain. Anyway, let me just quote that in his opinion, there is something behind what I just illustrated. Now, let me go to the result of the testing. This is a champagne. It's a very nice one, by the way. And this was tested with the standard coupe I described before, and with one of the last trend in the champagne glasses. You see that there are several peculiar points on this champagne. For instance, the tasting of chocolate. This is something that is not very common in white wine. Chocolate is usually something that you can find in the red wine. The high minerality depends, of course, on the grape, and there is a smell of fruit and candied orange. This can fit with the standard wine. Is something that usually comes from the Chardonnay, that is one of the most important components of the champagne. What happens if you change now glasses? You see that surprisingly, all these orange and white fruit that you can appreciate with the other glass disappear. And you are left with something that has a slightly larger acidity, like the apple, and everything looks very smooth. This could be connected from the fact that you lose the CO2 more quickly. And the blind scoring of the wine gives 4 points less over 100. So let me say that this is something about 5%. Is not a huge difference. Nevertheless, this was repeated with tens of people testing, and probably the effect is there, and nevertheless is not a huge change in the scoring. Another one, this is a Piedmont wine that has a nice peculiarity, is a wine with very low acidity. It's named Dolcetto. And this dolcetto means sweet in Italian, but it's not a sweet wine. People sometimes, when goes in the wine shop, they want something for the dessert. They buy the dolcetto, but then they are disappointed because it's fully dry. So it's named dolcetto just because the grape is quite sweet, but this does not mean that the wine is sweet as well. And so in this case, they start with this small average size balloon, and they can find the cherries, spices. This is typical of Dolcetto. And tannins are not aggressive because this is medium body, it's not a full body wine. And it has a low acidity, it is a marker of the Dolcetto. But when they change slightly the shape of the glasses, you see that tannins are even smoother. And this is somehow expected because this has a wider area, and so you have more oxygenation. And this somehow tames the perception of the tannins. The difference is, again, not a very big one. Let me conclude with Sauterne. This is a Bordeaux region wine that is quite famous. It's a sweet wine, although to define the Sauterne a sweet wine is somehow a limitation, is much more. By the way, the best use of the Sauterne is not with dessert, but is with few peculiar cheese. And they used 3 different glasses. You see, we start with this one, and again, you have notes of orange and slight saffron. In my opinion, saffron in Sauterne is quite strong, but you know that each of us has a different feeling when we drink wine. For me, the dominant note of Sauterne is usually saffron, but okay, this is quoted as something slight. It's sweet and salty. This is not surprising because the sapidity of the Bordeaux region is new to be quite high due to the terroir that is in that wine. And it's not a great structure. Okay, this depends from probably the peculiar type of bottle they open. Sauterne may have a very great structure. What happens when we go to the champagne favorite glasses? It's reported they lose a part of its elegance, and there are a slight smelling of burnt. This is something I never experienced in the Sauterne, but is what most of the people reported. But it's very, surprising what happens when you use a cup. They report something like dusty. It's not easy to tell you what means dusty. It's something that is quite close to rusty. Somehow is a negative taste that you can appreciate, and the fact that it's present in the Sauterne and that is perceived just with a cup, this is not easy to explain, but it's something that was repeated twice just because it is something that is quite unusual to find in a wine. And nevertheless, that you can appreciate a remarkable difference between the different glasses that you have used. So the conclusion, I think that we should be really grateful to the first person that thousands of years ago invented the glass, because otherwise we could forget the champagne. I don't agree with Professor Shefferd. I think that wine drinking is quite a relaxing activity. And the glass shape is important. Given the small difference, about 5%, that we see on the tasting report, I don't think that one has to spend too much money for an average glass of wine. But if you have the passion, not only for glasses, but also for wines, and you spend a lot of money for a good bottle, I think that you have to try an appropriate glass in order to avoid to spend a lot and then to lose the best of the wine that you bought just because you have a glass that is not appropriate. So given the timetable, I prefer to stop because I think that drinking wine is much better than discussing about it.
Thank you very much, Eugenio. This was a very intriguing question. Lecture, not question. It was a very intriguing lecture. But before we go to do experiment, we might have other questions for Eugenio. It was very intriguing, as I said. I think they are looking forward to really to do an experiment. But before we do that, I think since we are at the end, I want just to say a couple of words. First, I want to thank all the outstanding speakers that really made this day very interesting. And so thank you very much. But also, of course, all the participants, because they made everything very lively. And I want to thank the SIF personnel, in particular, Barbara Alzani and Giovanna Bianchi-Bassi. I don't know if they hear me. But of course, they did a lot of work in preparation. And of course, the main organizer, who is Professor Luisa Cifarelli. But I want also to thank, because this event was decided when the president of the academia was Professor Walter Tega. So I think we really appreciate that he decided to accept this event. So thank you very much to him too. And so I don't know if Luisa wants to thank personally more. The INFN group, of course, they did. Yes, sorry. Sorry, because no, because they always do a very good job here. Also for in other occasions for SIF. So the INFN group, and Riccardo Loguglio. Okay, sorry. So this is the famous for also for the beard, no? Also famous for the nice beard. Very. Okay, so I think this was a very exciting day. I think we go back with a very good memory of this nice day. And we are ready for the experiment that was promoted by Eugenio Scapparone. And so thank you very much to everyone.